Welcome back, everyone. Leo and I are here for day 3 of the completely free Google Professional Cloud Architect Certification Bootcamp. My name is Mike Gibbs. We also are joined here by Leo Paredes from our team. He's over there in Sao Paulo, Brazil. He's got about 2 decades plus of engineering, a master's degree, and he's got a lot of demos for us to go through. So today we have about 2 hours of lecture, about an hour of labs. They should be kind of fun. They're in the networking world. Tomorrow we'll have a little bit of networking and compute stuff, and then we've got lots and lots of things to do next week. So we're back. We're happy to be here. We are excited to be here. So as a reminder, if you just joined us, you can go back to day 1, day 2, and day 3. They're on our YouTube channel, and go back and see the first several days of this Google Professional Cloud Architect Certification Training Bootcamp to prepare you for the Google Professional Cloud Architect exam. So we're here. We're here for day 4, and I hope you're all doing well. Now, I'm going to ask you for a hashtag, but I'm not really one for acronyms because acronyms really mean a lot of different things. So what I'm going to do is I'm going to put the hashtag in, and if you don't want to type so many letters, maybe you can cut and paste it. So give me a minute. Maybe you can give me a Google Professional Cloud Architect so that I know you're here. You can even cut and paste mine if you don't want to type so many letters. But every time I see PCA, all I think is patient controlled analgesia because all these acronyms mean different things. Then it puts me in the mindset that I'm at the hospital taking care of somebody. So let's keep it to the technology. Give me a hashtag Google Professional Cloud Architect, or abbreviate it if you want. I don't care. But we are just excited to have you here. So I see Wallace. Wallace, so wonderful to see you in London. I hope you're having a great time as an enterprise architect. It was always great seeing you. Jacques, wonderful to see you. Adrian, good to see you. Unable to download the study guide. So did you sign up for it and wait 15 minutes for it to be emailed to you? If you've waited more than 15 minutes, my team will find a backup plan. But 90% of the people just don't wait the 15 minutes for the email. So give that a few minutes. I'm glad you're all having fun. And if you don't get it in 15 minutes, send someone. Chris from my team will make sure you send it to. They'll email it to you or something like that directly. Okay, so yeah, Phoenix. I'm loving this. India, I see that, which is great. I haven't been there in a long time. And for example, Jacques, I love that. Every time you see, I always go down the clinical things. In fact, as a little joke, we used to have something called permanent virtual connections in the first cloud that I worked in. And what there were these switch circuits and frame relay networks. And I got a call at like 2:00 in the morning, and someone said, Mike, we're having a lot of PVCs going down, and I see you have to give a lidocaine bolus and then start this. And they're like, what do you mean a lidocaine bolus? So yeah, I definitely understand how it's so easy to take one thing and confuse it with another thing. So hope that helps. So anyway, let's have some fun. Chris, let's get with the content. Leo, before we do you want to say anything to everybody about your labs today?
Sure, Mike. Welcome, everyone. And today we will have some labs about load balancers and also setting firewall rules.
Load balancing and firewall rules. Well, I love load balancers because they increase performance and availability. And I love firewalls because they make things more secure. So fantastic, Leo. This sounds like it's going to be really fun. So Chris, let's roll with the content. You'll see us back in about 40 minutes. Ask whatever questions we can. We really want to do anything we can to help.
Let's continue our discussion on networking, and let's talk about access and inside of the virtual private cloud. So we talked about your virtual private cloud being your virtual data center, your private network that's all under your domain, where you put your systems in a secure, isolated environment. Now, what if you need to connect to other stuff other than just the stuff that's in your VPC, like your virtual machines? What if you had to connect to other services like Google Cloud Storage or BigQuery or other services offered by Google? Now, typically speaking, you could address them in a public way or you could reach them in a private way. So it all depends on what you actually need to do and where you need it. Generally speaking, you need an external IP address or a public IP address to connect to things that communicate on the internet, and use private IP addresses internally. So what if you wanted to connect to something in the Google environment externally? Well, then they have something called a public API endpoint, and an endpoint is something you're just going to connect to. So Google Cloud has public API endpoints that you could use to connect to, say, Google Cloud Storage. Now, you would typically need an external IP address to do this. But Google also has the concept of private Google access. And what is that really? It enables you, instead of taking your traffic from your network, going all the way out to the internet, crossing the internet and coming back into Google, for example, to just connect to something already in or located on Google using a private access through what I like to view as a private wire, a private network that gets me access to something. Now, it's all virtual, but to me, it's a private wire. So by doing so, we can keep things internal to the Google network, which is relatively secure, as opposed to sending data on the external network, which is not secure. By leveraging the internal network, we've got Google's control of the performance. Going on the internet means we have no control over the performance. So if we've got sensitive workloads that we want to send across Google, we use private access. If we want good performance and know that it's guaranteed performance, use private Google access as a general rule. Keeps all communication within the Google network. So we can also use private service access to get to third-party services that are hosted on other VPCs within Google Cloud. And this could be useful for accessing services that might be provided by somebody else on Google Cloud. And you still don't want to use the public internet to connect to them, maybe a third-party provider, for example. So the key here is this private Google access enables on-network private communication. It's designed with security in mind. It keeps your systems on the private network. It leverages private IP addresses. It reduces the risk of external attacks. We can integrate it with on-premise environments. We can extend private Google access to our data center, whether we're connected to that data center over a VPN or a private line, like an interconnect or a dedicated interconnect. But the point is it enables secure TLS sessions to your environment. So what this could look like could be something like this. You could have your data center connected to the cloud provider. And what this means is if you got a connection between them, regardless of what that connection is, you can access something privately that's on the cloud provider's network, if this is the something that you want to access. That's all it means. But this means it's very secure. So if we wanted to say, not go to the internet to upgrade software that we had, and the upgrades were on our premise, we could kind of push that kind of thing over here, over the wire. But it's just a private way of connecting. And here's the alternative. If we didn't do this, what we could do would be this, and I don't really think this would be the internet. And apparently, INTERNET. So the alternative would be to take our traffic, leave our data center, go to the internet, cross the internet, and come back in the cloud provider. It's not as efficient of an architectural option. There's no guarantees in performance, and it's less secure. Let's talk about some security considerations with the private service access. The point is Google is going to provide some fairly strong controls to ensure privacy and prevent security incidents. And they'll do this with the tenants that are sharing the infrastructure. It's going to require a careful assessment of the third-party offering, because the second you connect to somebody else, two people now you're connected, you've increased your risk. So we have that kind of thing that we need to think about, carefully assess what third party we want to use. So private access is there to increase our security. The key is it's going to maintain data inside of the Google's network, reduce the exposure to the internet. And in many cases, you may have a third-party software as a service provider that's attached to the same Google Cloud that you would be, and you can use this to connect to them. But you still have to do a risk assessment anytime you connect to somebody else. Now let's talk about cross-project communication. And what is that really talking about? It's communicating across your actual projects. So how do we enable that to happen? When do we want that to happen, for example? And we're going to talk about that. So it's going to be essential for communication between VPCs sometimes. Maybe you have two different VPCs and maybe they need to talk to each other about something. And sometimes your company, many times you will own multiple VPCs. So you're going to have to find a way to enable them to speak to each other. Now we have this concept of a shared VPC. And a shared VPC basically allows multiple projects to connect to a common VPC to be able to access things securely. So that's some things that we can typically talk about is a shared VPC. And that's going to allow multiple projects to share a common VPC for secure communication in the same space. This makes centralized management easy. And the projects can basically attach to things. So it's going to be great for organizations that require controlled environments and clear governance while basically allowing it pretty easy. So if we have a shared VPC, it's going to look like something like this. We're in our environment. We have two different things at the same time, two different projects that need to talk to each other. And they're talking to each other through the shared VPC. Now let's talk about VPC peering and what it actually is. So VPC peering is when two VPCs need to talk to each other, we're going to connect them. And by connecting them, they'll be able to share information, what have you, share services. So if you think about it, it's not a lot different than taking two networks and connecting them together. And that realistically is, quite frankly, all of net. So let's say we have two organizations, and it can be two separate organizations. It could be organization A is VPC. And we could have organization B. And maybe they need to talk to each other. So what we enable is VPC peering. And now they can talk to each other. Now, why would we do this? They're going to connect over the Google private network. So this is going to give us some relatively good performance. Now, understand the moment organization A decides it's willing to connect to organization B, we've got some security risks. So we're going to need to secure this. But here's another way you might use VPC peering. An organization might be very concerned about finance, about their security, and maybe they put finance in one VPC, and then we've got the leadership in another VPC. And then maybe we enable the leadership to the finance VPC so the leadership can see the things that are going on in finance, like the executive leadership VPC. So that's what we're talking about VPC peering. Now, VPC peering by default is non-transitive. Guess what? IBGP peering is also non-transitive. So for any of you that are used to IBGP, it'll be very clear for you to understand what non-transitive is. If you're not a networking person, that's okay. I'm gonna map it out for you, and I think it'll be pretty clear at the end. I'm doing this because it was an icky concept when it was first taught to me, but once you understand the concept, then it becomes fairly simple to understand. So let's say this is a finance VPC. Let's say this is a sales VPC. And then let's say this is a networking VPC. I don't know. I don't care what it is. Doesn't matter. These are just arbitrary concepts. What happens with VPC peering is the finance VPC can be selected to the sales VPC, and the sales VPC can be connected to the finance VPC. But there's no transitive routing, which means if finance can talk to sales, which is good, networking can talk to sales, which is good, but finance cannot talk to networking through sales. So the only fix to an environment like this, there's really two fixes when you have non-transitive routing, and I'll show you what they are. And they're going to, realistically speaking, you'll have two options. Option one is to what's called fully mesh them, which is every VPC would be connected to everybody. And by doing it this way, sales never has more than one connection to either the finance VPC or the sales VPC. Networking is never more than one connection away. So here, everybody can talk to everybody. But the problem is we run into this icky formula, which is n times n times n minus 1, which is going to be, and then that'll be divided by 2. So what does this mean? And this is, let's change this to an asterisk so you can see it. Well, what this means is very simple. In an environment with 3 routers, we have 3 times 3 minus 1, which equals 2. And then we divide that by 2. So we need 3 peering sessions. Equals 3. Now what happens when this is 10? We have 10 times 10 minus 1, right? 10 minus 1, which equals 9, right? And then we divide that by 2. So we now have 100. We now have 10 times 9. 10 minus 1 is 9, which is 90 divided by 2. So we have 45 peering points. So this is not going to scale long term, which is why in networking, we created things like route reflectors. It's the reason why AWS has like Transit Gateway and Cloud Hub, all for these reasons. So just keep that in the back of your mind. This VPC routing is not transitive. And now you understand what VPC peering is. Now, we also have the concept of a VPN gateway. And that's going to connect different projects or regions or what have you with an IPsec tunnel or a TLS tunnel or a VPN tunnel. And this is going to be used when you need to securely connect certain VPCs over the internet. So let's say you had an environment where your sales VPC was one that it was on the internet, and this sales VPC could have been maybe it could have been on the AWS cloud. And then maybe your finance VPC is on the Google Cloud. And maybe your network VPC, we should probably call it VNet because it is in Azure. But what we're talking about here is if we have a VPN gateway, which is the equivalent of a virtual router, we can create, call that a VPN gateway, and every provider has their equivalent of it. What we can do is we can create IPsec tunnels or secure communications across the internet to connect our environments, and that's what we need to use as a VPN gateway. A VPN gateway could also be used to connect any environment to anything with a VPN. So I hope that makes sense. So let's see this out. Here you can see I've drawn an environment of Google. This a finance VPC, which is on Google. I have a sales VPC, which is on AWS, and I have a networking VPC, which is on Azure. So all of these, we could be using the internet connection from Google to create an IPsec tunnel to another VPN gateway to our VPC on AWS, and we could have a different IPsec tunnel connecting them all together via Azure if we wanted to. So this would be one place where we'd use a VPN gateway. We might also use a VPN gateway if we've got a sales VPC on the Google Cloud. I'll show you another example where we'd use a VPN gateway because I really want you to understand where these are used, architecturally speaking. And the other place the VPN gateway could be used, let's say you've got a data center and it's connected to the internet. You could create an IPsec tunnel to the VPN gateway and reach your VPC that way. So VPN gateway just means router or device like a router that connects you to something. So that's a typical environment of a VPN gateway. We talked about a couple of use cases here. We have this concept of cross-project communication. And typically speaking, we've got a usage pattern of a shared VPC. And that's going to be great for organizations that need centralized control with distributed development teams that require access to a common network. So think shared VPC. Simple administration. Your developers put their workloads in there. And that's going to be simple. But now everything can talk to everything in the VPC. Now we might want to segment our system into multiple VPCs. And that we could use for security, and then we could use VPC peering to connect them together. We could also use a VPN gateway to connect to our VPC in multiple hybrid cloud computing environments or connecting to other clouds. Now, every method we're going to choose has its architectural strengths and its architectural weaknesses. So what we have to do is evaluate all of those strengths and weaknesses and then pick the thing that's going to be best for our environment. So let's talk a little more about the shared VPC. So the point is to give you that strict level of control. It's going to use, as I mentioned earlier, private IP addressing, but we're going to have this host project in the concept of a shared VPC. And that's going to act as the control plane where the VPC is and all the network elements are going to be provisioned. This is going to be centralized networking, centralized security policies that are all going to be defined in this host project. And service projects will be able to leverage the host project for network resources while still being independent in their operations. Let's talk about service projects, and they're going to connect the host projects to a shared VPC. And that means we're going to allow resources to be provisioned and assigned with these internal addresses in the shared VPC. And because they're all in the shared VPC, they'll be able to talk to each other. So that's going to make it easy for developers. And the billing is going to be attributed to individual projects, not the host projects. So you'll get clear billing to make it easy. So if we start thinking of an enterprise that have a lot of revenue generating business units that have to adhere to a centralized governance model, we can have each business unit running independently and manage its infrastructure and still adhere to the overall organizational security policies. And at the same time, separate a bit the business to different business units, and then we can have a chargeback where each department or each business unit could pay their cloud computing bills. With regards to scalability in the shared VPC, we can have multiple shared VPCs created within a single host project. And then we can have a service project that can only connect to one host or project at a time. So keep in mind that multiple VPCs can be created in a host project, but a service project can only connect to one host project at a time. And it's going to be commonly adopted in large enterprises to distribute cloud computing costs while maintaining secure and organized infrastructure. Now, with this shared VPC concept, we've got security and control. We can centralize, the network administrators can be centralized. They can define policies that govern the entire organization. They can ensure consistent security and compliance. And this is going to help allow enterprises to maintain a controlled environment and provide sufficient flexibility for the individual teams to do what they need to innovate and develop. The shared VPC is pretty easy from a billing and cost management perspective because they're managed at the service project level. And that makes it real easy to determine where the expenses are coming from and bill a specific business unit. And this is becoming increasingly popular among large organizations because of the ability to both provide control and still be flexible. So easier administration and flexible environment while still maintaining controls. Now, I know I talked about VPC peering and I drew it out, but I want to make sure we cover all the features you need for the Google Professional Cloud Architects exam. Remember, it's about letting two VPCs talk to each other. And it's great for organizations that have decentralized governance and different ownership of projects. Now, remember, separate environment. We can put a firewall in between and we can get very secure here. But at the same time, we have to remember that VPC peering is non-transitive, so we have to fully mesh our VPC peers if we're going to do something like that. Now, with regards to VPC peering, we have to think of the governance and ownership because we now could have two different companies or two different teams that are managing their own projects and their own VPCs, and now they need to create a connection between them. Now, when you connect to external entities, that provides business opportunities, but it also provides the risk. So think about who you're peering with and the security controls that you'll need in between these environments. Now, if we realize that the VPC peering is occurring on the actual network for Google, it's going to look and feel as if it was in the same VPC. The performance, because it's all on the same cloud. No latency by doing this, by connecting to different VPCs on the same cloud. Now, we can put firewalls on each side to only allow, say, certain IP addresses even coming in. We can use firewalls that are adaptive. They can look for patterns of anomaly, intrusion detection, and potentially block things dynamically. So lots of times we have business units that need very isolated environments that need to exchange information between a subset of its users. We can use VPC peering and strong access controls, strong firewall controls, and really protect these environments. Now let's talk about Cloud VPN. So Cloud VPN enables secure connectivity between the Google Cloud VPC networks and external networks. It's a VPN. And effectively what that is good for is a hybrid cloud environment where you want to connect your Google Cloud VPCs to another network, such as an AWS VPC. And we talked about this, how we're using some form of a VPN environment to create these IPsec tunnels. And in this case, we've got a transitive IPsec tunnel. So Cloud VPN provides an IPsec tunnel that is secure and encrypted, but it allows transitive networking. So that means these devices can talk to each other with Cloud VPN. So that could be great, or it could be a security nightmare. And let me explain what I mean. In a non-transitive routing, for example, so let's say this is in non-transitive routing, if we had three separate VPCs, VPCA, VPCB, and VPCC, in non-transitive routing, if we're over here, what you can see is A can talk to the core. I'm just going to call it core to make it easier to look at. So C and A can talk to each other, non-transitive routing. But you know what? From a security perspective, B can talk to C, or can talk to the core, but A has no ability to talk to B this way. So in non-transitive routing, we have no ability for A to talk to B, which means A can't hack B through the core of our network in non-transitive routing. Now in transitive routing, it changes everything, and Cloud VPN provides transitive routing. So with transitive routing, if the core is connected to VPC A, and the core is connected to VPC B, and the core is connected to VPC C here on the bottom, then A will be able to talk to B and C through the core of our network. So Cloud VPN is transitive, which is great when you want an environment where multiple VPCs need to talk to each other. But that means you now need to plan for the security. If it's non-transitive, their systems are inherently secure. They can't reach each other. Transitive is much more scalable, but it requires much more careful network planning. So Cloud VPN is great for hybrid cloud environments. We do have to understand there's some throughput limitations that you're actually dealing with. Direct peering is typically about 3 gigabit a second, so it's still not that fast. And internet-based VPNs are typically based for 1.5 gigabits of throughput, which is going to be a bottleneck in a lot of high-demand environments. Cloud VPN enhances the throughput, and hopefully they'll continue to update over time. But it requires the management of multiple VPN tunnels, the knowledge of the routing to make that actually happen. So, Cloud VPN can be great, but network architects need to really help you as a cloud architect, for example. Let's talk about cloud DNS. And what is DNS? It's the domain name system that maps a name to an IP address. And Google has a DNS available to you, and it's a managed service. They provide internal DNS, which is going to be, for example, you will have a DNS-friendly name to some degree for every single system you have, like your virtual machines, your load balancers, whatever. So you can connect to it with a fully qualified domain name as opposed to an IP address, which may make it easier if you need to change IP addresses later. So a fully qualified domain name looks like this. It will have something called a host name. And let's say we do, and the host name could be Mike. Then the domain name could be Go Cloud Careers. .com. Now what you'll see here is you have the top level domain, which is .com. We have our domain, which is gocloudcareers.com. And then we have the host name, which is Mike. That's the basis of a fully qualified domain name. Google provides this. You've got your internal DNS for your internal DNS records, because you might want to access them via DNS name. Now, Cloud DNS is a managed service that offers the ultra low latency, high availability. They say 100% SLA. And that is an authoritative DNS server that you can use for your internet, publicly faceable, internet visible environments, and your private, your internal network of visibility. And, that uses the DNS addresses that are typically known by Google. They're Anycast addresses of 8.8.8.8 and 8.8.4.4. These are the two addresses. They are Anycast, which means they're going to be there. I'll show you a little bit about how Anycast works, because I always thought Anycast was the coolest thing. So in IP networking, what we really need are devices to have unique addresses every single time. But Anycast is a little different. So the way Anycast works and Anycast DNS works is we're going to have two DNS servers, and they're both going to have the same IP addresses. So let me show you why why Google's doing this. It's for a high availability thing, and it's great. We use it for multicast. We use it for a lot of things. So both of these are the same IP address. And let's say this is the internet. INTERNET. And let's say I've got a user over here, and my user over here is in Miami. And the closest Google DNS server, wow, as it turns out, is actually in Miami. So when the user goes on their browser and types www.gocloudcareers.com, this user over here, the DNS server that's sitting in Miami with the address of 8.8.8.8 is going to reply. And the user in Miami got a fast DNS response. Now, if for some reason this DNS server in Miami were to get sick and die, or the server crashes, or the group of servers crashes, guess what? I will make my www.gocloudcareers.com request on my browser, and it will look at my hard-coded DNS addresses, which are sitting inside of my server, or the ones I obtained via DHCP, and it'll say go to 8.8.8.8. And since the local server is not there, the next 8.8.8 I'll reach. Now, maybe the next 8.8.8 is in Raleigh, North Carolina, but at least I can reach it. So when the local Miami one is there, I use the local one. But if it's not here, for some reason, the internet routes me to the next Anycast address. Google uses Anycast, a great DNS provider. The question becomes if you have a 3-cloud environment, should you manage your own DNS? But the Google DNS is excellent DNS service. So if we think about that, we have to think about cloud DNS use cases. We could use it for internal DNS. We can use it for external DNS. So we've got a lot of here. But if we're using cloud DNS for internal DNS, private zones must be configured, and the VPCs must be authorized to use these zones. We can also do DNS peering, and that enables the querying of private DNS across different VPC networks without needing to connect to the networks directly. This is going to be particularly useful in hub-and-spoke networking models, where DNS peering is going to enable DNS queries from spoke VPCs and hub VPCs in a hub-and-spoke environment. I had drawn a hub-and-spoke environment with one of the architectures I had showed you, so let me show you what hub-and-spoke looks like again. This is particularly a hub-and-spoke environment We've got a hub site, which we have here listed as C, and then we have these spoke sites. This is called hub and spoke networking. You may notice that you also see this in air travel as well. So I live in South Florida, so Delta is most likely the hub that I go to. So Delta has a hub in Atlanta. So let's say I am over here. If I want to leave Palm Beach and I want to go to Greece, for example, I might actually have to leave my house in Palm Beach, jump on a plane in West Palm Beach, and then fly to Atlanta. And then from Atlanta, I might be able to grab a flight directly over to Athens, Greece. See, airlines use a hub and spoke model too. With regards to DNS peering, again, it's going to enable DNS utilization across different VPCs. So let's talk about connecting to the cloud providers, because we're going to have some connectivity. And how do we determine what kind of connectivity we need? We have to determine what our needs actually are. Do we need a guaranteed amount of bandwidth? If so, we have no choice but to use a private line. Do we have flexibility in the amount of needs we have? If so, it may be a lot cheaper to use a virtual private network, which is typically an IPsec tunnel, or it could be a TLS tunnel through the actual internet. So we need to determine that. So that's going to be absolutely critical. So we need to determine the bandwidth we need. We need to determine what service level agreement. Do we need a guarantee or do we not? What level of redundancy do we need? And what level of cost do we need? You know, we might need an environment where we need extremely high bandwidth connectivity to the cloud. And if so, we'll get it. We may not, but the business needs are going to drive our networking needs. Now we have this concept of a cloud router. And realistically speaking, it is a software-based router the cloud provider has that exchanges routes between your VPC and your on-premise location. And it can be done via Cloud VPN, or it can be done through a dedicated internet. So what does that actually mean when you really think about it? Whenever you need to connect to environments, you use a router. So here, this could be your data center. You need a router. Now here, this could be your VPC. It doesn't matter. Your virtual private data center. And you're going to always need a router to connect these things. And you're also going to need a router to determine how to get to your various subnets. So realistically speaking, while this is a physical router that you might buy from Cisco systems, you know, we've got this virtual router that's running routing code at the cloud provider. So what happens is you create some kind of a link, and then what you do is you have to exchange routes, and you have to exchange routes via BGP. BGP is a fairly complicated routing protocol, but Mark Milovanovic and I made a completely free BGP 7-hour tutorial. My team will pop the link in the chat box to really explain BGP to you. There's also a whole lot of free cloud labs that you can also download that are going to help understand BGP. And you can, again, sign up for them. You'll find them in the chat box. My team will give that to you. So at least the key to remember is that it's just a router. And we'll use the router to basically connect us to the cloud provider. Now, with regards to BGP, obviously, we've got external BGP, which connects us to external entities. And we have internal BGP, which connects us internal entities to each other, so all using the single autonomous system. So how do you know if it's external BGP? You've got a different autonomous system connecting to a different autonomous system. In internal BGP, you're all in the same autonomous system. So this BGP speaker would say be in 65312, AS65312, and this BGP speaker will be an internal 65312. Because they're in the same autonomous system, it's internal BGP. But if it was 65312 of an autonomous system connecting to 65313 as an autonomous system, it would be external BGP. Now, there's a lot of rule differences beyond that. It is way beyond the scope of the Google Professional Cloud Architecture. So when we connect to the cloud router, we need to exchange routes, so we use BGP. If you recall, BGP is an exterior gateway protocol. It's used to connect to external entities. We are not the same company as Google, and that's why we will always use BGP to connect to them. The other reason the cloud providers make us use BGP is it is very scalable and it is very tunable. So because of that, it's one of the few routes that can routing protocols that can enable a company like Google to have tens of or hundreds of thousands of clients and be able to handle all those routes in the routing table. So that's why we use the Border Gateway Protocol. Now we have this concept of regional routing and global routing, and I want to explain what they both are. Regional routing shares routes and subnets in the specific region where your cloud router is deployed. Global routing will share all the routes from all the subnets in the VPC across all regions. So you're going to get much more broad routing and understand things much better with that. We can advertise a custom route. So with BGP, you typically what's called advertise a route. It's not like a normal routing protocol where all the routes are just there. We have to tell BGP which routes do you want to advertise. So we can advertise a certain subnet, but not a certain subnet. So think about that. If you don't have a route to it, you can't reach it. So what does that mean? It means that, let's say over here we have two subnets. We have the 10.0.1.0 subnet /24 that we want to reach, that we want people to be able to reach. But we also have this 10.0.5.0 subnet that we don't want anybody to reach. No reach. Keep unreachable. So if this is the case, what we do is we tell BGP to advertise, and yes, the term is advertise. I didn't make it up. It's part of the specification. We would tell BGP or advertise 10.0.1.0 /24. So by doing so, BGP will tell this virtual router or the cloud router only about 10.0.0.1. And what does that mean? It means if the router here has a packet that's destined for 10.0.1.0, it'll be sent. But what it also means, if there's a packet that's destined to 10.0.5.0, there won't be a route on the routing table for it, and the router will just drop the packet. And that's one way routing can enhance your security. If you don't have a route to it, you can't reach it. One of the reasons we use BGP. Let's talk a little bit more about Cloud VPN. It is a virtual private network. It enables you to create a secure tunnel over an insecure media like the internet. And by being able to provide encryption over an insecure media like the internet, we get three things. One is we get to make sure the hosts identify themselves. So there's typically a key. So if the two routers know the key, that means they can connect and they can talk to each other. So it prevents a man-in-the-middle attack where I think I'm talking to somebody, but I'm talking to somebody else. With encryption, the endpoints are identified. So if I'm talking to Cindy and Cindy's talking to me, there's a guarantee that we're only talking to each other. With encryption, we also turn whatever we have into gibberish. So if a hacker would see it, they couldn't understand what the traffic even does. And of course, we get message numbers or sequence numbers, something like that, with these SSL TLS type protocols, which provides the ability to make sure that the user can't say they didn't send the data after the fact. It's called non-repudiation. So we use VPNs for a lot of reasons. Often we use IPsec because it was a protocol designed exactly for this. And we can do a couple of types of IPsec with regards to the Cloud VPN. We can secure data between hosts, device to device, server to server if we wanted. We could do network to network where we could secure data between two security gateways, basically two routers across. And we could do network to host where we can basically share data between a security gateway and then a host. So we've got lots of options with regards to VPNs. And Cloud VPN can help secure connections. We can use it to secure connections from other environments and gives us transitive routing. So let's talk about the types of VPNs we can actually deal with. We have the classic VPN, which is going to support static routing and dynamic routing. It requires an external IP address for each VPN gateway, and it's generally not recommended unless there's a need for static routing. By comparison, and static routing is you tell everything which route to go. Here's the problem with static routing. If something breaks or changes, it doesn't heal. It's kind of like planning out static routing is like planning out your route and writing down directions. after you looked at a map to go from point A to point B. The problem is what happens if there's the roads blocked? You're stuck. Whereas dynamic routing will recalculate your route much like a GPS, so it's going to provide much higher availability services. And with a high availability VPN, we can connect multiple on-premise VPNs to a high availability VPN gateway without the need to manage them. So this could be used where you need flexibility. And realistically speaking, IPsec tunnels are typically cost effective because the internet's already there.
Okay, well, we are back. We are here for questions. We are here for anything we can do. Okay, I got to ask, isn't cloud networking cool? I mean, maybe I'm just a networking geek and I just love networking and all parts of networking, but I think cloud networking is cool. If you think cloud networking is cool, give me a hashtag cloud networking is cool. And if you don't, I understand that too, but it's still part of everything. So I'm glad we're doing it. Chris, behind the scenes, did any questions come in? Okay, so speaking of BGP, could you explain the BGP confederation and the way that works with autonomous system numbers? Absolutely. And Google Cloud, anytime you're going to connect via like a private line or something like that, you're going to use BGP. So let's really map this out. So what we're really talking about as to a confederation. And it's not going to be something you're going to be doing on, most likely on any cloud provider where you'd be running a confederation. So let me go, bear with me. Let me get all set up to share screens over here, create a confederation in real time on a drawing board. I'm not like the most coordinated over here, so it just takes me a few minutes to get it set up. Okay, so here we've created a whiteboard. So in BGP, we have this nasty formula of n times n minus 1 divided by 2. So if you're a big internet service provider and you have 10,000 routers spread throughout the world, which you probably have more than that, and a lot of the networks I've worked on have 10,000 plus routers. So assuming you have 10,000 routers and you needed to exchange routes inside of your system, and I'll give you an example what this would be. Let's say your internet service provider over here is ISPA, and you happen to be ISPB, and this is when you would typically do something like this. And then you've got ISPC over here. Now, if you want to provide transit, meaning people are going to go through you, and this is the way the internet works, is internet providers provide transit for other ones in certain places or whatever. And what you have to do in order to make this happen is you have to take the routes from ISPA, send them to ISPB, and then ask ISP and ask them to export them to ISPC. Now, if all we had was one BGP router here and another BGP router here, and we didn't have to worry about the entire network, that'd be fine. But because we get into this n times n minus 1 divided by 2, I want you to consider this. Let's assume if this over here right now is 5,000 routers. And there's a reason I want you to see this. So it would be very common for ISPC to have 5,000 routers. And in order to carry these routes across their network, unless they use something like MPLS label switching or some other way to do it, they're going to have to fully mesh or use route reflectors or use confederation. So let's talk about what this is. So let's take this number 5,000 divided by 5 minus 5,000 minus 1 and divided by 2. So let's do this. We're going to do the math on 0 and then 0. So let me do this in the calculator, even though it's pretty easy math, and then I'll cut and paste the answers in. And actually, why don't you do the math too and pop your answers in the chat box? So using that formula, the n times n minus 1 divided by 2 if we have 5,000 routers inside of that environment, that's the amount of IBGP peering sessions we would need to use. Now, the key here is the way this just goes up in an almost exponential manner. So the concept behind the confederation is, what if I could chop this internet service provider into multiple mini internet service providers? So now let's take this ISP. We're going to chop it up and we're going to turn it into a confederation. Good job, Adrian. Great job, Ben. So in this particular environment, what you would see we would have is what we would take this ISP and we would chop it up into 4 little mini ISPs or 5 little mini ISPs. And now that we've chopped it down to 5 mini ISPs, now we only have 1250 on each one of these. So we've got 1250, and it's still going to be an obscene number. So I'm going to tell you what we'll also do here and how we're going to knock that down. But now we're getting into some fun, seriously fun network architecture. So what we would do here is that we would take that, and now the new formula that we're going to be calculating will be 1250 times 1249 divided by 2. So let's make sure we know this gets done in first. And you'll see that while it looks pretty bad, it's not going to be anywhere close to as bad as it was before. 1250 times 1249 equals divided by 2. So now instead of needing 12 million IBGP sessions, now I only need 780,000 IBGP sessions for this environment. So how did we make that better? So what we typically did then inside of this environment is, instead of fully meshing our IBGP peers, we would use route reflectors. So the route reflector would be a route that was allowed to take routes in and send them out. So if you're familiar with something like AWS Cloud Hub or AWS Transit Gateway or any of these other kind of things, they're basically they're basically serving this function. So what we would do here is we would have these devices connect to a route reflector, or 2 or 3 and 4, and that way we could knock it down to maybe 200 BGP peering sessions, or a couple hundred BGP peering sessions for each one. And then what we would do is we would run eBGP between these, and then we would advertise out to the world. So if this is our real AS 1, 2, 3, 4, 5, internally this might be 65312. This might be 65313, 65314, and then 65415. So what we're really doing is we're just finding new ways to get past this n times n minus 1 problem by either creating multiple smaller domains, and that's in a confederation. And then we get inside of our confederation, we typically have route reflectors and a few other things. So it's there. And then you may have noticed now things aren't as bad, because what we could truly do is we could have our service provider backbone. Let's say this is our backbone. And we could have an ingress router over here. And we can have an egress router that's leaving our system over here. But now what we can do is, and this kind of made a lot of these IP clouds a lot easier, is if we ran MPLS over here, what we could do is we could take the BGP message or the packet, but let's say it's a BGP message. We could basically tunnel that as if these two were directly connected. Because what would happen is all the IP packets, they would enter the network as an IP packet. They would hit here. They would have a label on them, a labeled IP packet. And then as the labeled IP packet was ready to leave, it would hit the egress router, which had BGP, and the label would be removed. And then the IP packet would leave the network. Now, they could have popped it on a router here versus a pop there here. They used to call it penultimate hop popping versus end popping. And there's architectural reasons, but it's all doing the same thing. It's all trying to get around this ridiculous, nasty IBGP peering. All right. I might have gotten a little too geeky on that one, but people asked about BGP, and BGP can be kind of fun. And we do have a BGP workshop that goes on for about 6 or 7 hours, but this is more internet service provider, more CCIE, CCDE network architect as opposed to cloud architecture. But it was fun with the question. Did I answer all of the questions here? What are my thoughts when talking about BGP route reflectors? They're like anything else. They're an architectural tool, and you use them when you need to kind of minimize the IBGP peering environment. You only have 3 things. You don't need a route reflector. You've got 300 things. Starting to find a need. Good question, though. All right, let's get back into the content. Thanks for bearing with me getting real deep and geeky and label distribution protocols and tag distribution protocols and MPLS tunneling and BGP. But it was fun. Let's get back to the content, Chris.
Now we're going to discuss private line connectivity to the Google Cloud, and we're going to be talking about Cloud Interconnect. And basically, that's an ability to provide dedicated access to the cloud provider. So there's going to be 2 options here. We're going to have what's called a dedicated interconnect, and I'm going to show you what that is. We're also going to have what's called a partner interconnect, and that's okay too. We'll talk about what that is. So with a dedicated interconnect, what we're typically dealing with is we're in our data center. Let's say we've got a data center, and then what we do is we have a router. We buy a wide area connection to a point of presence somewhere, which is where a whole bunch of internet service providers are there. And in this environment, we typically have our device. So this is a router. Now because this is custom, we own this, we're buying a link between our router. We're going to call this a customer edge router. Now, typically what you'll see is your cloud providers over here. And I want you to understand all elements about the way this is going to work. And let's say this is your VPC. What happens is you ultimately buy a wire between your router and your other router in this point of presence locations where you're connected. And typically speaking, what you'll see here is Google will have their device or their switch. This is typically going to be called a provider edge device because it's how you connect to the provider. And then what they're going to do is they're going to have a lot of high-speed networking that's going to be backhauled to the provider. So what you do is you buy a wire or a virtual wire and a dedicated interconnect between you and your router, the customer edge router, and the provider is already connected to that point of presence. And then what you need to get is what's called a cross connect, which you'll have to get authorized, which is basically the ability to run a wire from your router to the provider edge router. So now what happens is, a lot of this is transparent to you. What happens is your router will send your information to this point of presence. It'll then hit the provider's edge. It'll then be backhauled back to the provider, and the traffic will be put in your VPC. Now this is you owning all of it. You get 10 gigs, you get 10 gigs. This is a dedicated interconnect. A partner interconnect is similar, but kind of different. Let's take these environments. Let's steal this. So in here, we've got the designated setter and our router, and now we connect to a partner. And now the partner itself is connected to the cloud provider. And now what happens is you connect to this partner. The partner then routes your network to the VPC. And why would people do this? Typically they do this because here they're going to buy 10 gigs. Here they might be able to buy 2 gigs out of 10 gigs. And basically they buy a 10 gig link to the partner, and the partner rate limits them at say 2 gigs versus 10. If they need more capacity, they can pay more to get to 3 gigs. So that's basically a partner interconnect. Now, typically speaking, with the partner, you're going to pay more for each thing of network, because then they now have to provide the network and they'll charge you for it to run it. So this is going to be the cheapest if you use the maximum bandwidth. But if you don't need 10 gigs and maybe you only need 2, you might use a partner, because it might be cheaper to pay for 2 gigs here than it would be the 10 gigs here. So there are going to be your 2 options for private lines. So use that cloud interconnect when you need guaranteed performance between maybe your on-premise location. And if you think about it, having a dedicated line, a dedicated wire will make their performance so much better. So we're going to have low latency on this. We're going to have high availability, typically speaking, because unless these links go down. And typically speaking, you're going to get a second link if it matters. So we're going to have to think about that. And what do I mean by second link? And let's talk about what I mean by second link, because I want you to understand what I mean by this. So let's say we're dealing with a very high availability environment. So let's say this link that we bought over here was on AT&T. If we need guaranteed performance on the backup, guess what we also need? We might need a backup direct interconnect. Now, putting the backup interconnect on the same provider, no matter how good AT&T is, as the primary link doesn't make sense architecturally, and we almost never do that. Because, yes, if this link gets cut by a cable, then maybe the other link still works. If this router port goes down, then maybe the other link still works with the same service provider. But what happens if AT&T has a outage? Well, then we're down no matter how many links we have. So your network architects will basically typically use a second. So maybe this link is on AT&T and this link is on Verizon. And obviously, when the people make the links, they're going to have to check the underground cables where the data center are and make sure that both of these links aren't coming inside of the same place. So, for example, what if the AT&T and the Verizon link came into the same conduit inside the building? Well, that would be a problem, because if anybody cut the conduit, you'd lose both. So typically speaking, when the network architects, when they look into this, they're going to make sure that the AT&T link is, say, coming on this side of the building, and maybe the Verizon link would be coming on the opposite side of the building in case somebody dug into the ground. So this is what we have to think about when we design for availability. So let's talk about the speeds we can typically get. Realistically speaking, we're typically dealing with 1 gig, 10 gig, and 100 gig. But not everybody needs this kind of guaranteed bandwidth, but it's under our control and our domain. Now, realistically speaking, with a dedicated internet connect, the traffic is not encrypted by default because it's not traversing the public internet. Now, that doesn't mean you may not want to encrypt your traffic over the wire, but it means that it's not going to be encrypted by default, because in order to get access to this traffic, you typically have to dig up the cables underneath the building to put a sniffer on them. So they're relatively secure. So let's talk a little bit about the VLAN necessity and the interconnect attachments and why we're using VLANs when we realistically use direct interconnect. So let me map this out for you. And first thing I'll do is I'll show you what a VLAN is, and then I'll show you why the cloud providers are actually using the VLAN. So if we wanted to take a switch, let's say the switch had 48 ports in it. And by default, if a switch has 48 ports, and let's draw some switch ports, we'll draw a couple of them for fun. And if a switch has 48 ports, by default, they're in the same VLAN, which means all of them, every last one of these ports, can now talk to each other. So if we've got devices all plugged into the same switch, everyone can talk to each other. So this is one switch. So let's say we have 2 switches. It'll help in a minute. So let's say we have 2 switches. And now let's say we decided to say these 10 ports on this switch, just these 10 ports, can talk to each other. And we decided to name this one, and they're all finance users. So this is the finance VLAN. And let's say that we decided the next set of users over here, these ports over here, which is a lot of ports. Now, maybe this is the sales VLAN. And the sales VLAN can only see sales stuff, but they can't actually see finance stuff. So we'll call this the sales VLAN. Now, right now, sales will only ever be able to talk to sales. The sales VLAN cannot talk to the finance VLAN unless they're connected with a router. And while we're at it, let's add one more VLAN. Let's call this VLAN the dev test VLAN. Doesn't matter what we call it. The point is they're isolated. So these are our three VLANs. So finance is officially segregated from sales and dev test. They can't talk to each other. Now, at the same time, let's say, for example, we had another switch that was going to connect to each other, that we needed to switch these. And it'll make sense in a minute why, oops, no, I didn't want to do that. And it'll make sense in a second why I actually am doing what I'm doing. Oops, not working here. So let's say that if we have the same finance VLAN on the other switch, the same sales VLAN on the other switch, and we have the same dev test with the systems on the other switch. Now, I want you to understand that right now, nobody outside of each switch could talk to each other. So let's say we wanted the finance VLAN switch to talk to this finance VLAN on another switch. We have an option, run a cable from finance to finance. Now, let's say we have the sales VLAN on both switches. We can run a cable from a sales port to a sales port, and then the salespeople can speak to each other for both switches. And we could do the same thing for dev test. Note, that's 3 cables. This works perfectly, by the way, and you could do this. But what if we wanted something slightly different? And I'll show you what I mean. What if we wanted, or we had only one single wire, like a single direct connection to the cloud provider, and we wanted to be able to reach multiple things securely? Well, we also have this concept of a VLAN tag, or an 802.1q VLAN tag. So here's how this works. Let's say we have a single piece of fiber between this. What happens when we take a frame, when the frame's going to leave the finance VLAN? So let's say we've got an Ethernet frame. What else will we have on an Ethernet environment or an Ethernet switch other than an Ethernet frame? What will happen is this. So right now, if we have a wire between them, the Ethernet frame is just sent between these two wires. But what if now we want to separate the traffic from finance and sales, but they still want to use this? So what we'll do is we'll have this Ethernet frame. And what we're going to do is we're going to smack a tag on this. And it's going to be called an 802.1q tag, generally speaking. And I'll call it that. And it'll say finance VLAN. So what happens is as this Ethernet frame leaves the environment, what's going to happen, it's going to have this finance VLAN tag. This is going to be this 802.1q tag. It will be added. And once that frame reaches the next switch, what will happen is the VLAN frame will be stripped off and the Ethernet frame will be sent to the right VLAN. And if the sales wants to send a packet, it'll be a sales packet. It'll slap the 802.1q tag for sales. And by doing this again, I'll do it one more time. We have an Ethernet frame. As the Ethernet frame leaves the switch, as it's going to leave that switch and hit this wire, it's going to be given a tag, an 802.1q tag that identifies the VLAN. It's going to reach that far end switch. The frame will be sent to the right VLAN, and the tag will be stripped off. And that way, I can securely send finance data on this wire. I can send sales data on this wire, and I can send dev test information on this wire. So let's think of another alternative environment. This could be a single VPC that you have. And this could be an additional VPC, and you connect it to the cloud provider. So you've got your data center. Then you ultimately connect it to the cloud provider's network. And then they've created a virtual private wire for you across your VPCs. And they kept your traffic segregated or moved it because they looked at your VLAN tag. So why does it matter? Well, if we go back to this environment here, you've got your data and many other customers' data that you can see is being backhauled to the cloud provider over this private wire. So the VLAN tag can keep everybody's traffic separated on this end wire. So keep that in the back of your mind when we talk about tags when we're actually dealing with this. Now, I talked about a cross connect before, and a cross connect is the ability to go from your device to the provider's device. It's just a cable. It's called a cross connect. And basically that's just a wire or either a copper wire or a fiber optic cable that connects your device to the provider's device. And I talked about why we would use VLAN attachments on, realistically speaking, when we connect to cloud providers. So remember, the dedicated internet is a wide area network that gives you private access to the cloud and makes it feel as if they're on site, especially if you've got a fast private line connection. It's not going to the public internet, so we don't have to worry about what kind of IP addresses we're using. We don't have to worry about the security, and we're not doing egress from the network, at least going out the internet. So if there's egress costs, and these things change all the time, you won't be paying them. So private Google access. Now, I talked about the partners, and I talked about why they're fairly cost efficient if you don't need to use the full link. There's typically a wide number of partners across your geographies, but instead of connecting directly to Google, you connect to somebody else and then they connect back to the Google network. So that's really all we're talking about with regards over here. Now let's talk about cloud load balancing. So Google Cloud obviously owns its infrastructure and it can provide load balancing. And we talked about lots of types of load balancing, network load balancers and application load balancers, but understand Google provides load balancing services. And, Google's been around for a while, so they've got a lot of experience building private data centers, high availability environments. They've got a lot of ability and knowledge with security. They've got a lot of knowledge with networking. So they're there. So they have a global load balancing service, and that's going to be a fully distributed, high performance, software defined managed service. And that's going to distribute load dynamically across your infrastructure to enhance your performance and availability. Now, with regards to Google Cloud Load Balancing, it uses a single Anycast IP. And that means it's going to front end a single IP address to wherever it's going. And that means you're going to have that multi-region failover. And I showed you how Anycast IP works earlier. Now, when it comes to load balancer types on the cloud, we have a global load balancer, which is going to distribute your traffic across multiple regions. That's going to be a global load balancer. And we also have HTTPS load balancing, which is going to be optimized for web traffic. We typically have network load balancers, application load balancers. We have, in this case, HTTPS load balancing that's going to be optimized for web traffic with content-based routing. We have TLS, LSLL-based routing, which is going to support applications that rely on TCP or SSL, and that will offer enhanced performance. We can do UDP load balancing, which is how we can efficiently handle a lot of UDP traffic, like real-time traffic, non-reliable traffic. We can do something called secure sockets proxy and HTTPS load balancing. And the key here is the load balancers can terminate the SSL traffic. Now, why does this matter? Encryption is heavily expensive computationally. So when we're dealing with this type of SSL-based proxying, it enables the load balancers to offload the servers, which means the servers can scale better. And we can also do what's called internal load balancing, which is load balancing across our internal systems. So we might want to use cloud load balancing. Let's say we've got a website that supports millions of global users. Cloud load balancing can distribute it evenly all over the backend VPNs. It can prevent server overload by ensuring that the traffic is going to be spread wherever we need it based upon servers' capacity and health. And this is going to give us very high performance. So we have plenty of load balancer and load balancing types that we can typically use. And I'm going to show you a graphic which we actually created that I think will help summarize this for you. Okay, so let's talk about these load balancers one more time. Have a graphic here. Had a graphic here that I think would help you a little bit. So let's talk about an internal load balancer. And realistically speaking, this is going to be to load balance our stuff internally. We could do internal HTTPS, which is going to be based upon, let's say we had a HTTPS front end browser accessible application we were using internally. We talked about SSL proxy, which is basically terminating the SSL connections for you. And of course, this external HTTP, HTTPS kind of thing is for external facing websites. So external load balancers, we have to think about load balancing for external traffic. And when you typically think of a TCP, UDP external load balancing, you're typically thinking about load balancing some type of traffic. Now, if we're talking about TCP load balancing, external load balancers, TCP, UDP, we're looking at networking information. So very good for low latency load balancing across environments that we might need to do. So what does this really look like? Well, it looks like this. External load balancing is for internet facing things. So if this is the internet, and realistically speaking, these are our web servers. So here's our load balancer. Now here's going to be our web servers. Bear with me. We're going to be load balancing the web servers that would be seen by the internet. And that's why it's an external load balancer. It's an external load balancer because it's load balancing things that are actually connected to the internet. So we need low latency, we need good performance, and we need to do it externally. It's an external load balancer. Now, an internal load balancer is going to be a little bit different. The internal load balancer will load balance between our stuff internally. So what does this mean? It means in our, let's say this is a whole entire environment is our VPC. Let's fill this up. Let's get rid of the fill. Let's call this our VPC. What if we had an application that was internal for a whole bunch of users? So let's just call this as an HR app. So let's say we have a internal load balancer here. And then that's load balancing services for the HR app. And these are our load balancer virtual machines. And then this is going to load balance between internal servers. So this is an internal load balancer. And imagine here's your user and here's your data center. It's connected. It's connected to the cloud provider, right? Through a router of some kind. Let's say your direct connection. And now users in the data center or users in the building that's connected to the data center can now access the HR servers, and they are load balanced to increase their performance and remove single points of failure. Now, I already talked about the way load balancers work and the way they run health checks to determine if a server is not going to be there. So we've talked about that previously. And that's one of the ways that load balancers do a great job of enhancing availability. Now, we have to understand that if we have any firewalls in place, the load balancer is going to have to be able to do a health check. And if we block the health check with some type of a firewall rule, the server would be removed from the rotation. So we need to make sure we have the right firewall rules. Otherwise, we're going to get these HTTP 502 and 503 errors, timeouts, and other issues. So make sure that we're permitting the health checks. Because if an instance or a virtual machine is not going to pass a health check, it's going to be considered unhealthy and we'll have problems. Now, I previously talked about content delivery networks. Google has their own content delivery network. It's called Cloud CDN that provides fast, reliable content delivery network services, and therefore it improves their performance. Google has a global scale and a global reach that uses the Google's global infrastructure. They're paired with, for the most part, with every major internet service provider worldwide, and they needed to be because of their Google business. And of course, they leverage Anycast architecture to make sure that the IP addresses are going to be consistent and there and alive and use the best performance. And of course, the content delivery network will provide caching services that will reduce latency, increase the scalability of the systems, and potentially help with DDoS attacks. Now, we can integrate Cloud CDN with other cloud content delivery providers like Cloudflare and Akamai, and that's going to give an organization many flexibility services. For example, Akamai, they have a lot more points of presence, and it does a lot more points of presence than the Google one. So you can choose what you need and where you want to actually connect, which is a great service that they provide this. Now, whenever we think of networking, we need to make sure that the network somehow enhances the confidentiality of the information in our systems. It keeps our data accurate and unchanged. Encryption can help us with the first two. And that our network is available when necessary, which means we're going to make sure we need as many links and connections and redundancies as possible. If we don't have redundancies on the network, everything will fall apart, and it will fall apart badly. So when we deal with networking, we're typically looking for any kind of way that we determine who the users are before they access to the system. Authentication. Authorized, meaning they're allowed to use the system before they even get on there, which means we may need network admission controls, locking up these network devices, blocking the ports that could even plug to the network at our side anyway, so that only the right devices are allowed to plug in. Defense in depth. Obviously, we can use access control as firewalls and a whole bunch of things simultaneously, and we should be. And no matter what, we should always adhere to the principle of least privilege. So we have to think about everything we do that we can. And in many cases, when we're dealing with networking, we're dealing with security as well, specifically in the area of network security. So many people think of the old school, and I still do to a degree. That's that castle and moat architecture that we typically talk about, that we traditionally have, because that's the traditional environment where we've got good, hard external boundaries. And you'll recall I drew that out previously, where we had these good, firm boundaries, and you knew exactly where your traffic was coming from, and we built a castle and we secured it. So realistically speaking, that's traditional security. And it's this, we talked about it, it's this castle where we protected the environment with walls, and maybe we put warriors on top and a defense in depth in case somebody could climb the walls, the warriors could keep it. And you recall then we defended the castle with water that was filled with sharks and alligators. And then behind that, we had some behind the gate, we had some security people that were there. So this is the traditional model. But here's the traditional model. We own it. Now in cloud computing, we don't own everything. And we can't provide anywhere near this level of security, which is going to be why we're migrating towards zero trust and other fundamental elements that we actually can do on the network. So if we don't have this castle and moat like we used to, now we're going to have something else. And that brings us more towards zero trust. But the key to remember that they want you to know is the shared security model. And this is very easy to understand. You are responsible for the security of your stuff, and Google's responsible for the security of their stuff. So if you're using infrastructure as a service, you're responsible for your virtual machines, your containers, the operating systems on your virtual machines, for example, your routing security, your network security, all of it. For the most part, that's you. Now, what is the cloud provider responsible for with that infrastructure as a service? Their stuff, the underlying server, the underlying network, the stuff that they manage for you. You'll recall platform as a service are things like AWS Elastic Beanstalk or App Engine, where you just upload your code and it goes. And software as a service, think Google Office, Microsoft 365. And think about the control element. If you're just uploading your code, then you're responsible for your code and the IAM strategies to your code for the most part. And in a platform as a service, the cloud provider manages, for the most part, everything. The infrastructure, the operating systems, and all you have to do is manage your code. Now, in a software as a service environment, the provider provides everything. They even store your data for you, but the only thing you control is your IAM, who's allowed to access the system under permission. So we have to think about it consistently. Now, network security gives us a lot of options. Now, network security is not enough for security of the entire system. We'll need application security. We'll need physical security. We'll need so much more, but there's a lot of importance on network security. And we should use these options when we have. And networking gives us lots of options. I showed you how if you didn't have a route to it, you couldn't reach it. So whenever we design anything, we need to think of what it's going to look like long term. What's the network going to need to support it? What's it going to expand to? What kind of services? What kind of bandwidth? What kind of latency? At the same time, networking gives us the ability to segment or microsegment. Maybe we break our environment into multiple VPCs. In each VPC, we have various subnets that are protected off or firewalled off from each other if we wanted to. And we still have our IAM. So it's going to be this layered approach. Real world projects are going to have some extreme requirements. And they're going to have some engineering challenges that may make it that you have to do workarounds that get past best practices. So you're going to have to be able to understand how to secure it. And that's way beyond the scope of a Google Professional Cloud Architect exam, way beyond the scope of a Security Plus, designing a security architecture is substantial. But we're going to talk about what we can here. We have a security architect program for people that are really interested in designing cloud security architectures and security architectures. And if you're interested in a little more knowledge, not enough to be an architect, but enough knowledge to learn a lot more about cybersecurity, we have a completely free CCSP, CISM, and soon a CCSK certification on our YouTube channel. 2 out of the 3 are actually cloud security certifications, and one of them is more the business level. So they're great certifications you can check out to enhance your security knowledge that goes way beyond what's here. But whenever it comes to security, we get into this concept of the CIA triad, which means we need to protect the confidentiality of this data and protect unauthorized access to that data. We need to ensure the integrity of the system. Everything is what it's supposed to be. The data hasn't been changed. The system hasn't been changed. And we need to ensure the availability of the system. And let's face it, if a system is hacked, it might not be available. So the CIA triad you'll typically hear a lot about. No, we need to prevent as many outages, as many security events as we can, and it's going to take a holistic environment to do it. That's going to encompass everything from application security to IAM to network security. There's just so much that's going to go into it. But there's a lot we can do on the network. We can detect potentially DDoS attacks and often thwart them with our content delivery networks and our IDS, IPS systems and our firewalls, for example. And we can look for weaknesses in our systems. So the key is we're going to have to be here. But we're going to have to prevent incidents. And of course, the security architects will have to design incident response procedures, what have you. When it comes to network security principles, we want to collaborate across teams because we need to know what needs to talk to what. If we don't know what needs to talk to what, then we have to allow everything to talk to everything. And that's nowhere close to a secure environment. We typically want to make sure we use some kind of efficiency to make sure we don't have any weaknesses in the system. And that's easiest done by infrastructure as code. Imagine having 100 cloud admins all doing their own thing. To think of a number of mistakes that could be made. Now think of infrastructure as code. One person, one expert, what's a perfect configuration scope. None of the mistakes that the 100 admins could have made would have been done. And it's done quickly, efficiently, enabling one person to replace the work of maybe 30, 40, 50 people and add accuracy and consistency and hire one expert that's great as opposed to a whole lot of people that you have to be concerned about. So the key is I always want more people and I want better people, but the infrastructure as a code avoids those little mistakes which enables businesses to focus on bigger issues, hire people with strong skills, and innovate faster without worrying about all this, bringing things up and down and changing them and changing them. Now, Google Cloud gives you somewhat sophisticated, as sophisticated as any other provider's security tools. And of course, you can use other tools that'll give you much more capability. So let's talk about the Google front end. And that's what you call a very smart reverse proxy system. It operates at the control plane level, the global level, and it is interconnected through Google's network. It provides user authentication, and it can provide security, and it is a reverse proxy. Now, if you're not familiar with reverse proxies, we'll talk about what they do. They basically provide load balancing services, and they typically actually cache at the same time. So typically speaking, reverse proxies, that's what they're doing. Now, Google front end is a reverse proxy. They can help with distributed denial of service attacks. It's going to be managed by the Google load balancer, and it acts as a traffic cop in many cases, and it can route user traffic directly and securely to right back-end services. So Google front end is a reverse proxy. What is a reverse proxy? And generally speaking, I will draw it out for you because they're so much like a load balancer, but I want to make sure you completely understand what we're actually talking about. So let's draw it out. So let's talk about reverse proxy services, and Google front end is Google's reverse proxy. Now, here's what a reverse proxy normally does. So a reverse proxy should look a whole lot like a load balancer to you. And the reason it's going to look a whole lot like a load balancer to you is it is. So typically speaking with a reverse proxy, so let's say this is a server. Typically what happens is we have, let's say, a request or something that's destined for a server. The reverse proxy will send it to this server, or this server, just like a load balancer. Now, many reverse proxies also cache. So let's say in this particular case, like an F5 reverse proxy would be doing caching. So something hits the reverse proxy, it goes to the server the first time, and the response responded. Now, the next time somebody hits the reverse proxy, they request the same thing that was requested the first time the reverse proxy answers. Now, the next time somebody requests something, it's not on the reverse proxy, it's sent to the next server. So that's typically what a reverse proxy is. It's a load balancer. Now, that's opposite of a forward proxy. And if you want to see what a forward proxy is, I'll go through it here before I get to anything else. A forward proxy is used, typically speaking, in today's world when you need to deeply control traffic. So let's say this is the internet. And let's say you had a forward proxy going out to the internet. We'll call it a forward proxy. What you do is you point your internal users. Oops, bear with me. You got a bunch of users, so let's take some users. And when the users want to go to the internet, what they do is they connect to the reverse proxy, or the forward proxy here. The forward proxy goes to the internet responds to the forward proxy, and then the forward proxy delivers it back to the server. The next user wants to go to the internet, they connect to the forward proxy. The forward proxy, if it doesn't have it, goes to the internet. It returns it to the forward proxy, and then the forward proxy sends that information to the user. Now, this user wants to access something, but the previous two users just accessed it. So they hit the forward proxy cached it, and it sends the packet back immediately. So reverse proxies are like load balancers. Forward proxies are designed to control internet traffic. And why would you do this? Let's say you didn't want your user shopping. So you'd send your data to the forward proxy. The forward proxy would say that website's blocked for you. You can't go. So typically done for that to block illicit content or other things. Organizations use forward proxies. But reverse proxies are what we were talking about. I just wanted to see if you wanted to know what a forward proxy is. So that Google front end can help provide some DDoS protection like all load balancers typically would do, like all load balancers, so they distribute the load. And imagine your servers are now auto-scaling. You've got an overwhelming amount of traffic, and they can also scale out on demand.
Okay, we are back. So I know we got a little into networking here, but I like networking. Hopefully you think networking's cool. Let me know. Give me a hashtag Google Professional Cloud Architect so I know you're still awake. Some people tell me they don't love networking. I've also heard people say they don't love cats or people don't love dogs. I love all furry things and I love networking. So who knows? So in any case, if you've got some questions, bring it in and let us see what they actually are. Then we've got one more lecture. And after that, we're going to have a video on, we're going to have a nice lab on networking. So let's see if anybody brought in any questions. Like in a cloud computing world, can I briefly explain by design the VPC for both infrastructure as a service and software as a service? So let's separate the two of these out because they're completely different things. Your VPC is your virtual private data center. So in your virtual private data center, you will put your stuff like your virtual machines. Now, all of that is infrastructure as a service. Your load, so there's that. Now, by comparison, there's software as a service, which is something that's going to be completely different. Software as a service is basically another company that provides access to live software, meaning typically speaking, they host the underlying network, they host the underlying compute, they host the underlying storage, they host the applications, and they even host your data. And the only thing you have any control over is using it and your usernames and passwords that you actually use with this system. So they don't have a lot to do with each other. So here's the way an organization would use a SaaS provider. So let's say you've got your VPC or your VNet on Azure, and that's where your private systems are. The software as a service provider is completely outside of your organization. So there are going to be a couple ways you can connect to it. The least efficient way, which I probably don't recommend, but you could do it, is what you could do is you could connect to some form of an internet gateway in your cloud provider, and then you could put a virtual machine there, and then you could create a tunnel and use that virtual machine to connect to the endpoint that's posted on the public internet. So that would mean leaving your VPC, going out to the internet, and then to the SaaS provider outside the internet, and then coming back. Now that's one way people do it. Now, another way, which makes a whole lot more sense, is maybe the SaaS provider is already on your cloud provider. So let's walk through that architecturally. I think I can help you understand what that's going to look at, and then I can show you the alternative options that those of us might typically do. Let me build a slide over here real quick. So typically what you'll do now, where's my little, too much software on my computer. For one person to try to manage to do this stuff sometimes. So let's just say we've got this. Okay, so here we've got your VNet, your VPC. And let's say your VPC is on Google. And at the same time, the SaaS provider you want to host to is also hosted on Google, but they're hosted in their own organization. Typically, they'll offer you an endpoint that you can connect to. And then what you would get is like a private link, like a virtual wire across your cloud provider, where you're basically using the network in a private encrypting connection between your VPC and the SaaS provider. This is a virtual private link that you're getting. It's running on the cloud provider's native systems, not the internet. So you're not going to the internet to connect. It's much more secure and it's much more performant. Now, the other thing that you can do, and you'll see this will happen a lot of times, is you could have your VPC, and your VPC can have some kind of like a direct connect gateway, transit gateway, whatever you're dealing with. And what'll happen is you will have there are private lines between, say, the SaaS provider. So this would be the SaaS provider that you might see here, and this could be this is a I'm going to call it a gateway. It's a gateway that'll go from a direct private connection from the gateway, and you can get a private connection that would then go to your VPC. So basically, you can buy a private line or a wire that's going to connect to the one of the virtual routers at your cloud provider that'll then connect into your VPC. The other way these architectures could work is you can actually have your users here, and this is very common. You've got your users and your users in a campus. Maybe there's a 5,000 users in the campus. Now the campus has a private line, or basically a wire between you and the cloud provider. And then in this particular case, the SaaS provider is actually sitting on the internet. So let's say the SaaS provider is Microsoft. Maybe you're using it for Microsoft 365, like Office type applications. And maybe you go out your user campus where your users are through your firewall out to the internet. And then you're through the internet, you're reaching the SaaS provider. And you could do this over here. And by doing so, this is going to cost a whole lot less than trying to do it from the cloud. And it's going to give your users, typically speaking, better performance. Now, there are other things we can do. We can sometimes put like a cloud access security broker along the way. And what we can do if we have a lot of SaaS providers and things is we can actually route the traffic in an encrypted manner. We can leave our campus. We could go to this cloud access security broker, connect here via proxy-like manner, and then the cloud access security broker will regulate policies and prevent like data loss and data prevention from the various SaaS providers. So we can also architect it that way. They're your primary architectures for working around these kinds of scenarios, integrating cloud into software as a service. So they're your typical architectural options that are there. Bear with me while I find the right window that I can actually talk to you from, that you could typically use to connect to a SaaS provider. I hope that helped. Any other questions come in, or maybe we did a good job and explained networking so well that no one had questions. Adrian, Google Professional Cloud Architect, I love it. Jacques, Google Professional Cloud Architect, thank you. Ben Kim, I see your way. Google Professional Cloud Architect, thanks so much. Yeah, boy, P, Professional Cloud Architect, love it, love it, love it. So wonderful. We're going to have one more video. After that video, we're going to get involved in a really cool lab. Leo had some fun with it for you. So I always like watching these things because I'm an architect, and as architects, we never build anything. We just design things and things. So it is kind of cool. If you just got here, as a reminder, there's a free e-guide that goes through this that you can subscribe to. And that free e-guide will basically I'm sorry, it's not an e-guide. It's a study guide that's designed to help you pass this exam. There's about 550 pages of content my team created out of our notes, and it's designed to help you win and pass on your Google Professional Cloud Architect exam, because we want you to get that certification if it's on your certification plan. So hope that helps. If you're having a good time, maybe give it a like, maybe subscribe to our channel and hit the bell to be notified of other videos to help you in your career. And please spread the word. Help us share this with others that you know will benefit from this. Okay, Chris, let's get back to the content.
While we're discussing networking and security, we'll talk a little more about firewalls. I know we talked a lot about networking and a lot about security, but nothing works without the network, and the network has the ability to do a lot of security. So now we're going to get involved in a couple of different kinds of firewalls. So we talked about how firewalls work. And now I'm going to talk about how layer 7 firewalls work and next generation firewalls work, as opposed to just traditional firewalls. So next generation firewalls have included intrusion detection and intrusion prevention services, and that can greatly enhance security. And the best firewalls now are adapted. They're using artificial intelligence to enhance the security. So I can draw out what that means so you understand. So all firewalls do this for the most part. Any modern firewall made within, say, the last 20 years or so. And they're all stateful. So let's say this is the firewall. And let's say this is the internet. And let's say this is our internal environment. This is our LAN, for example, our campus. What normally happens when a user goes out to the internet, let's say we have a user, and let's say the user is Cindy the cat. She wants to go to the web. The user is Cindy. She's on the LAN, and here's the website which Cindy wants to go to. And this is Cindy's Best Tuna and Shrimp.com. I hope this is not a real name. But let's make sure it's not Cindy the cat's best tuna and shrimp.com. I'm pretty sure this is not a website that anybody would actually choose, especially with cats misspelled wrong. So let's say Cindy wants to go access the website. She gets my credit card. She takes her paws, walks on my computer. She goes out to the internet. Her private IP address is translated into a public address via something called port address translation on the firewall. Her traffic goes to the internet. Cindy, the website responds to the internet. The firewall accepts it and says, oh, that's returning the data to Cindy because I saw it when it was sent out, and sends it back. Now, at the same time, the way all firewalls work is we've got a hacker over here, and the hacker wants to talk to Cindy. The hacker hits the firewall, and it's dropped. Life's good. So this is a normal firewall environment. Now, a next generation firewall is a little different. It does all of this, but instead of at the packet level looking at things like TCP, UDP, protocol, port number, what have you, the next generation firewall, if it wants, can look all the way up to layer 7. So it's already got more intelligence. It can do what's called deep packet inspection and really see what's going on. But the other reason we typically use commercial firewalls is the included IDS IPS. So now we've got a couple of things. So let's say the normal firewalls still function, but now all of a sudden, there's a bunch of hackers that decide they're going to start trying to hack us. And a bunch of hackers decide to start hacking us. And while they might have been able to overwhelm then they went through the internet, it hit the firewall IDS IPS system. And for some reason, their traffic was allowed through the firewall initially because of policy that said so. But now this firewall is saying, these users, they're behaving in what looks like a hacker manner. Let me just build an ACL and block them and just deny all these folks access or reset their TCP connections or do something. So a next generation firewall gives us this intrusion detection, intrusion prevention. It can thwart an attack, and many use AI to do this. So anytime we have firewalls, one of the risks is that they're misconfigured. So anybody can make a mistake, especially someone that doesn't understand networking or security, which is usually the problem. It's usually not the typo. It's usually the person didn't know what they were configuring or why they were configuring it. They did 1,000,001 hands-on labs and they know how to configure, but they don't know what or why. And that's the biggest challenge we often have. So keep that in the back of your mind. So it gets hard to do this. Anytime we can automate firewall configurations, we should be using it. Now, we have to know what we're doing before we automate, because if we don't know what we're doing, we're going to automate and break things. But keep that in the back of your mind. It becomes hard to manage a lot of firewall rules. So realistically speaking, we need to think about how do we manage them? How do we automate the management of them? Now, if we can use automation with infrastructure as code, like using Terraform to manage firewall rules firewalls across all 3 clouds, this is great. So somebody can make a request to do something, and we can deploy it rapidly and easily. Now, this way, we've got central governance. The central governance can check in the impact of each chain, and then it can be done instantly or easily whenever the time is deemed right with automation. Now, when it comes to firewalls, we typically have 2 kinds of firewalls. We have those next generation firewalls that we talk about, which is what you would use in a modern world. And we have web application firewalls. As a rule, the next generation firewalls protect your entire organization. So they'll protect you against all kinds of threats, and they're very good at it. We may have something called a web application firewall that is specifically tuned towards web applications. And they look at web applications potentially in certain circumstances better than a traditional next generation firewall. Now, what does this mean? It means that a web application firewall by itself is usually not going to be enough for security because it doesn't provide all those other security protections. But we could have a next generation firewall followed by a web application firewall and get the best of both worlds. Now, these web application firewalls are often more complex to manage, but they're also going to be part of our web solution. So that brings us to Google Cloud Armor, which is the Google's WAF solution. And it's going to protect against common website attacks like cross-site forgery, cross-site scripting, SQL injection. It's like an AWS WAF or an Azure version. Now, trying to manage 3 different WAFs across 3 different cloud providers usually doesn't make sense. So we might use a standard WAF provider, but this is the Google WAF solution, and it's quite a good WAF solution. So that's one option we have. Now, we also have the VPC firewall rules. Unrealistically speaking, these allow or deny connections to a virtual machine based upon a configuration. So rules will be enforced at the network level, not the instance level. So I hope that makes sense. Now, we can also have a distributed firewall architecture where every VPC functions as a distributed firewall, and rules are set at the VPC network level, and we apply it on a per instance basis. Then we can have firewall rules that can control traffic between instances and other networks, or between instances and the same networks. Now, when we talk about the VPC firewall rules, we have to talk about the characteristics of those rules. They can either be applied ingress or egress, but not both, because they're stateful. They keep track of what's going on. You only need to apply it in one direction. So they're monitoring the traffic. Now, when it comes to a firewall rule, basically speaking, you can either permit something or you deny it. That's it. So what will happen with VPC firewall rules, each firewall rule will be associated with a specific VPC. And the rules are not going to be shared across VPCs. They're going to be separate and defined for each VPC. Each VPC is going to have its own VPC firewall rule. So they're going to determine what traffic can hit a network, which can then determine what traffic can hit your virtual machines. So keep this in the back of your mind. And if you're dealing with a shared VPC, then the firewall rules will be centralized and managed by the host project. But they're going to be very similar to traditional firewalls rule, allow, deny, what have you. So when we get to our firewalls, the rules will be configured. They'll be given a number, range 0 to 6,500. The rules are processed with the lower number being the highest priority. So we can create a rule that targets everything in a VPC, for example, or just an instance or an instances by a service account. We can match protocol and port when creating a rule. So that means TCP is a protocol port 443, like SSL or port 20 or 21 or whatever ports you've decided you need to allow open. So we always have this implicit rule at the end of a firewall that is deny. So what does this really mean? Generally speaking, you tell it what you want to be allowed and everything else is going to be denied. So I hope that kind of helps. So ingress by a firewall is typically going to be blocked unless you tell it otherwise. And egress, allows your traffic going out. And it's typically the way a firewall works is all your internal traffic is always allowed to go out and then come back, but no internal traffic is allowed in. So if you want any traffic in, you have to explicitly permit it. And we have the concept of a hierarchical firewall policy, where policies can be defined at an organization level or at an individual folder level. And that by doing so, it enables us good centralized management of firewall policies. And this will help us building consistent and granular firewall policies. And we want to do this because we want to know exactly what we need, apply it in the right way, and be as restrictive as we can with the firewall, only allowing what we need in. Try to not open up more than you need, and definitely make sure that you didn't accidentally open up something. So if we talk about Cloud Armor, it is a managed web application firewall that's going to be integrated with HTTPS load balancers. So it's going to protect applications that are going to be exposed to the world through an external IP. It's going to give us level 7 application layer security and enhanced layer 3 for 4 DDoS protection because it's designed for that. It's a web application firewall that's specific for web applications. We can also integrate it with other load balancers like HTTPS load balancers to provide WAF capabilities directly to the load balancers. So it's going to enhance our security beyond the normal type of protection we would typically get from DDoS mitigation that we get from load balancers, Cloud Armor. And it comes with pre-configured rules that are going to protect against common web vulnerabilities like cross-site scripting attacks, SQL injection attacks, local and remote file inclusion, and remote code exclusion. It's based upon the OWASP mod security core rule set. And of course, we can create custom rules. And the custom rules with Cloud Armor are going to be created using something called custom expression language or CEL format for security needs. Now, we can use Cloud Armor to enforce policy. It will enforce the policy that's necessary for what's allowed in and what's not out. And these policies can be accessed when external traffic reaches the Google front end during any kind of process. So the Cloud Armor is going to look at it. Is it allowed before it hits the proxy, which would then go to the servers? We have the ability to provide access control and traffic filtering. So we could say, block this country by looking at a geographic region-based IP address ranges. We can look at the rules ahead of time with a rule preview from a management perspective. We've got the ability to look at the effect of a rule before we put it, which is really great to protect against unintended consequences. We can log the activities that are going to be associated with the load balancer, so we see what's working. And we're going to need these logs to be critical for security monitoring. And typically, we're going to send all of our logs to a SIEM system somewhere that's going to be able to correlate these logs and analyze these logs. Now, we need something called NAT, and NAT translates one address to another address. And Google provides a NAT service, Network Address Translation. And that's a managed service that allows virtual machines and Kubernetes clusters, etc., to connect to the internet without actually needing an IP address. So you may actually hear AWS, for example, has the equivalent of this called an internet gateway. And what it does is it translates external. Now, with regards to a NAT, in inbound connectivity, typically speaking, it's not designed for inbound communication. And it's only going to be permitted as a response to an outbound request. So what on earth does this mean? Let me kind of draw this out for you. What it really means when we're dealing with CloudNet is the follows. CloudNet is going to take all of our private addresses. Let's say these are our private subnets. It's going to enable them to, let's say what we'll call a CloudNet. It's going to do the netting. And that's going to enable them to go to the internet and their traffic come back. Now let's talk about why you might need this. So let's say, here's the environment that we actually have. We've got CloudNet. Now, all our users are going to be in private subnets like they're supposed to be using these RFC 1918 address spaces. Remember, that's the 10.0.0.0/8. It's the 172.16.0.0/12, and that's going to be the 192.168.0.0/16. These are those private addresses specified in the Internet Engineering Task Force RFC 1918. So that means these systems can go to the internet and their traffic's allowed back. But nothing from the internet can come in. Why might we need this? Why might we want this? What if these are all our internal systems in our VPC, and we want to be able to patch the systems by going out to the internet and get the patch and then come back? So a CloudNet would enable us to go out to the internet and come back. And we might do this for servers, so they can update their operating system, patch them, what have you, but still not be reachable from the internet. It's the equivalent of an AWS NAT gateway. So that gives us the ability to connect to the internet and the security of coming back. Interestingly, firewalls are typically used to do this for the same reason. Our traffic can go out, our systems can be reachable, but our systems are still not reachable from the internet. Now let's talk about something called a VPC service control. And VPC service controls help secure access to the Google Cloud's managed services. So maybe BigQuery, Google Cloud Storage that are hosted in your VPC. So they mitigate data exfiltration risks, and they ensure that data remains private inside your perimeter. So one of the things we need to worry about is data leaving our organization. But the VPC security controls enable access to these managed services inside of the Google network. So it's outside your VPC, but we're reaching it through the Google network, not the internet. And we're going to provide security here, which gives us the ability to create a security perimeter. And VPC security controls allow security administrators to define a somewhat of a security perimeter around these managed services. The perimeter restricts access to these services and from these services, making sure that the only data that can be accessed is inside of our established boundaries. So protects against data loss prevention. So it provides data protection. So if we've got that service perimeter, we know it's not leaving our actual enforced boundaries. So this prevents complications like a compromised user or a malicious user taking data outside of our VPC or taking data outside of a Google service like BigQuery or Google Cloud Service. So it's protecting our environments. So it's keeping us safe. So we want to implement VPC service controls, even though it can get fairly complex, because anytime we start determining who could talk to whom, we need a lot of knowledge of what needs to talk to what, and that means careful, serious planning. And it's going to be necessary to be patient and very deliberate in defining any kind of use case and any kind of controls to meet the security needs of the organization. So the security architects are going to have their work cut out for them, and as well as the cloud security architects. Now, the point here with these service controls is we want to secure our environment, protect sensitive data, and keep it from being exposed to the outside world. We also have something called an identity-aware proxy inside of Google, and that's Google's Beyond Corp, and that basically shifts your traditional networking perimeters to more of a zero trust type model. And this enables organizations to secure resources without the need for necessary VPNs. And what's going on here with these identity-aware proxies and these zero trust models is we realize that some of the boundaries to the internet are getting broken down and a lot of devices are connected. So what we're going to try to do is micro-segment whenever possible, encrypt wherever possible, assume breach whenever possible, so that we have a lot of controls in, and we're not going to trust anything. We're going to verify every request. An identity-aware proxy can control access to cloud-based and on-premise services and virtual machines and applications on-site of the Google Cloud Platform. So it's going to use identity and context to determine whether a user should be granted access to specific resources. So it is context-aware access. Context-aware access is going to determine where you are and should you let someone on. So context-aware could say Mike works 7 a.m. to 9 p.m. every day of the week. So if someone's trying to access the system at 10 p.m. or 6 a.m., it's not Mike. Maybe don't let them have access to the system. Or maybe Mike's in Florida. Don't allow Mike's access from any place outside of Florida without issuing a multi-factor authentication challenge. So if I'm normally on a Mac in Florida, and all of a sudden I'm on a Windows machine in Athens, Greece, determine if it's me, send an additional challenge, or just block it. So, as we start getting into zero trust, identity and access management becomes one of the last lines of defense we always had. I mean, we always had it, but we had boundaries. We're losing these boundaries. So because of the boundary loss, we need something good. So we're going to be using context-aware access. And that's going to integrate very nicely with cloud identity, this identity-aware proxy, and that's going to further enhance our security. Now, when we deal with identity-aware proxy, it does give us some advantages over traditional VPNs. It reduces the overhead of managing traditional VPNs and provides very secure, or I should say very granular access control over resources, which is going to enhance security compared to just perimeter-based solutions like a VPN. But they're not mutually exclusive. You can use both defense and zero trust at the same time. Now, identity-aware proxy is going to simplify user access. It's going to make it easy for users to work across a wide variety of locations. This model this concept of zero trust and context-aware IDAM and perimeters going down is pervasive. It's going on everywhere. So more organizations are using it, and hence Google has got a good functionality for it. The benefits here are it gives you, we're dealing with multiple levels of protection and context aware at the same time. So we're trying to future-proof our environment by making sure we not only have security in our environment, but at the same time, know who the users are, what they're allowed to do. We encrypt everything, and we literally make sure every request is legitimate. So that's really where we're headed with this identity-aware proxy. Now I'm going to talk a little bit about network logging. Network logging is going to be important. You need to know what's going on your network. If you don't, when things break, you won't know why. Or you won't understand if you've got a security problem that's related to your network. Or if things break and it's a network problem, you're not going to figure it out. And you're going to have to get live and troubleshooting and debugging, which you still may need, but you still need logs. Logs should be consistently collected. They should be output, and they should be ideally directed from a security perspective to a SIEM system long term. We need to make sure that we're correlating the logs. If the firewall logs and the network logs and the system logs all say the same thing, maybe we see something going on and we catch it better. So we want to consistently monitor our network. We want to monitor everything. And networking logging is gets us to helps us with that CIA triad, that confidentiality, integrity, and availability. Logs will make sure that the things are confidential. So imagine somebody adding an extra connection to their house on our network. Well, that would be a problem. So we'd see that on the log. New wide area link or new IPsec title turned out. So logs can help us and make sure the systems haven't been tampered with. And they can also prevent tampering, because if you know that you're going to be logged, you might be less likely to do something. So we'll talk more about logs in future chapters, but understand that logging is important. So, in the old world, it was on-premise networking. And guess what? We're having a lot more of it with the cloud repatriation movement. Many things are going back to the data centers. In the cloud, it's basically a virtualized version of the same thing. So you'll determine where you need to place your systems. Should they be in the cloud? Maybe. Should they be in the private data center, private cloud? Maybe. It's going to be up to you to determine what's going to be there. What kind of performance do you need? What kind of security do you need? What kind of control do you need? What do your workloads work like? That's how you determine. And when you talk to a chief information officer or someone else, all you're going to really do is you're going to make it very clear, well, this is the equivalent of this that you've been using. And then they're going to understand what they have, as well as the migration to the cloud. Okay, Leo and I are back. So we are back. We are here to see if any questions popped up. Then we're going to get into Leo's labs and have some fun with that. So if you're having a good time, maybe give it a like, maybe subscribe to our channel and hit the bell to be notified of some new videos, because we have a lot of them. We produce at least almost one every day. So we've got lots of things to help you in your career. Leo, before the labs, you want to talk about the labs? Do you have anything to say about the labs?
Well, the demonstration that we follow is about creating firewall rules and the different ways to restrict the scope of that rule, to restrict in the case, how many virtual machines will be allowed or to receive the traffic allowed by that firewall rule.
Sounds good. Sounds good and a lot of fun. Were there any questions, Chris? Kevin had a question. Is setting up VPC peering in GCP hard? So I'll give a part answer. I'm going to have Leo answer that. So here's the thing. If you know what you're doing, I don't think anything is very hard. So Leo knows cloud computing very well. Leo knows Azure very well, and Leo knows AWS very well. And Leo knows how to design a data center and what goes in the data center. Now, when I asked Leo to demonstrate this, Leo, had you ever touched the Google Cloud before? Or only the other clouds? So how long did it take you as someone that knew cloud computing to figure out how to set up VPC peering the first time?
Well, given you have the documentation to show the details, in a couple of hours, you can learn how to do that.
Yeah. So, and the point is you knew what a VPC was. You knew what a router was. He knew what a switch was. He knew what a route table was. He knew BGP and all that stuff. So in that case, once you're an architect, you can pick up another cloud just very, very quickly. So that's kind of what you need to think about. As long as you understand the underlying piece, any of this stuff is silly easy. But don't understand the underlying technology, And it's like me speaking Portuguese, and all I can say is papagayo, which means parrot. And other than that, I just have no idea, because I had some Brazilian friends that were staying at my house, and my wife was speaking Portuguese because she was fat. She was able to learn it in a few weeks while they were there, and that was the one word I knew. So, that's the key. As long as you know it, you should be fine. All right, give me a hashtag Google Professional Cloud Architecture, something that I know you're awake, and then we're going to start having fun with the labs.
Hello, in this lab, I will demonstrate how to create firewall rules to restrict HTTP traffic to specific virtual machines. I will use the virtual machine to which I attached the service account in the previous lab. I will click Docs to open Google documentation. And here from the left side panel, I will click Networking, scroll down. I will click Network Security, and then Cloud Next Generation Firewall. This opens the Cloud Next Generation Firewall documentation, and this contains different document links for you to learn more about the firewalls and the firewall rules. There are some training and some related videos as well. I will scroll back up and click Read Product Documentation. Here is another document on the Cloud Next Generation Firewalls, and it shows some different types of firewalls, some standards and essentials. And here from the left side, under the Configure VPC Firewall Rules, I will click the VPC Firewall Rules Overview. I will recommend again that you read the documentation to understand and learn about the services. There are a lot of content in these documents for you to learn more about the firewalls. Here, under the Target Source Destination section, the first statement says targets identify the network interfaces of instances to which the firewall rules apply. So when you create a firewall rule allowing some traffic into the network, you need to specify the targets or to which virtual machines that traffic is destined. Here, under the target parameter section, there are three different targets: the all instances in the VPC network, the instances by target network tags, and the instances by target service accounts. There are different forms or ways to restrict traffic to the virtual machines. Here, under source and target filtering by service account, the first statement says you can use service accounts to create firewall rules that are more specific in nature. For both ingress and egress rules, you can use service accounts to specify targets. I will scroll a little bit more, and here filter by service account versus network tags. The first bullet point says a network tag is an arbitrary attribute. One or more network tags can be associated with an instance by any identity and access management principal who has permissions to edit it. So, network tags are more susceptible to be changed by different users with IAM permissions. A service account represents an identity associated with an instance. Only one service account can be associated with an instance. You control access to the service account by controlling the grant of the service account user role for other IAM principles. For an IAM principle to start an instance by using a service account, that principle must have the service account user role to at least use that service account and appropriate permissions to create instances. So it is much difficult to change or tamper with service accounts associated with virtual machines than it is to change network tags associated with virtual machines. I will keep scrolling down. It shows some use cases here. But here from the What's Next session, there is a link to create and work with firewall rules. See this document, use VPC firewall rules. I will click the link to open the document. And here under the create VPC firewall rules, there are the steps to do to create the rule. But before I create the rule, I will show the existing firewall rules in my VPC, and I will also test the access, if I have access to the virtual machines the way it is right now. I will open the VPC and network firewall page in another tab here. And here I can see there are two rules on this VPC, one allowing ICMP traffic and the other rule allowing SSH traffic. There is no rule to allow HTTP traffic in this VPC. I will now test the accessibility to each virtual machine web server. These virtual machines I have here, they were created with a custom image with an Apache web server installed on this virtual machine. So if there is access to the virtual machine, it should show a hello world minimum HTML page that is configured in each of these virtual machines. I will copy the external IP address of each virtual machine, paste here in the tab, and this is simulating user attempts to access the web server on those virtual machines. And right now, all virtual machines or all requests sent from this browser to the virtual machines are not being replied. So at this moment, there is no access to those virtual machines because there is no firewall policy or rule allowing HTTP traffic into those virtual machines. Let's create a firewall rule allowing HTTP traffic. Since I am already here in the VPC firewall policies page, I can click create firewall rule. And then I give the rule a name. I will call it allow HTTP traffic. I will select the network as my lab VPC network. The direction of the traffic is ingress, meaning attempts coming from the internet to access the web server on those virtual machines. The actionable match is to allow the traffic, and here on the targets, I will select the first option, all instances in the network. This is the least secure of the three options, but I will just use it for demonstration on how easy it is to allow one specific traffic to access or to reach all instances inside the network. The source IPv4 range here, this range represents all possible IPv4 addresses from the internet. And here under protocols and ports, I will select the TCP protocol and set the port A. This is the HTTP traffic And I need to remind everyone that this is not secure. On production environment, please use HTTPS, which is port 443. After setting all this, I will click Create to create the firewall rule, and I can go back to the virtual machine instances and reload them to check if the requests can reach them now that I have the HTTP firewall rule allowing traffic to the virtual machines, and all 3 virtual machines replied with the Hello World page. For the second rule, I will change the rule. Instead of allowing the traffic to reach all instances, I will use a network tag. And just to check the network tags associated with the virtual machines, the VM1 has no network tags. The VM2 has an HTTP-server network tag. And the VM3 has no network tags. This way, I can change the firewall rule to allow the HTTP traffic only to the virtual machines with the tag HTTP server. This is how you can change a firewall rule. You click the name of the firewall rule, click Edit, and then you change the parameter you want to change. In this case, I will change from all instances in the network to specified target tags. And the target tag is HTTP-server. I can now click Save, keeping all other parameters the same, and go back to the virtual machines and test if the requests can reach the virtual machines. The VM1 is trying without reply. The VM number 3 is also trying without replies. And the VM number 2 immediate response to the requests, showing the Hello World page, because the firewall rule restricts the traffic only to virtual machines with the HTTP server network tag. Let's go back to the virtual machine number 1 and add a network tag, just to demonstrate how we can add a network tag to an existing virtual machine. You select the virtual machine name, click the Edit button, and then here under Network Tags, you enter the name of the tag you want to add to that virtual machine. In this case, is the HTTP server. The virtual machine is still trying without success. Once I hit Save, I will test the access to the virtual machine number 1, and it shows the Hello World page. So the requests from the internet are now accessing the VM1 and the VM2, while the VM3, which doesn't have the network tag, is unreachable. Now let's change the firewall rule again, and this time we will use a service account to restrict the HTTP traffic. Clicking the name of the rule and clicking Edit, I can change from specified target tags to specified service accounts, and then I select the target service account, which is HTTP Access Service Account. Keeping all other parameters the same, I click Save, and now I expect only the virtual machine number 3 to be able to respond or to be reachable from the internet. Let's check the other virtual machines, and it seems they are working, but it was unexpected. Let's check again. Refreshing the VM1. Refreshing the VM number 2. And refreshing the VM number 3. Let's check the... Oh, for some reason I have two allow HTTP traffic rules. I will remove this one. I probably did a change in the wrong rule. And I'll click the name of this rule. And it's still using target tags. I will click edit to change from specify target tag to specify service account. Select the service account and then click save and test if the requests from the browser can reach the web server on the virtual machines. The VM1 is trying without success, VM number 2 also trying without success, and the virtual machine number 3 is responding almost instantaneously. I will go back to the firewall rules, and I will now demonstrate how you can delete a firewall rule. You select it, and then you click delete. Now we only have two firewall rules, one allowing ICMP and the other one allowing SSH traffic. Since there was an unexpected behavior when demonstrating the different possible targets with firewall rules, I recorded a review of what I have demonstrated today. I recorded this part again to try to uncomplicate the explanation and the actions I did. Here I have my firewall rules. I will refresh to make sure I only have two rules, one for ICMP and another one for SSH. So at this moment, I don't have any rules allowing HTTP traffic into my network. Here I have the three virtual machines, and to make it quicker, I already have the VM details open here, so I can check the network tag. For the VM1, there is no network tag, and also check the service account. For the VM1, the service account is the default one created. Let's check the VM2. The VM2 has no network tags as well. The service account is also the default service account. Now checking the VM3. The VM3 has no network tags, but the VM3 has the HTTP access service account attached to it. Just to prove there is no connectivity to any of the virtual machines, I will open their external IP addresses here in different tabs to test if any of them is able to reply to requests from the internet. And all of them are trying, I have three tabs trying to reach the three virtual machines, but they are getting no replies. I will now create a firewall policy to allow HTTP traffic and I will select the network. And for the first one, I will select all instances in the network, select the TCP protocol, and define the port 80, and click Create. Firewall rules, go to issues. Oh yes, I did not set the source 0.0.0.0/0, allowing all and any IPv4 address to reach the virtual machine, since now I have a firewall rule allowing traffic to the virtual machines. So now I have this firewall rule with targets all. It applies to all virtual machines in my network. Let's refresh or reload the 3 different tabs to try to reach the virtual machines. And all of them are replying to the requests coming from the internet. At this point, I have my allow HTTP traffic rule allowing traffic to all virtual machines. Let's edit this firewall rule and change from all instances in the network to specified target tags. And the target tag will be HTTP server. The same source range, the same protocol and port, and click Save to save the change to this firewall rule. Reminding that none of my virtual machines have a network tag, not VM1, not VM2, and not VM3. For this reason, none of them should be reachable from the requests sent in the browser. And the browser is trying, but there is no request, so it will keep trying until it times out. So let's create a network tag in the virtual machine number 1, reminding I have three firewall rules, one for HTTP that allow traffic to the target with HTTP server network tag, and we have another rule for ICMP and another one for SSH. Let's edit the VM number 1 and add a network tag to this virtual machine. Here is the network tag, and I will enter HTTP server and click Save. Notice when I saved, it checked the Allow HTTP Traffic option here. And over the firewall rules, I will refresh. It created another rule to allow HTTP traffic also for the targets with HTTP server network tag. So keep in mind that every time you edit a virtual machine to add a network tag, it will create another firewall rule allowing traffic to those targets. I will delete this newly created firewall rule because I already have my allow HTTP traffic for those targets created. And I will go back to the tabs trying to reach the virtual machines and try to refresh them to see which virtual machines are reachable. And as expected, only the virtual machine 1 is reachable. The other 2 are trying until they time out because there is no response from VM2 or VM3. If I go back to the firewall rule and change it again, I would select the name of the rule, click Edit, and now I will select Specified Service Accounts, and I will select the service account that is attached to the virtual machine number 3. And now, for some reason, that service account doesn't appear as selectable. But I have demonstrated this before, so the only important part of this review is that whenever you edit a virtual machine and add a new network tag, a new firewall rule will be created. Keep that in mind. And that's it for this review. To delete a service account is just a matter of visiting the IAM and admin service accounts page, selecting your service account, and then hitting delete. The service account is deleted. In this lab, I demonstrated how to create firewall rules to restrict HTTP traffic to specific virtual machines. I demonstrated using different targets, all instances in the network, network tags, and service accounts. Thank you for watching, and see you in the next lab.
Okay, Leo and I are back. Does anybody have any questions for Leo about these labs, or me about anything otherwise? If so, now's a great time to ask them. If not, I'm learning how to play YouTube. If you're enjoying the video, give it a like. Please subscribe to the channel, that kind of thing. And but if you do have a question, we definitely want to answer it. Leo, what's next?
Well, Mike, before telling you and everybody what's next, I will just go back to that question: how hard is it to configure the services on the platform?
Okay.
Right? This lab was an experience, and I faced 2 moments where something unexpected happened. The first one, when I created the network tag, a new firewall rule was automatically created. I wasn't expecting that. And the other moment, when I looked to create a firewall rule with the service account, and the service account wasn't there, could not be selected. So sometimes you have to deal and learn your ways into the interface of the cloud platform, so you avoid those difficulties. What we will see now is a demonstration about load balancers, how to create load balancers, how to define the targets, the load balancers we will use.
Sounds good. I love load balancers. Give me a hashtag load balancers, or a hashtag Google Professional Cloud Architect, or Google Professional Cloud Architect certification, or Professional Cloud Architect exam, or even PCA or patient controlled analgesia, whichever you prefer. Professional Cloud Architect or patient care associate, whichever. And this will be the last lab that we're going to do today. So let's have some fun with it.
Hello. In this lab, I will demonstrate how to set up a regional external load balancer. I will start here at this page, cloud.google.com, and I will use the search functionality here and enter the keywords external load balancer. Here, the first link is External Application Load Balancer Overview. I will right-click this link to open in a new tab, and I will scroll down to see if Here is another link, Cloud Load Balancing Overview. I will click this link to open in this page. And here is the Cloud Load Balancing Overview documentation. As usual, I will recommend you read the documentation to learn about the technology you are going to use. There is a lot of content here, the different types of load balancers, the differences or the characteristics of the application load balancers and the network load balancers. The components of the load balancers, the underlying technologies. And here is an interesting section, choose a load balancer. The first statement here on this first paragraph reads, to determine which cloud load balancing product to use, you must first determine what traffic type your load balancers must handle. So everything should start from the need. You have one specific type of traffic that will direct your selection of the load balancer to use. I will keep scrolling down. Here under the What's Next session, there is a link to help you determine which Google Cloud Load Balancer best meets your needs. See, choose a load balancer. I will click this link to open the document, choose a load balancer. And besides what is in that section of the previous document, there is a lot more content here on this specific document. The aspects of the load balancers, the traffic type, global versus regional load balancing. So there is a lot of content here, and you can cover this content on your own time. I will close this tab to switch to the other document. I opened the external application load balancer overview, and it covers the different modes of operation, the architectures of the load balancers. You see, it's a very content-rich document. And here, under the Firewall Rules section, it reads, the load balancer requires the following firewall rules. For the global external application load balancer, an ingress allow rule to permit traffic from Google frontends to reach your backends. For the regional external application load balancer, an ingress allow rule to permit traffic from the proxy-only subnet to reach your backends. An ingress allow rule to permit traffic from the health check probe ranges. For more information about health check probes and why it's necessary to allow traffic from them, see probe IP ranges and firewall rules documentation. Here on this table, there is a health check source ranges and two side ranges or IP address ranges appear here. And the source of Google front-end traffic depends on the backend type. For instance groups and zonal network endpoint groups, you should use these two ranges. For other types of backends, you should use other IP address ranges. Here from the left side menu, I will click Set up a regional load balancer, and then I will click Manage VM Instance Group Backend. This opens the Setup a regional external application load balancer with virtual machine instance group backends. Here there is some information about the permissions needed to do the activities for setting up the load balancer. If you have created your personal account to learn about the Google Cloud, you have all the permissions needed to do all activities on the Google Cloud platform. But if you are an employee, you will need specific permissions to execute different tasks. Scrolling down here, under the Setup overview, there is a diagram. I will right-click this diagram to open in a new tab, and we can observe that there is no single block or logical block named load balancer. We see there are some external forwarding rules with reserved external IP addresses. There are some regional target proxies, regional URL maps, regional backend services, regional health checks, proxy-only subnets, and the VPC structure with the availability zone and virtual machines inside a managed instance group. Going back to the other tab, I will keep scrolling down. Here we have the configure the network and subnets section, and we have the steps to configure the network and subnet for backends. The first set of steps here, they will create the VPC. Since I already have the VPC from another labs, I will use that existing VPC, and I will open from the top left menu. So I go to VPC network and then VPC networks. And here I have my lab VPC network with 3 subnets. And I have one subnet in the region US West 1, and the other 2 are on region US East 1. From the firewalls tab here, I can check the existing firewall rules. And there are only 2 firewall rules to allow SSH and ICMP. Now I will switch to the Compute Engine VM instances page to show the 3 virtual machines I have. They are running, they are active, and they were created using an instance template. I will show how they were created or the content of the instance templates in a while. Right now, I will copy the external IP address of each one of these virtual machines, and I will paste that IP address in a browser tab to try to reach the virtual machine. These virtual machines, they are configured with a web server, with an Apache web server. Now we have one tab for each virtual machine, and the requests are being sent, but no replies are being received from the virtual machines or from the web server from each virtual machine. The next step would be to configure the proxy-only subnet. And here are the steps to configure the subnet. But before going to the steps, there is an important message here. So I will read these paragraphs. A proxy-only subnet provides a set of IP addresses that Google uses to run envoy proxies on your behalf. The proxies terminate connections from the client and create new connections to the backends. This proxy-only subnet is used by all envoy-based regional load balancers in the same region of the load balancer VPC network. There can only be one active proxy-only subnet per region per network. So this is a limitation. There can be only one active proxy-only subnet per region per network. And the important information here is don't try to assign addresses from the proxy-only subnet to your local load balancer's backend. You assign the backend instance IP addresses from a different subnet range or ranges, not this one. Google Cloud reserves this subnet range for Google Cloud Managed proxies. To create this subnet only, we need to go to the VPC networks and then click Add Subnet and enter name, region, the purpose, and one specific IP address range for the proxy-only subnet. So let's go to the VPC network. I will open this in another tab. Switch to that tab. Click the name of the VPC. I already have. Click the Subnets tab. Then click Add Subnet. Here I will enter the name of the subnet, and as per the documentation, I will enter proxy only subnet. The region will be US West 1. And as per the documentation, the purpose should be regional managed proxy. And the IPv4 range should be 10.129.0.0/23. As I mentioned, the load balancers are virtualized software devices, so are the proxy-only subnets. They have this IP address range, which doesn't change from project to project. There is one distributed proxy-only subnet with the same IP address range, and that's why you can only have one active, because the IP address ranges for all proxy-only subnets is the same. I will go back to the document, scroll down to the configure firewall rules, and here we have the name of a firewall rule, firewall allow health check, an ingress rule applicable to the instances being load balanced that allows all TCP traffic from the Google Cloud health checking systems. This example uses the target tag load balanced backend, but since the virtual machines I have, they use a different target tag, I will change this parameter to the target tag already existing in the virtual machines. The other ingress rule is applicable to the instances being load balanced that allows TCP traffic on ports 80, 443, and 8080 from the regional external application load balancers managed proxies. Without these firewall rules, the default deny ingress rule blocks incoming traffic to the backend instances, and they are unreachable, as I demonstrated before. Let's scroll down to the steps and let's create these two firewall rules. From the VPC networks, now I will select firewall and open in a new tab. And now I will click create firewall rule. Let's use the name of the rule as per the documentation, firewall allow health check. I will select the network, which is the existing network I have, you need to use the name of the network you have created. Specify target tags. I will not use the target tags from the document because the virtual machines I have already created, they use the HTTP-server target tag or network tag. And here for the source IPv4 ranges, I will use what is informed in the documentation 130.211.0.0/22, and the other one is 35.191.0.0/16. I will scroll down to select the TCP protocol and enter the port 80 and click create to create this first rule. And then I will click create firewall rule again to create the second rule, which is named firewall allow proxies. I will select my VPC network, the same target tag HTTP-server. Now the source IPv4 ranges is the CIDR range for the subnet only proxy, which is 10.129.0.0/23. I will select the TCP protocol, and now I will enter the ports 80 and 8080. I will not enter 443 because I will not use HTTPS on this demonstration. If you are doing something similar for production environment, you should use HTTPS on port 443. I will click create to create this second firewall rule. Now, since I have these two firewall rules allowing HTTP traffic into the network, I will check if I can reach the virtual machines. And it seems they are still unreachable because the firewall rules are limiting the origin of the connections from two specific places. One is the proxies only subnet, and the other one is the health checks. I will go back to the document and scroll down to the next step, which is to configure a regional external application load balancer with a virtual machine based service. Create a managed instance group backend. In my case, I already have the managed instance group. If you don't have, you can use the steps to create the managed instance group. I have demonstrated how to create the instance template and the instance group in previous labs. I will now show how these virtual machines I have were created. I mentioned before they belong to a managed instance group, and I will demonstrate here by selecting instance groups in a new tab. This instance group has 3 instances, and use this template to create those instances. US West 1A -subnet 1. And if I open the instance templates page here, the US West 1A -subnet 1 template was created having the network tags HTTP-server, and it belongs to the lab VPC network and uses the custom image, Ubuntu Apache custom image to create the virtual machines with the default service account. This instance template also has a startup script, and this startup script is a little bit different from the one presented here in the documentation in this part. It has the same effect, or the objective is the same. Here, this first command queries the virtual machine metadata and get its name and stores in this variable VM dash underscore name. The second command queries the metadata to obtain the external IP address and save in the external IP variable. Those two variables will be used later in the same code. After getting those variables, the next command removes the existing index.html file, and then the other command creates a new index.html file with this content. So this is a minimum HTML file. Here the head is what shows on the browser tab. Under the script, there is a small script just to randomize the background color of the page. And in the body of the index.html file, we have one title, welcome to my custom page, and then two lines showing first the virtual machine name and then the external IP address of this virtual machine. Since this startup script runs when each virtual machine boots up, each virtual machine will display their own name and their own IP address on the index.html page served by the web server installed on those virtual machines. Going back to the documentation, I will go to the next step, which is to add a named port to the instance group. I need to go to the instance group page and then edit to add the name tag, name port. So instance group page. I click the name of the instance group, then click edit. I scroll down to the port mapping section, and then I click add port. And well, I need to enter HTTP and then the port 80. And then I click add port. Well, actually this one is already added. Let's click say is already entered the data. I will click save to create this mapped port. Let's go back and see port name mapping HTTP 80. The next step is to reserve the load balancer's IP address. I will go to the VPC network IP addresses page. I will right click and open in a new tab, switch to that tab. And if I select external IP addresses, there are 3 IP addresses. Each one belongs to one of the virtual machines, and internal IP addresses also 3, one to each virtual machine. I will click Reserve External IP Address or Reserve External Static IP Address. Enter a name that I want for this reserved static IP address. Static IPv4. And as per the documentation, I will change the network service tier to standard. I will allow the regional as selected for this IP address. I will select the region where my VPC exists, US West 1. And from attached to, I will select none as instructed in the documentation. And then I will click Reserve. Now from external IP addresses, there are 4, and one of them is named static IPv4. Here there is a warning that is not being used by any service, and take care about the costs involved with IP addresses or reserved static IP addresses, because they are charged more when they are not in use by any service. Going back to the document and scrolling down, the next step is to configure the load balancer. I will scroll down to the steps, and now we have quite some steps to execute. But we need to start with the step number 1. That is to go to the load balancing page, and then I will go to the network services load balancer. If you are not seeing the network services on your menu, click View All Products, and then from networking, you can find network services. Click Create Load Balancer. And the documentation instructs to select an application load balancer and click Next. Then allow the public-facing external to be selected and click Next. For the global or single region deployment, select Best for regional workloads and click Next. And then click Configure. Here, there is the basic configuration. I will enter the name for the load balancer, and the document calls it Regional Layer 7 X Load Balancer. I will select the region as US West 1, and also the network, my VPC network. It already detects that I have the proxy-only subnet already configured. And then now I can go to the front-end configuration and name this front-end configuration as Layer 7 X Load Balancer Forwarding Route. The protocol is HTTP. The documentation instructs to change the network service tier to standard, and then enter the port 80. And now I need to select the IP address or the reserve static IP address. That is this one, static IPv4. Click Done. The documentation follows with the instructions for HTTPS. I will not use HTTPS. Therefore, I will skip to the backend service. Click backend configuration here, and then select create a backend service. Enter the name for the backend service, which the documentation called layer 7 X load balancer backend service. The backend type is based on an instance group. The protocol is HTTP, name port HTTP. Here under backends, I will select the instance group to which the existing virtual machines belong to, or they were created by this managed instance group. The balancing mode is utilization, and we can keep the remaining parameters and then click done. From the health checks part, I can click create a health check and then enter a name for the health check, which is layer 7 X load balancer basic check. Protocol HTTP port 80, and then we can click create, and then we can click create. I will click OK now. Into routing rules, the documentation informs to set the mode to simple host and path rule, and to ensure that the load balancer backend service is the only backend service for any unmatched host and any unmatched path. So there is only one. And then I can click review configuration, and then I can click create. When the load balancer is being created, I will go back to the document, and then there are some steps to connect if you have a domain to connect with the load balancer. Since I don't have a domain, I will use the reserved IP address to try to access the load balancer and therefore the virtual machines. The next step here in the document is to test the load balancer. So in the load balancing page, select the load balancer just created, and in the backend section, confirm that the virtual machines are healthy. Let's go back to the load balancing page. Here is the load balancer. Let's check the backends. Here is the backend service. Clicking its name, it will show 3 of 3 virtual machines are healthy. So now I will go to the virtual machines again and check if I can reach them from a web browser, simulating requests coming from the internet to those virtual machines. Even though now I have 2 firewall rules allowing HTTP traffic into the network, those rules are very specific and they don't allow any requests coming from the internet to reach those virtual machines. Once I copy the external IP address reserved for the load balancer, and I use that address in a browser tab, we reach the welcome my custom page. And here we have the name of the virtual machine and its IP address. The first one ends with 97, which is this IP address. And we have if I go to the virtual machines page, This is the virtual machine 97. The other virtual machines IP addresses end on 151 and 144. If I refresh this external IP address trying to reach the virtual machine in the load balancer, each refresh will change, or at least will send a request to the virtual machine. If it goes to the same virtual machine, at least it will change the background color, because each request will generate a random value for the background color. So we can see the virtual machine names and IP addresses changing here with each refresh of the page. Going back to the documentation, there are some additional configurations I will not do in this lab. You are free to play with these configurations and try learning new aspects of the load balancers. Here, from the What's Next session, I will go to the Clean Up the Load Balancer setup. I click the link to open the document, and it states that deleting the project will delete everything with that project. But since I will reuse the virtual machines, the instance group, I will delete individual resources. And we start by deleting the load balancer itself. So if I go to the load balancers page, and here load balancers, I select the name of the load balancer and then I click delete. I select the other services that were created with the load balancer, so they are deleted as well, and click delete to delete them. Now I will go to the IP addresses page and refresh. The static IP address is not being used because I issue the deletion of the load balancer. I can select the static IPv4 IP address and release this static address, so I am not incurring any costs for having this reserved IP address without use. Since I deleted the IP address, it doesn't make sense to use the IP address in a browser. It will show some error or will not receive any reply from the virtual machines. And if I test the virtual machines, they continue not reachable. And now I can go to the firewall policies and delete the two policies that were created to allow HTTP traffic inside the network. I can also go to the VPC network and under click its name to show the details, and from the subnets I can delete the proxy-only subnet that was created to be used with this load balancer. I click the delete icon here and confirm I want to delete that proxy-only subnet. In this lab, I demonstrated how to set up a regional external load balancer. I used existing virtual machines that were created with a managed instance group which used an instance template with a custom image, a network tag, and a startup script to be run on every boot of the virtual machines. Thank you for watching, and see you in the next lab.
Okay, we are back. So hopefully people had fun with Leo's labs. I'll check and see if there were questions with Leo's labs. Then I'll remind everybody that we have another day tomorrow, which is lots of fun. And the day, and then next week, all next week, we have plenty of more Google Professional Cloud Architect training. So, were there any questions that popped in along the way? And then,
well, Mike, if I may, this load balancer was a regional load balancer. The backend virtual machines were in one region only. Tomorrow, we will have another demonstration about load balancers, which the backend virtual machines will be in 2 different regions. So it will be a multi-region load balancer. And in this lab, I mentioned instance templates, create and manage instance groups. I used a custom image to the virtual machines. All this we'll demonstrate in labs as well next week.
Yeah. And I think there was one question I think I'll address. So the web developer that would write a web page code, they can trade the color, but as a cloud engineer, you're not making web pages. And as a cloud architect or a solutions architect, you're not going to be touching the web either. So Leo was just using them as a demonstration, but but I understand. But if he was a web developer, he'd do all kinds of things to make it look like it fit for the outside world. So we're going to start with labs first thing in the morning. Before we go to the next session of content on compute, I like to babble about compute. I love compute. I've not only worked with servers forever, I've been building my own stuff for fun forever just because it's kind of cool. So we'll talk about that. And I'm on a custom system I built here myself just because my Mac wasn't strong enough. So I've got a cool little toy that I built myself because sometimes it's kind of fun. So Leo's got all kinds of things that he'll be talking about. He can enlighten you on that. But Leo, what else are you going to be talking about tomorrow?
Well, in the sequence, tomorrow we'll start the compute content, and related to the compute, we will have labs demonstrating how to create virtual machines, how to use startup scripts, how to create the custom image to use in virtual machines as well. So
got it.
Be prepared.
Sounds great. Maybe give us a like if you had a good time. Please share this free boot camp with others that you could use help. I see we had people all over the world today, for everywhere from South Africa to India, all over the United States. I saw we had people in England. I know there's some people in Europe as well. So please share this with others. We want to do what we can. And, maybe subscribe. If you're not a subscriber, I produce a video almost every day. Honestly, sometimes it's more than I do on a day. But so hopefully you'll get to see these things. So good to see everyone tomorrow. Tomorrow we'll begin with the labs. Give me a hashtag Google Professional Cloud Architect, and we will see you tomorrow. Okay, welcome back. We are here for day 5 of the Google Professional Cloud Architect Bootcamp to prepare you for the Google Professional Cloud Architect certification and Professional Cloud Architect exam. My name is Mike Gibbs. I'm one of your instructors throughout this program. I am joined here by Leo Paredes from our team. Leo is a dedicated engineer with more than 2 decades of experience. I'm obviously an architect who's been an architect for about 25 years, well, a little more than that, but I'm just going to keep it at 25 years. It doesn't sound so bad. So we're here today for another day in the Google Professional Cloud Architect Bootcamp. If you just joined us now, or just heard about this now, or just found out, don't worry. You can go back and watch day 1, day 2, day 3, and day 4. And we'll be training all of next week for this Google Professional Cloud Architect exam as well. So you can watch them all over the weekend. Maybe invite a couple of friends to watch the videos with you. And then we'll be back next week. Couple of things to talk about, and then I'll give you the overview of the day. And then Leo's going to talk a little bit because Leo's got a big role today. But I wanted to let you know that we have a guide on how to help you pass the exam. My team wrote it. It's about 550 pages. It's probably almost as thick as this book that I actually really like from Cybex. That's that I actually thought was great to prepare the exam. Yes, about 200 pages. Ours is about 500. So hopefully it'll give you a lot of guidance. Again, I do like that Cybex book and highly recommend it. I'm not an affiliate. I don't get paid for it. I just like the book. I think it's a great book. But to show you, we put a lot into this. So go download the study guide, or download. I mean, sign up, and it'll be emailed to you. And go out there and really learn something from this. So, that's good. I'll let you know that every Thursday we have an architect webinar, how to become an architect. My team will drop a link to that. We'll go over what we do as cloud architects, solutions architects, AI architects, executive architects, any other kind of architect you want, and we'll answer any questions. And I also want to let you know that about once a week I come online to answer career questions. So keep track of us, subscribe, hit the bell to be notified of new things. When I come online and you've got questions to ask, I'll be here to answer them for you. So today we have a lot of labs. We're going to start out. We've got a lot of labs, like one big one and a couple of small ones. So, and then we also have some lectures today, but it's going to be a big, heavy lab day, which I think a lot of people are going to have some fun with. So, Leo, could you tell me what labs you have going on today?
Sure, Mike. The first lab for today is a continuation of yesterday's topic, the networking. The lab is about load balancers, how to use load balancer to direct traffic to virtual machines in different regions. Yesterday's lab was about directing traffic to virtual machines in the same region. Today's lab will be multi-region load balancer.
And that's great. So thank you for that, Leo. I'm going to be talking about compute, like things like virtual machines and containers. We're going to have a little fun with that. You'll get to see some of these things in action. So let me know that you're awake, you're alert, and you're oriented. Give me a hashtag Google Professional Cloud Architect or something to that so that I know you're awake. And as soon as I start seeing that and I know you're awake, let me know. I also like to know where you're at today. Where are you at in the world? I know I'm in Port St. Lucie, Florida. I know that Leo's in Sao Paulo. I know Chris is behind the scenes in St. Petersburg. But where are you? St. Petersburg, Florida, as opposed to St. Petersburg in Russia. So, but that's where he's at today. So let me know where you're at. I know some of you have got to be in Europe. I know a lot of you have got to be in Africa. I know some of you have got to be in the Middle East, and some of you are Asia or even Australia or other parts of the world. So let us know, South America or North America, like us. And we'd love to see that in the chat box. So let me know where you're from. And give me that Google Professional Cloud Architect. I heard it from Adrian. I know Adrian's awake, alert, and oriented. I see it from Ben. Gives me a little idea of the amount of latency between the time I speak and the time you guys see stuff as well, because there is a delay on this. So Phoenix, Arizona. Oh, that's a nice dry place. Jersey City. I actually worked in Jersey City for about 1.5 years. It was really hard to get to because it was either take like the PATH train and all these other trains or drive up, which is what I did every day. Emmanuel in Germany, fantastic. I absolutely love that. We've got someone in India. I absolutely love that. Thank you for sharing some of your geography. I love knowing that we have people everywhere. And because we're all the same. And it's nice to actually get everybody together for a common goal. At least that's something that I've always dreamed about is get everybody together, train people for the better future, and all have better lives. So, Chris, I think we know where people are from. I think they're awake, alert, and oriented. Let's start with the content.
Hello. In this lab, I will demonstrate how to create or set up a multi-region load balancer. In the previous lab, I used this document to set up a regional external application load balancer with virtual machine instance group backends. From the left side menu, I will scroll down to open the Explore Tutorials topic. Then I will click the first item, Request Routing to a Multi-Region External HTTPS Load Balancer. I will use HTTP and not HTTPS in this demonstration. Here, under the Overview section, it reads, "This guide provides instructions for creating a load balancer that directs traffic based on the path in the request URL and balances traffic across multiple regions. You create 8 total compute engine instances in the US in Zone US Central 1B and Europe in Zone EU West 1B regions. You then create a load balancer that routes traffic to these instances. And here is the diagram for this system. I will right-click and open the diagram in a new tab. And the functionality of this load balancing is basically to receive the requests from the internet. A forwarding rule will forward the request to the target proxy. The proxy will pass the request to the URL map, which has the responsibility to directing the URLs that contain the /video in it to the corresponding backend service. The requests that don't contain /video in them, they will be sent to another backend service. Each backend service is responsible to direct traffic to two different regions or two different groups of virtual machines, one in the US in region US Central 1, another one in Europe in region Europe West 1B. The same is valid for both backend services because the pool of virtual machines, they are for different responsibilities, but they are located in the same region. The same US Central 1 region will have a pool of virtual machines for anything except video, and also a pool of virtual machines for responding for video requests. The same is valid for the other region. I will not use Europe. Instead of having this backend directing the requests for a group of virtual machines in Europe, I will configure a subnet in South America. I will continue to scroll down. And there are some permissions considerations here. If you created this account to learn the Google Cloud Platform, your user has every permission needed to do this lab. If you are an employee in an organization, you will probably need specific permissions to do these tasks. I will keep scrolling down. Here is the setup part. And there is an optional suggestion to create a new project. This makes the cleanup easier because when you delete a project, you delete all the requests or all the resources inside it. But if you want to reuse the project later, you should do the cleanup, deleting the individual resources used in this demonstration. Here is the configuring a network and subnets section with the names of the subnets, the respective IP addresses to be used, and the regions where the subnets will exist. I will replace the EU subnet with a South America subnet, but using the same IP address range. Here are the steps to create the custom mode VPC, and I will go to the console to execute those steps. From the top left side menu, I will select VPC Network and then VPC Networks. I will click Create VPC Network. And then here, the name of the network I will follow and use all suggestions from the documentation. It should be LB Network. The subnet creation mode will be custom. And the new subnet, the first one will be called US subnet. And the region will be US Central. US Central 1. I will only use IPv4 in this demonstration. The IPv4 range for this subnet should be 10.1.10.0/24. And I click Done to create this subnet or to finish the configuration of this subnet. I will click Add Subnet to add the second subnet for this project, but I will not call this EU subnet, but I will replace the EU with South M as in South America, and the region will be South America east-1. The IPv4 range is the same suggested for the EU subnet in the documentation 10.1.11.0/24. And click Done. Now I have the two subnets set to be created, and here I have the option to set or select some firewall rules. On the bottom, we have two rules that cannot be unselected. They are created by default, and the first one is to deny all incoming traffic, all ingress traffic into the VPC with a very low priority or the lowest possible priority. And the other rule is to allow all egress or all traffic going outside the network. So no traffic by default is allowed in. Any and every traffic by default is allowed out. Any rule that you create will, with a different priority, will override the default deny all ingress traffic rule. For this demonstration, I will need to create a rule to allow HTTP inside the network. For now, I will select the ICMP and SSH rules just for simplicity. The dynamic routing mode, I will select global since I'm using more than one region, and then I will click Create to create this VPC network. While the network is being created, I will go to the firewall page here on the left, and it shows the ICMP. This VPC network already has a default VPC. Let's go back to the VPC network VPCs, and the default network already exists. For this reason, there are some rules here in the firewall rules that are for the default network. These are the only rules for the load balancer network VPC just created. And I need to create a new firewall rule. So I will click Create Firewall Rule, enter the name of the firewall rule as Firewall Allow Health Check in proxy. If I haven't done, I will not create the first firewall rule on the document, which is for creating the SSH, allow SSH, because I already selected the option from the firewalls page. I'm creating this new rule here. And here I will select the network is not the default one, is the load balancer network, and look at the priority. Every time you start creating new rule, the priority is set to 1000. This rule will override the default rule to deny all incoming traffic. The direction of traffic for this rule is ingress, and the action is to allow the traffic. And here I will specify or restrict. This rule only applies to the virtual machines that has the following target or network tag: allow health check. Only the virtual machines that contain this network tag will be able to receive the traffic allowed by this rule. And the source IP address range, as per the document, is 130.211.0.0/22. I will tab to allow me to create the next one, 35.191.0.0/16. So these are the IP address ranges from the health checks. The incoming requests will not go straight to the virtual machines. The incoming requests will be received in the HTTP proxy, and the health check will verify if the virtual machines are healthy, and then the traffic will be sent from the proxy to the virtual machines based on the response for the health check. That's why only the health check IP address ranges are allowed as source of the requests that are coming to the virtual machines. Here, from protocols and ports, I will select TCP and the port A and click Create. Now I have the firewall rule allowing HTTP inside this virtual private cloud. Let's go back to the document and see the next step is to create instances. The virtual machines in this lab will be created based on instance templates. We will create the templates and we will create manage instance groups which use the templates to create the virtual machines. But the first step is to create the instance template. So I will switch, or I will go to the Compute Engine Instance Templates page, click Create Instance Template, name as per the document, US, or better, video, US template. And it will be created in the region US Central 1. I will keep most of the defaults already selected for creating the instances, but I will change the boot disk because I will use a custom image I have. After selecting the image, I click Select, and then I will open the advanced options for the networking. I will enter the network tag for the virtual machines that will be created with this template. And the network tag is allow health check. Since I created the firewall rule for SSH, I will not create the network tag for the SSH rule. The network interface was created in the default VPC. I will delete that one. Click Add a network interface, select the load balancer network, and select the subnet in the US for creating this network interface. I will click Done. And from the Manage part, I will scroll down to the automation where I will enter the startup script. The document suggests a startup script here. I will not use this exact startup script, but I will use one that does a similar job. I will copy the startup script from my external source and enter it here. And I will explain this startup script. Here, it informs that this is a bash script. The first command will query the virtual machine metadata and bring the name of the virtual machine and store that name in a variable named VM_name. The next command will query the metadata of the virtual machine, bringing the external IP address of this virtual machine and storing this value inside the external _IP variable. These two variables will be used later in the code. I will explain them. After querying the metadata, the script creates a directory because since I'm using an image that already has Apache web server installed, Apache's default path for the resources the web server will send to the user as the response for the requests, the default path is /var/www/html. Since these virtual machines created with this instance are for responding for video requests, I am creating, or the script will create, a video subdirectory inside the default path, and the resources from this directory will be sent as response for the user requests. After creating that directory, the next command removes the original index.html created in the default path of Apache Web Server, and another one is immediately created, but with the following content. Here is the HTML code. Inside the head of the HTML file, there is a title which says My Apache Web Server page. This will be shown on the tab in the browser when this index.html is sent back to the user as a response for the request. Under the head of the HTML file, we have a script section. This script is basically generating a random color for the background of the web page every time this index.html is sent to the user. This means each refresh on the browser when accessing this virtual machine, each refresh will generate a new random color for the background of the page. Now, in the body of the HTML file, there are 3 lines. The first one is the welcome to my custom page. This will be shown on the page on the browser. The second line shows this is virtual machine, and then it shows the content of the VM_name variable, which contains the name of the virtual machine. The third line shows external IP address, and then it shows the value of the external IP address for each virtual machine that is sending the index.html file back to the requests, to the user requests. The last command in the startup script is to copy, since this HTML file was created in the default path for Apache Web Server. The last command will copy the index.html from the default path and paste it into the new path with /video. So the index.html file will exist inside the video subdirectory because some of the virtual machines will respond to requests containing /video in the URL. After setting up the startup script, I can click Create to create the instance template. The next template I will create should be for video as per documentation. The next one should be for video EU template. But as I am not using Europe, I will use South America. This will be called Video South America template. Video South America template. The region will be South America, East 1. Again, I will accept most defaults, but change the boot disk to the custom image. Click Select. Open the advanced options. From networking, create the Allow Health Check. Network tag. Then delete the default network interface and add a new network interface in the load balancer VPC and select the South America subnet click Done. Then from the management, scroll down and paste the startup script. And click Create to create this video template for South America. Now I need to create the www US template. Create instance template, www US template, US Central 1, change the boot disk to the custom image, click Select, open the advanced options from networking, allow health check, network tag, delete the default network interface, add a new one in the load balancer network, South US Central subnet, just to make sure, yes, I selected the US Central. Click Done, and from the management, paste the startup script and click Create. And the last one will be the www Europe template, which I'll use www South America template. The region is South America East 1. Change the boot disk for the custom image. Open the advanced options from networking, create network tag, allow health check, delete the default network interface, create a new one in the correct VPC and region. Click Done. From the management, paste the startup script and click Create. Now I should have the 4 instance templates. I have Video South America, Video US, and www South America. For some reason, the www US doesn't show, or I skipped that step. Let's create the www US template. US Central 1, change, use custom image, open the advanced options, create the network tag, allow health check, delete the default interface, add the new interface in the load balancer network, US subnet, click Done, open the management into the startup script and create. Now I should have the 4 instance templates. And the next step is to add a name port to the instance group. Oh, better, before I add a name port, I need to create the manage instance groups. I'll go to the instance groups page here on the left side menu. Click Create Instance Group. Make sure you select the stateless Manage Instance Group here from the left, and then you enter the name of the instance group as per the document, instance group, video US. In the instance template is the video US template. The location as per the documentation should be single zone. In the region will be US Central 1B. For the autoscaling, I will select off as per recommendation of the documentation, and the maximum number of instances will be 2. Then I will click create. And I will create another instance group. Instance group video South America. The instance template will be video South America. The location will be South America East, South America 1B. Autoscaling set to off, and maximum number of instances 2. Click create. Now creating the www manage instance groups. The first one will be instance group www US based on the instance template www US template. Location US Central 1 zone US Central 1B. Autoscaling turn to off, maximum number of instances 2, and then click create. Now to create the last instance group, that is www South America. Instance group www South America. Instance template www South America template. Location South America East 1, South America East 1B. Autoscaling set to off, maximum number of instances set to 2, and click create. There are some warnings on the instance groups. They are about the autoscaling being turned off. But I see the instance groups were created with one instance. I will click each one and force the number of instances to be 2. I will do this for each manage instance group to make them have 2 instances each. Now, all 4 managed instance groups should have 2 virtual machines each. We only need one more to have 2 virtual machines. Now, the next step is to add the named port to the instance groups. So for each instance group, I will click Edit, and then scroll down to the port mapping, click Add Port, and enter HTTP and the port AE. Click Save and go to the next instance group. Now, all 4 managed instance groups have the port mapping set to HTTP with port 80. The next step is to reserve the external IP address. I will go to the VPC network IP addresses page and click Reserve External Static IP Address. The name for this IP address will be load balancer IPv4-1. Keep the network service tier as premium. The IP version is IP version 4 and the type is global. Click Reserve. We can see the external IP address with a warning, and this warning is about not being used. The static IP addresses reserved, they cost more if they are not in use than when they are in use. The next step in the documentation is to configure the load balancing resources. So I need to go to the load balancing page. From the top left menu, I select Network Services, Load Balancing, and then I click Create Load Balancer. The type of load balancer will be Application Load Balancer. Click Next. The public facing or internal should be selected as public facing and click Next. The global or single region deployment should be best for global workloads. Click Next. And the load balancer generation should be set to Classic Application Load Balancer. And click Next. And then click Configure. Here, we enter the name of the load balancer, which should be WebMap. And then the documentation instructs to configure the backend services. So let's select backend configuration here, the center, and then click the backend services and backend sub buckets and click Create a Backend Service. The name of the backend service should be Web Backend Service. The backend type should be instance group, the protocol HTTP. The new backend instance group selected will be should agree with the backend service. Since this is a web backend service, I will select the web instance group. The balancing mode should be utilization, and then I click done. And I will add another backend. Since this backend service is for web, I will select the other web instance group, which is the www South America instance group. So now we have, for this web backend service, we have two backends, one in the US and another one in South America. I will unselect the Enable Cloud CVM here, and for the health check, I will click Create a Health Check. The name of the health check will be HTTP basic check www. The protocol will be HTTP port 80, and then I can click Create. And then I click Create. We now have the web backend service. Now I will click Create a backend service again to create the video backend service. The backends now will be the video US, and click Add the backend for selecting the video South America. So for the video backend service, we have two backends, one in the US and another one in South America. Again, I will unselect the Enable Cloud CDN, and from health checks, I will click Create a new health check. And the name is HTTP basic check video. The protocol is HTTP, and then click Create. And then click Create again. And there is some issue. Let's remove some letters here and click Create. Now we have the two backend services, one for web, one for video. I can click OK. Click Hosts and Path. Here, for all unmatched path, host and path, when the web backend service is already selected. For the video backend service, I will select the host as in asterisk or star, and the paths will be /video, hit tab, and then /video /star. According to the documentation, now I should configure the front end. And there is some IPv4 configuration and also some certificate. I will set the IPv4, but I will not use certificates in this lab. And then from the front end, I will delete this ephemeral existing one, and I'll click Add Front-End IP and Ports, and I will use the name HTTP content rule. The protocol will be HTTP, and IP version IPv4, and the IP address I will select now the static IP address we created before, and then click Done. And now I can click create. And with this change, the load balancer is ready. The next step in the documentation is to configure IPv6. I will not use IPv6 for simplicity. And the next step would be to connect the domain to a load balancer. I will not use a domain in this demonstration as well. I will skip to the sending traffic to the instances. Basically, is to test the functionality of the load balancer. For sending traffic to the instances, I will switch to the Compute Engine VM instances page. And I will test one external IP address from an instance, or I will test two. Let's say one for South America, one for US. And the requests sent in the browser tabs, they are not receiving responses from the virtual machines or from the web server. I will now get the external IP address from the VPC network IP addresses. I will copy this static IP address and paste it in a new tab and hit enter. And at least it's different. The external IP addresses from the virtual machines, they don't seem to respond. The browser keeps trying, but no response is received. For the external reserved IP address, there is one answer: the site can't be reached. I will keep refreshing this tab with the external reserved IP address up to the point it becomes responsive. While the servers are not responsive, let's go to the network service load balancing. Open the configurations of the load balancer and check the monitoring. Let's go back and select backends. And now, for instance, the video backend service, we can check the healthy, that 2 of 2 virtual machines in South America are healthy, 2 of 2 virtual machines in the US are also healthy for the video backend. Let's go to the web backend and verify if the virtual machines are also healthy and all 4 of them are healthy. Let's try again to refresh the browser tab with the external IP address for the load balancer. After some time, the virtual machines start to respond to the requests I sent for the external IP address allocated to the load balancer. And here I have the response from a virtual machine named instance group www South America with the IPv4 ending on 44. Let's see if we can reach the other virtual machine in the same instance group. And we have the virtual machine number 21 still for the www managed instance group, and all of them in South America. So we have the virtual machines ending on 21 and 44 for the www managed instance group. And now I will add the /video to the request URL and see if virtual machines from the other managed instance group will respond to these requests. And here, the name of the virtual machine is instance group video South America with IP address ending on 52, and the other one will end on 217, still with video from South America. So I have already reached the two different instance groups, one for video and the other one for www in South America. Now I will connect a VPN to obtain an IP address in the United States, and I expect to receive responses from the virtual machines from the US instance groups. The first one should be www. I will not add the video part yet. I will hit refresh now that I have the IP address located in the US. And let's see if the requests are responded by the www US virtual machines. And here we have one with the IP address ending in 58, and the other one ending in 68. Both for www. Let's add the /video to the request and see if the video US virtual machines respond to the requests. And here we have one from South America, probably is about the cache that was in the browser. Let me refresh the page. And now we have a virtual machine from the instance group video US responding to my video request. IP address 236. Let's see the other virtual machine is the virtual machine ending with 43 from the instance group video US. With this, I demonstrated that all 8 virtual machines are responding to requests sent by the browsers. We have 2 different backends, one for video and another one for anything but video. And we have 4 managed instance groups, 2 managed instance groups in the US, one for video and one for www, and 2 managed instance groups in South America, one for video and one for www. And the tests showed all 8 virtual machines responding to the requests. If I try to reach the virtual machines directly using their external IP addresses, there is no response. In this lab, I demonstrated how to create the instance groups, the managed instance groups, how to reserve the external IP address, and how to configure the multi-region load balancer. I will now demonstrate how to do the cleanup without deleting the whole project. I will close these tabs I'm not using anymore, and I'll go back to the console, and if I follow the documentation, the cleaning up starts with, if I'm not deleting the whole project, start with deleting the load balancer. So I will go back here to the load balancer. I select the load balancers, and then I select the name of the load balancer here and click delete. It offers to delete all backend and health checks as well. I select all of them to be deleted with the load balancer. The next step will be to delete the instance groups. I will go to the compute engine page instance groups. And let me see if I can select all 4 instance groups to hit delete. I can't. So I will select, not even selecting one by one. I will click the name of each managed instance group and then hit delete group from inside the group. I need to type delete and click delete to confirm I want to delete the instance group. I will do this for each one of the 4 instance groups to delete them. The next step in the documentation is to release the external IP address. I will go to the VPC network IP addresses page, select the static IP address, and then click Release Static Address, and click Release to confirm I want to release that IP address. Then there is the deleting firewall rules part. I will go to the firewall here on the left, and I can delete the firewall rules created for the load balancer network. Then it suggests to delete the virtual machine instances, but this was done when deleting the managed instance groups. So the virtual machine instances page should show the virtual machines already being deleted. For some reason, 2 virtual machines were not deleted automatically by deleting the managed instance groups, and I don't have the option to delete them. So I assume the instance groups are still not deleted. We are still deleting some instance groups. After some time, the managed instance group is deleted, and so are the virtual machines. Now I can go to the VPC networks, click the name of the VPC, and then select Delete VPC Network. I need to enter the name of the VPC here on this field to confirm I want to delete the VPC. After some time, the VPC network is deleted. In this lab, I demonstrated how to set up a multi-region load balancer, and I demonstrated at the end how to clean up and delete all resources used in this demonstration. Thank you for watching, and see you in the next lab.
Welcome back, everyone. So I hope everybody enjoyed Leo's lab. We got fairly technical on that. Leo, while we wait to see if there's any other questions, and there's a question, really good question from In Production that I'm probably going to spend 10 or 15 minutes on, because it's a real question, it's a deep question, and I have to give them the test answer, but I want everybody to know the real answer. Do you want to tell everybody real quick what the next labs are about?
Sure, Mike. We will have labs on creating the virtual machines and how to use the startup scripts on virtual machines as well.
Sounds great. Okay, so Chris, why don't we bring in the first question? If you have some questions, ask them. And so I know that you're here and you're awake and you're alert and oriented. Maybe give me a hashtag Google Professional Cloud Architect or something like that. So in production, Mike or Leo, could you discuss the machines, type, series, codes, platforms you see? So here's what I'm going to discuss. First, I'm going to answer your question in the most professional certification approach. And then I'm going to tell you the reality that you actually need to know. But for the professional approach, I'm going to point you to this Google page here. And I'll pop the link in the chat box. And this Google page is updated by the people at Google Marketing. And they basically give you all the names that they actually call their systems as they use them. So if we walk through this, you can see as we drive down, they'll have their machine families, and you can view what they viewed as their first and second generation servers. Now, these will tell you they're Intel. You're going to have to research the processors on what these actually are, and I'll actually talk about what that is in a minute. But they'll use the way they categorize these technologies. So, for example, you'll be able to see which ones have local SSD that you could use versus something that would just be block storage somewhere else. You can tend to create your own. And then they're going to make recommendations on marketing, like this type of C4, this is good for a database or a high volume web traffic or an analytics traffic. So they're going to tell you what they actually recommend, but these are marketing terms. For example, AWS has i3 instances. They call them general purpose compute. The i3 instances, I use them in my house. I've got to tell you, I bought the servers from Amazon. They're $400 right now. You can buy these same servers. They've got dual Xeon E5 2670 V3s in it, about 128 gigs of RAM in it. I've got like 10 of them, and they're about $400 each because they're end of life. And Intel stopped selling the processors 5-6 years ago. Now to Amazon, they're still general purpose compute, and they're about $1,100 a month to use them on their system. So the key is that's every provider is going to have general purpose, what they consider to be memory optimized, what they consider to be store optimized, but none of that's going to mean anything. We're going to talk about what really is going to matter for you now. So let me get past this. And okay, I gave the answer, official answer. Go to the Google website. I pasted the website in. Now, let's talk reality. Let's talk what actually goes into compute and what goes into processor architecture. In order to see that, what I'm going to do is draw out a processor. I'm going to show you where the compute is, and I'm going to show you where the latencies and pain points are going to be in your average server. And when you see that, I think it's going to put you in a better position. And I'll walk you through a server processor and what it looks like, and I'll walk you through a video game processor and what it looks like. So you'll be able to see different hardware is going to be geared towards different things, but it's the way your applications are written and the workloads that they're going to run on matters, not what Google's marketing department calls them or Azure's marketing department calls them or anybody else's marketing department. We got to get specific here. So let's say we go into a server, and in most servers, I think I drew a motherboard for you the other day of what a server looks like, but let me walk you through the processor itself. So a processor is going to look like this, and there'll usually be two in a server, but the processor itself is the brain. It's going to do all the calculations, route the operating systems, handle all your systems calls. And even in an AI environment, the processor is going to be routing the AI destined traffic to the GPUs to do it. So if we look in a processor, the old days we used to have one CPU chip per system. But now on a chip itself, we have something called virtual processors. And what these are actual physical CPU chips themselves. And they sit on this big metal die. So depending upon how many of these you have will determine how much workload you can do if in certain applications. And I'll show you what I mean by this in a second. Let me just draw a few more cores. And this is why you're going to have to figure it out yourself. Now, this server, let's say, has 9 cores or 9 CPU chips in it. Some applications are designed that they can be split and run on all 9 of these at the same time. That is called a multi-threaded application, and multi-threaded applications work very well on a multi-threaded processor. Now, by comparison, there are some applications that can only use a single thread no matter what. So you can have a whole lot of these processors, but only one of them is doing the work and the rest are sitting idle. Now, applications that run on a single processor are going to work on the processor's frequency, how many million calculations or trillion calculations it can do for a second. And what you're going to see, that's going to be considered the clock rate of your CPU, or the frequency. I'll get to this in a minute. Now, you'll also notice that you'll have a number of cores. So your total performance ultimately will be the speed of each core times the number of cores that you have in a system. So all things being equal, and all things are not being equal, but all things being equal, if you have 4 cores and all 4 are running, if you move them to another processor that's the same kind of processor, it'll need 4 cores in the cloud, 4 cores in the data center, 4 cores on the cloud. But what if these 4 cores were from a server that's like 15 years old, and now 1 core has the performance of all those 4 cores? Well, we're going to actually have to take into this. So we have to know exactly what our workload is. Now, on the CPU chip itself, we're going to have something else that I want you to see, and this is also going to affect the CPU's performance. We're going to have some cache RAM over here. And the key with this is I want you to see how fast it is. So the cache is directly on this chip, which means if we store anything in it here, it is going to be brutally fast. Because imagine this happens, and this is typically what happens in a server. Stuff comes in, gets run. Stuff comes in, gets run. But sometimes a lot of the stuff could sit here. And if you could fill this and wait, then 100% of this capacity would be used. You may notice you use a queue in a database for a very similar reason, but that's one of the reasons you're here. Because you've got your system DRAM, which is going to sit on the motherboard. And this isn't a normal x86 type architecture. It's a little different for RISC processors. But what you can see is if the information's in DRAM, it then needs to leave from DRAM across the motherboard to get into the CPU. So the more cache you have and the more stuff you can load in this cache, the more work it can do. So what we're typically looking at is the frequency plus the clock rate. And by that, you'll be able to determine what you need. Your application developer should know, what every time that thread runs, how many CPU cycles it's going to hit. And if not, you're going to have to test it. You're going to have to test it anyway. And then the slow storage on the servers would obviously be the storage, the hard storage, which is why, and just in case you were curious, I'll just call this a hard drive. If a CPU is running low, if the computer is running low on memory, it will start storing memory on the hard drive called virtual memory or swap file so it doesn't run out of memory. Now, when that occurs, the hard drive is relatively slow. So the fastest we can keep it is on the cache. The second fastest we can keep it is in DRAM. And the third fastest we can keep it is on the hard drive, generally speaking. So as we tune this, we can get to better performance. So let's look at various CPUs. So I just went over to CPU Benchmark. It's a great website. You can use it to compare processors. You should notice a couple of things over here. One is, do you notice this is the ranking of the processors in order? Look who makes every last one of these top processors until you get to the Intel Xeon, which is 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16, 17, 18, 19, 20. So the 21st fastest processor is made by Intel. But notice the AMD owns the rest of them. And you may actually notice that a CPU that's $2,900 or $2,800 from AMD actually outperforms the Intel one that's sitting there for, I got to look pretty close, double the price. So if you're wondering why there's a lot of things in data centers that are trending AMD, right now AMD has the fastest processors. Other times in history, it's Intel, back and forth. But just keep that in the back of your mind, what's going on right now. So we have to look at the processor, but then we've got to look inside the processor and its performance capability. There's a couple things I wanted you to notice here. This is a service processor. No, this is basically this multi-thread rating. It's taking each core and combining them all together, and that's the max performance you're going to get out of this. Look very carefully at this. This processor speed is only 2.3 gigahertz, which isn't that fast. But if you notice, it's got 192 cores. That's 192 CPU chips on that main die. That is incredible. Because in a virtualization environment, we could put, if each user was taking 4 cores, that's a whole lot of customers we could put on there. Now you may notice also threads, because what these processors can do is hyperthread, which is they can split their physical cores and logical cores. And when you get a virtual machine on the cloud, I will show you what that means in a minute. Now look at this instruction. Look at this cache over here. When you get to that level 3 cache, that is 384 megabytes. That is one of the biggest you will ever see on a chip. So this is the kind of processor where you expect it to be used all the time under extremely heavy load, like a cloud provider who has 50 customers all on a single server. We'll go back to that hyper-threaded thing in a minute, but note, see that single core rating? It's not that high. But if you look at that multi-threaded, this shows you how good this server would do. Like if it had a bunch of virtual machines on it, it is huge. Now, let's take that to the video game processor. This Intel Core Ultra 9 28985K on paper has some incredible specs. Look at this. It's very different. Now, if we look at the specs over here, we note that single core performance, 5097. Remember that server processor was 3210? And then when we get the multi-threaded performance, this thing is 67.8, where that other thing was 130, was actually more than that. It was 166. So that AMD processor had the ability to handle at least 2 times the workloads, maybe 3. But this computer, because video editing and video gaming is more single-threaded, video games will play better on this system, where a data center would do better on a processor like this. Now, let's talk about the difference between the real cores you get in the cloud, in the data center, versus the virtual cores you get in a cloud provider, because they're not necessarily the same. So let's go to our processor and let's create one more slide so you understand how these work, because this is how you're going to size them. So let's say this is a core. And let's say we have 192 of them in here. Now, the way this hyper-threading concept works is, if I send a thread to a single core, the core can do nothing else until the thread runs through. I'm going to say that again. So if this is a little nothing workload, and that little nothing workload tries to go here, it's going to keep it as busy if it was a big, heavy number crunch workload in certain cases. Not always. Now, this core sending that thread through might only be 5 or 10% of its capacity, or 50% of its capacity. So what this core can then do is it can virtualize itself, and it can turn it into 2 virtual cores. And it can split the load in half. So it'll take one big load. You see what this looks like? And it'll chop the load into 2 small loads if the application's written this way. And then the 2 small loads will go faster than the one big load did. That's the concept of hyper-threading. So I want you to understand this. This whole thing is these 2 halves equal this whole thing. So if you have 4 physical cores in the data center, you actually have 8 virtual cores. And if you only get 4 virtual cores on the cloud, it might not work. So you're going to have to calculate that, size that, test that, and figure that out. So just keep that in the back of your mind, because if each one of these is 50%, yeah, this is great. But what if this core is used at 100%? The last thing you need to consider in all environments, all cloud and all internet service environments is, let's say we've got 392 cores, physical cores on here. That can give us 784 logical cores. Generally speaking, not always. What an internet service provider would do, or somebody else, is maybe they'd sell 1,000 cores on the server that says 768 or more. And it works on the assumption that not every single user will be using all of their capacity at the same time so they can oversell things. Your internet service providers do it. Everybody does it as well. So I'm not saying any cloud provider does or doesn't. Just keep that in the back of your mind. When you don't own the infrastructure, these are the things that occur. So that's why I wanted to give you the answer. The marketing answer is this. Go to that Google page and always go to the Amazon page and always go to the Azure page. And here's why: they're going to consistently change what their marketing terms are as new processors come out. But at the end of the day, I want you to know that you need to understand the processor and understand the sizing and understand what's going to fit and not take any marketing numbers seriously. So I hope I answered that question. And unless any other questions came in, I'm going to let you know that we've got a lecture now for about an hour, and then we've got some labs that are going to be some fun. Leo's got about 3 more labs to do, so that's what the plan is for today. Unless somebody asks me a complicated question and it takes a good 10 or 15 minutes to answer it, but I feel like it'll be good for you to answer, and I'm happy to do that too. So let's get back to the content. If you're having a good time, give a like, subscribe to the channel, hit the bell, tell a friend, all those kind of things, and give me a hashtag, Google Professional Cloud Architect.
Now we're going to prepare you for the next section of the Google Professional Cloud Architect exam preparation. And we're going to talk about compute and containers. Now, we introduced them earlier in the training when we talked about things from a high level, and now we're diving deeper. We're still going to give you a refresher on what these are to make sure that you understand them, and then we'll talk about all the Google specifics that are related to these things. So if we look at computing and we look about it for a long period of time, when I started processors, there was one single processor on a computer, and it was in megahertz. And now we're in an environment where we put a processor chip on a computer. And as of the time we're making this, we can put 192 cores on that one single processor chip. And now we could put multiple of these chips in the same server. So it gave us massive compute capacity. And now we're at the point where private data centers, cloud computing environments, they have so much compute. And the performance of this compute is so good. It enabled us to do things that we struggled to do many years before. The technology didn't change, and honestly, it's almost identical to what it was. And in many cases in the data center, we still have more capabilities than what we get in modern cloud computing because it's emulating what we have in the data center. But understand that the power we're getting is really growing. We used to have something we used to call Moore's Law, and that was at about every 2 years, processor speed could double. But we've actually gotten beyond that in many cases, especially with GPU speed. And the point is the processors are getting so fast. The capacity is getting so fast. These servers are getting so big that it enabled us to do things. Networking has gotten so fast that we can host our virtual data center 1,000 miles away. And it's almost as good as the performance as if it was right next to us. So when I started, every company bought servers, they created their data centers, we hired our technical staffs, and we designed our own. And it worked quite fine. At some point, that became fairly expensive to operate, and organizations started to move to cloud providers. In much the same way the cloud provider's business model was, well, you don't create your own power, do you? So why would you run your own data center services too? We can do it better, faster, and cheaper than you could. And early in the beginning of cloud computing, that actually might have been true. What's changed recently is processing power has gotten so fast. And as processing power has gotten so fast, and processing power has come down in price, and storage has come down in price, understand in today's world, it's often substantially cheaper for some workloads back in the data center. Some workloads may still be cheaper in the cloud. And as a cloud architect, you're going to have to analyze that. And you're going to have to analyze what's best for your client. And each individual situation is going to be something different. So keep that in the back of your mind. One thing that cloud providing computing does is it provides a very semi-managed environment where the hardest work, the biggest heavy lifting, is done by the cloud provider. And you're just managing your infrastructure, whatever that may be, depending upon the computing model used. And if we look ahead, cloud computing provides capacity because it's already there. It's already pre-built. So for a startup business that may not have the funding to actually, or to be able to get the financing to invest in a data center, In many cases, the cloud computing pay-as-you-go can work fairly well for startups because they don't know what their needs are and they could just rent them fairly easily. So we're going to be talking about the various offerings in compute and containers with regards to Google. And we'll talk about the offerings as they pertain to pricing and what they should or shouldn't be able to do. So that brings us into Google Compute Engine, which again is nothing more than a virtual machine. Nothing more. So in our data center, we may have a server just like this. That server will typically be running a hypervisor. It could be the free Linux hypervisor that's like KVM. It could be a VMware hypervisor. It could be a Microsoft Server hypervisor. Or it could be the cloud provider's hypervisor. And then typically speaking, that hypervisor will manage the memory. It will manage the CPU, potentially even the storage resources that are sitting in the host server. And what that actually does is it will enable multiple virtual machines to share this underlying infrastructure. So that's typically what we're dealing with a virtual machine. And the key is this is not new. It's the same as it's been forever. And this is the way Compute Engine will the same as AWS EC2, which is the same as an Azure virtual machine or an Oracle virtual machine. Now, the names of these will be different. The way these things are built out between providers might be slightly different, and the names of these will be slightly different when you use their name services. But please understand, the technology is pretty much identical. And for the most part, all data centers have been using this architecture since about 1999. That's when VMware invented the modern hypervisor, and that's when, right around the time organizations started to use server virtualization. So Google Compute Engine is an infrastructure as a service environment. It enables organizations to create a virtual machine on demand, stop that virtual machine on demand, add a virtual machine and have it auto scale out and add capacity. So this is going to be the basis of of servers inside of the cloud. Now we'll talk about managing these things and how you're going to create them. So you can create a virtual machine the way anyone always did it. And you can, we'll talk about, for example, pre-made images that you can get from the cloud and how that works. But it's all going to be exactly like we talked about. But there will be different levels of service, for example. And what I mean by different levels of service is the cloud providers typically have excess compute capacity left over. All of them do. And what they typically do is they offer it out at a lower price. AWS has spot instances. Google has, for example, preemptible instances, which is extra capacity on the cloud. And if you want to use it, you just create a bid. And as long as Amazon accepts the bid, your systems are running on those preemptible systems. And then if somebody else outbids you and say, I'm willing to pay more, your workloads are shut down. So that still might be great for batch jobs or processing things, but other times it would not work. So when we go through things and we talk about the services, understand, we're going to get involved into tenancy, like where the things are and what kind of servers, the offerings, and that's really what this section is going to be about. Understand that Google Compute Engine will be a major core element of computing on the Google Cloud because it's a virtual machine. And while there's a trend towards containers, many things run well on a virtual machine. Our most powerful applications typically run on virtual machines. Our highest security applications typically run on virtual machines because it's harder to do a hypervisor attack than it would be to escape one container to go to another, typically speaking. Not always, but typically. So we have the ability to set up our infrastructure based upon what we need. Now, when we think virtual machines, we have to think of CPU, like, for example, the capacity we need, the frequency of those CPU chips, and the number of cores, that core level performance, and the number of cores we're going to need. We typically think in the amount of DRAM we need, because obviously that's going to be required. We typically think in the amount of storage space we're going to need. We typically have to think of the kind of network performance we need. We need to think about things like, do we compute on the CPU or do we compute on a GPU? Do we use an x86 type architecture like an Intel or AMD, or do we have something that's based on a RISC processor? And do the applications need to be coded that? So we always need to be thinking about this. So there's going to be a lot of these types of environments and compute systems we'll be talking about today. Now, understand that for whatever reason, they decided to call virtual machines instances on the cloud. And an instance is just a single virtual machine. And when you want to create a virtual machine or the instance, if you hear something called the instance creation process, what's going to happen is we'll have to assign a name to the virtual machine, a unique name, which is going to help you identify it later. We'll add any key value labels that we might apply to the instance to help us figure it out. We'll typically have to determine where we want this virtual machine to be, in what region, and in what data center in that region. So we're going to have to determine where we want it to be. If we put all our stuff in the same data center in the same region, and there's a problem with that data center, we lose everything. So we need to think about the implications of these decisions. And then we have to pick the type of machine. And we'll talk about that. So we also want to pick about the project. So we want to associate every virtual machine with the project that it's going to belong to. And of course, we talked about creation of projects before, but you can create and you can manage multiple instances inside of a single project. So let's talk about what the machine type might be configured. So we have to understand that we're using virtualized hardware, which means virtual memory. It means virtual CPU cores. Virtual CPU cores. And why am I highlighting that? When you have a processor, and let's say we're using the newest AMD EPYC processors that have 192 cores, that each one is effectively a CPU chip. But let's look at what can happen on the normal cores versus a virtual core. So a normal core is a single physical core, and a virtual core is almost like a half of a physical core. And I'm going to show you what I mean by that. So in a compute environment, if we have one thread or one thing that needs to happen on the CPU, it has to be run to completion before the next thing needs to be run. So if I have one thing and then something else behind it and it needs to be scheduled, this has to go through before this can go through. Now, what if this single thread that's going through doesn't use 100% of this capacity, and it only takes for the one thing to go through 50%? Boom. 50%, boom. So what happens is 50% of this processor is going to be wasted. So what modern processors do, or most processors, especially server processors, enable us to do, which is where they get the vCore concept, is instead of having 100% go to this thing and it doesn't take it up, and most threads that go to the CPU don't take up 100%, it lets this processor chop itself into two virtual cores, and then it lets each thread be sent over a different virtual core. So in the end, the total compute capacity is not more than one of these, but because if the load isn't big enough, it'll send half the load down one and half the load down the other, which is pretty cool. But understand that if you had a single thread that were to take up 100% of this, you wouldn't be able to still handle the workloads on the second core. So a physical core is actually two virtual cores. So if you had something running on a bare metal server in your data center, and the server was running at 60% capacity on 8 physical cores, it doesn't mean it's still, that means that server has access to 16 virtual cores to actually do its job. So if you move it to just 8 virtual cores on the cloud, it's probably not going to be okay. Now, if it was running on an 8 virtual core in the data center, and these are the same CPU specifications with the same performance, and you're using the same number of virtual CPU cores on the cloud, then you should be okay. So make sure you consider that. It's way beyond the scope of the Google Professional Cloud Architect, but it's pretty important. So I wanted you to understand that. Now, there's going to be machine families, and here's what machine families are. The marketing departments at AWS and Azure and Google have defined things such as general purpose compute or memory optimized compute, which is compute with a lot of memory, or compute optimized. So they've come up with multiple marketing tiers. Now, these are tiers of servers that they, as a cloud provider, feel are good for general compute, or general this, or general that. All the cloud providers use that. And you could use that as information. But I encourage you to dive deeper, to actually look at what the processors actually are. Look at the single core performance of each processor. Look at the multi-core performance you're going to get on that average virtual machine. Because if you're going to take one virtual machine from the data center and you're going to move it to the cloud to another virtual machine, and you don't compare your CPUs, and you go from 8 cores into the data center on a good, strong CPU to 8 cores on the cloud with a weak CPU, you may have some serious performance issues. So just keep that in the back of your mind. For the purposes of the exam, we're going to go over the flavors of what they are. So you should know them because it could be an exam question. In real life, as a cloud architect or a solutions architect, please actually look at the CPUs, the kind of CPUs and the performance of the CPUs before you make an architectural recommendation. Now, we have general purpose, which is considered to be balanced performance across various workloads. Again, not exactly specific. We have memory optimized, which are designed for memory intensive workloads like in-memory databases and caches, for example. We have compute optimized, which are typically designed for heavy-duty compute intensive type tasks. So that's typically what we're thinking about when we talk about these things. Now, how can we manage these virtual machines? Well, there's a couple ways we can do it. We can manage these things directly from the Cloud Console and use a web-based interface. We can use a command line tool to script and automate various things. We can connect to these instances via a REST API and manage instances programmatically via API calls. And of course, we can use SSH or Secure Shell, assuming we have connectivity to these virtual machines. Or with Windows, we can connect via remote desktop protocol. So those are the options, and those are going to be the options you can remote access pretty much any cloud provider's environment. Now, we're going to talk about the instance lifecycle. What is it? So a virtual machine may have lots of times or states. It may be off, it may start, it may run, it may be stopped, and you may delete it from the system. So that's considered the instance lifecycle. And, managing these stages is going to really help keep cloud costs under control. Because if we keep virtual machines running that we're not using, we're going to be paying for them every minute of the day. So let's talk about what they call the marketing department at Google categorizes virtual machines. So we've got the E2 machines. And E2 machines are designed to be low cost. They're designed for day-to-day computing. Common use cases would be things like a web application, a back-end application, a small to medium-sized database, maybe some microservices, maybe some virtual desktops, maybe a good inner development environment. So general basic stuff. Now, Google has the N as in November. So November 2 Delta as N2D, and November 1 machines. And these are designed to balance price to performance. Again, what is that? It's more of a marketing term. So where are these systems geared? Well, web applications that would be a little higher performance, back-end applications that need greater performance, medium to large databases, a little bit of caching, and some media streaming. So that's your November 2 series and your November 1 series. Now, they also have the M series. M is in Mike, and I'm using the phonetic alphabet, not my name. So Mike 1 and Mike 2 machines. Now, these are designed for memory-intensive workloads. Now, these are going to give you a lot of memory per core. And these can get fairly high DRAM, upwards of 12 terabytes of DRAM. So if you think about where you would need a high memory server, it'd be things like a large in-memory database. You might think of SAP or HANA or Redis, some kind of big, heavy in-memory database, cache, or some form of in-memory analytics as well. Now, we next get to compute optimized machines. And realistically speaking, these are designed to have better compute performance, compute intensive workloads. These are usually on Intel scalable processors. Typically now they're probably on something different beyond that. They give you some really high performance computing. I didn't see any mention of AMD EPYC server processors at the time we talked about this, but understand they could probably be here now, and these types of compute optimized machines may change over time. And now let's talk about some of the memory optimized machine types. And these are shared core machine types. And here we're going to talk about focusing on cost efficiency by actually sharing physical cores. So in this case, we're talking about very kind of small things where we're trying to share a core between other things. So what you basically have here is the E2 micro and the E2 small and the E2 medium. So Echo 2 micro, Echo 2 small, Echo 2 medium if you use the phonetic alphabet like I do to avoid errors. And you've got 2 virtual CPUs for a little tiny period of time if you need it, like a little burst, like you need a little bit of compute performance for a couple of seconds, that kind of thing. But for most of the time, they're very small. So these are for running some little mini non-resource intensive workload, because it's often, for many applications, we need a lot of cores. And this is sharing a core with other stuff, so it's going to be really type small. So let's talk about preemptible virtual machines. So what is a preemptible virtual machine? Now, this is going to be the lowest cost virtual machine we have access to in the Google Cloud. And it's designed for, things that don't require high availability, that can require starting and stopping at a moment's notice. So imagine you had something that just needed a pool of servers to do a lot of compute calculations for a very short period of time. This is perfect for these preemptible machines. You have a batch job, you launch an infrastructure as code script, you open up 10,000 virtual machines, they do their compute for a couple of hours, and you close it all down, for example. And that way you're getting very low-cost compute. So a big batch job, and I may have exaggerated how big, and it might actually need to be that big. It's also for something that might be a non-critical. So you may have something that doesn't need to run continuously and it doesn't need an uptime guarantee. That would be a preemptible virtual machine. The key to remember here is these things can be terminated immediately on you at any time if someone chooses to bid higher than you. So bulk compute capacity, cheap when you need it, but you can't use it for anything too important. And understand they're not covered by any service level agreement. And by doing so, Google can offer these things very inexpensively too. Think about it. These systems can be shut down. You have no service level agreement. You can't offer any availability levels with those. So short-term, non-critical workloads. Let's talk about a shared shielded virtual machine. And a shielded virtual machine is a virtual machine designed to enhance your security by ensuring that the virtual machine images are actually what they're supposed to be. They've maintained their integrity and they don't have any kernel level malware or rootkits. So if you've got a sensitive workload, a shielded virtual machine can really help you here. And these are going to be ideal for sensitive workloads. They're going to be great for companies that need strict compliance requirements. And what it's going to do is it's going to do a secure boot. And it's going to ensure that the virtual machine boots up with only the trusted software. It's going to basically provide a virtual trusted platform module like you might have on a server or a workstation that's going to give you that hardware-based security function and ensure that virtual machine is the same as that it was last time or what it's supposed to be. So this gives us integrity monitoring of the system. It'll monitor the system and it'll detect us or alert if anything were to occur, like tampering. We also have the concept of confidential virtual machines. So this is really cool because it's actually keeping all the information encrypted the entire compute lifecycle. So normally speaking, you can have everything confidential, and then by the time you open it up in memory in the CPU, you unencrypt it. The CPU can do a thing, and then it gets re-encrypted again. So that's what we normally do. But what if you could keep it encrypted the entire time? Because while your system is in DRAM or processor, what if somebody else, a hacker, could get it and steal that data? That's always the concern. So in a really secure environment, you use confidential servers that actually have this kind of, they call it confidential computing. In this case, it's called confidential virtual machines. And this technology pretty much encrypts the entire compute process. So a lot more inherent security than traditional computing. And secured encrypted virtualization actually started with the AMD second generation processors. We're at the 5th generation right now. It sorts in-process encryption, so the CPU can natively handle the encryption and decryption of the data in memory without exposing it in plain text, which is really cool from a compute perspective, especially in a server that may have a lot of users on it from different companies. And so it gives us some protection from unauthorized access, even if a memory dump were to occur by a malicious actor, because again, it's encrypted. So use cases, highly sensitive workloads where data protection is really going to be critical, especially in industries with critical security and compliance needs. So let's talk about what a solo-tenant node is, so you completely understand it. So let me first show you what normally would be like in a cloud computing environment. So let's say you get a server in a cloud computing environment, and let's say this is the underlying physical server. Now you're going to note there's going to be virtual machines from a lot of customers on this server. So let's say this is a virtual machine, and let's say this is company's A's virtual machine. And on the same server, you have company B's. You also have company C's. And you also have company D's, which is true in many cases. And you may have company E. Now, depending upon the server and the kind of server, you could have a lot of different companies on this physical server. So some companies cannot handle that risk. Now, the reality is, let's call this, just let me show you what's going on here. So the reality is this is a pretty secure environment, normally speaking, because you can't go from this virtual machine to this virtual machine. It's blocked. You don't really have that access unless you've got IP connectivity to these two. And that would have to be set up in the hypervisor itself and the virtual networking. So generally speaking, one machine shouldn't ever be able to talk to another machine. The only way this can theoretically occur is it's called the virtual machine escape, which would be the concern that you could leave one virtual machine and then walk into another virtual machine and then get into another and steal another company's data. Now, pragmatically, it's near impossible, because what you'd have to do is escape out of this virtual machine somehow, then attack the hypervisor, and then through the hypervisor, typically speaking, get into company B. So it is not a likely attack. But a solo-tenant node basically takes you out of the multi-tenancy where we have multiple companies, and it puts you into the environment where you're basically confirming that this server is mine, and only my virtual machines will be sitting on that server. So that's a dedicated hardware for an organization to put their systems. So the target audience of solo-tenant nodes are obviously people that need high security computing. It's targeted towards those maybe in the public sector or those with highly sensitive workloads, secret formulas for new things, for example, or, a weapons manufacturer or a bank that's dealing with hundreds of millions of customers, people that need real security. Weapons manufacturer might need a different level. It would probably need a different level of security. But you can think of all the businesses that are out there. We could be having oil coming from plane A to plane B, and an attack on an oil could cause a problem. We could have dignitaries going from plane A to point B, and servers could be determining where people are actually going. We could have medical breakthroughs, and we can have pharmaceutical research, $1 billion new blockbuster drugs, which people don't want access to. So there's times in speaking when we really do need this level of security. So that's what this is really designed for, going back to try to get closer to that data center level isolation while still benefiting from the benefits of cloud computing. So that's what we're talking about, a single tenant host versus a multi-tenant host. Now, with a solo tenant host, we actually have hardware isolation because it's just our stuff running on our server. And this kind of isolation can prevent security breaches, potentially speaking. So security sensitive workloads. Also, this might be good for performance sensitive workloads, and here's the reason why. If we need a performance for sensitive workload, we need some understanding of the capacity and utilization of that server. Are all these virtual machines contending for the same virtual resources at the same time? Now, if we basically have control over that server, we can make sure that server is not oversubscribed, that the server has, for example, enough capacity. We have much more control. So high sensitivity, but also performance-oriented customers may be interested in this as well.
Okay, we are back. Leo's back. I'm back for a few short moments to check and see if you have any questions. I know Leo's got a couple of things coming up that he's going to be showing you. Which you want to talk about real quick, Leo?
Yes, we have demonstrations on how to create virtual machines, with startup scripts, and how to create the basic infrastructure for a LAMP stack.
Oh, nice. The Linux, Apache, MySQL, PHP, in case you didn't know, which is a very common way that web applications are set up. So that sounds kind of fun, Leo. So were there any questions? Let me know you're awake. Give me a hashtag Google Professional Cloud Architect, or a hashtag I'm awake, or a hashtag it's Friday, or a hashtag I love cats, dogs, birds, or whatever your favorite animal is. I think it's obvious I'm a little preferential to cats around here, although I had a parrot for many years and I love that bird, and I love dogs too. So anything you want to know, we just want to hear from you. I want to know you're awake and you're having some fun, you're learning something. If you just got here, and you probably didn't, but if you just got here, it's a reminder that we have the first 4 days of this boot camp sitting on our YouTube channel. You can go back and watch the first 4 days. If you just got here, remember, we've got a completely free study guide that's going to help you pass the Google Professional Cloud Architect exam. The study guide's about 550 pages. It's comprehensive. It's based upon the notes that I actually made for this course. So it'll help you prepare for that Google Professional Cloud Architect certification. So good. So I see one hashtag. Are you all awake? Let me know that you're there. And then I'll get back to the content. And actually, it'll be Leo's content, so it'll be extra fun to watch. All right, Chris, let's go back to the content.
Hello. In this lab, I will demonstrate how to create a virtual machine. I will start by visiting this address, cloud.google.com/compute/docs/overview. This is Google documentation about the compute engine or virtual machine. We recommend you read the documentation to learn about the services you are going to use. Here on the left panel, I will select Compute Engine Instances. This page has a lot of explanation about the Compute Engine Instances. Scrolling down to the bottom under the What's Next session, we can find a link to create a Linux instance in Compute Engine. I will click this link, and then it will present a guide for the steps needed to create the Linux virtual machine. It has some basic steps here, like selecting the project. In this case, I only have one project in this account, and I will go straight to the step number 2. Make sure that billing is enabled for your Google Cloud project. You can go to the project console, opening the left side menu and going to billing. And then if you see a message to enable billing, it's because billing is not enabled. If you see a screen like this means your billing is enabled, or billing is enabled in this account. Going back to the steps, since billing is enabled, the step number 3 is to enable the Compute Engine API. I will go back to the console and select from APIs and services, enable APIs and services. Here I can click. If there were any APIs enabled, they would appear here on the bottom. As there are none, I will click the Enable APIs and Services button here. I will type compute. It will show the Compute Engine API. I click it. Here is the Compute Engine API. And now I click the Enable button. You can see that there are tutorials and documentation available for you to learn more. And we also have a documentation tab here. You can visit, read the documentation, and learn more about the virtual machines. The compute engine takes a while to be enabled, so I will accelerate. I will jump to the point where it is already enabled so we can continue from there. Now the compute engine is enabled. Let's go back to the documentation. And the next step would be the first step of creating the virtual machine. So in the Google Cloud Console, go to the Create an Instance page. Let's go back to the console, and from Compute Engine, I select VM Instances. And here I can see the Create Instance button, and also we see recommended documentation about this topic, about creating virtual machines. For each topic you select here on the left, you see different tutorials or guides appear on the right for you to follow and learn more about the Google Cloud. I will click the Create Instance button. Give the instance a name. And choose the region. You should choose the region that is closest to you. So in my case, I live in São Paulo, Brazil. That's the region I will select. And for the zone, regarding the availability zone, I will leave any selected by default. Here in the bottom, you see a table and also different kind of tabs or buttons here to select the different family flavors available for you to use. General purpose, compute optimized, memory optimized, storage optimized, GPUs. For this lab, I will just use general purpose virtual machine. And I will leave any tool selected because it's low cost day-to-day computing. Here you can change the specs of this E2 virtual machine you are trying to create. You can select a medium, a micro, or a small with different amounts of virtual CPUs and RAM memory. I will just leave the E2 medium selected. For each step, based on the configurations you choose, you can see the estimates, the monthly estimate charge for the virtual machine you are about to create. Here on the left side, I will click OS and storage because the default operating system is a Debian GNU Linux. I will change that for Ubuntu version 2404 long-term support, and I will accept the disk and the size for the disk. I will click select. I will not cover all the aspects of creating the virtual machine. You can do that. You can read the documentation and choose the most appropriate settings for your virtual machine. But most of the options you have, they are presented with a default value, and you can change that. But if you don't select anything different from the default will be applied to the virtual machine you are creating. Here, under the networking option, I will allow HTTP and HTTPS traffics just for following the guide here. And I will click Create Virtual Machine. So those are the steps needed to create a virtual machine as the first activity you do in a new Google Cloud project. Things like enabling the API or enabling billing on your account are things you do once on your account or on your project. You will not need to do that for every virtual machine you try to create. Here the virtual machine is being created. Yeah, still. Now the virtual machine is ready. You can see by the green status. You can see some settings, including the internal IP address it was attached to, or that was attached to this virtual machine, and also an external IP address. By default, Google creates all virtual machines with internal and external IP addresses. Therefore, if you want to protect your virtual machine, you need to enable virtual firewall rules to avoid bad actors from the internet accessing your virtual machine. This is basically how you can create a virtual machine. Of course, there are other options you can set and use, but they will change according to the use case you will have for your virtual machines. In this lab, the idea was to demonstrate how to create the virtual machine, and now I will show under these three dots, you have different actions you can execute on our virtual machine. One of them is to stop or shut down the virtual machine. It will lose the external IP address, but the internal IP address, the disk, they remain available while the virtual machine is stopped. So you can start this virtual machine again with the same disk and same internal IP address. If you delete the virtual machine, it will completely delete all the resources that were created when you created the virtual machine. So if you are just learning and after creating this virtual machine, if you want to delete it right away, click the three dots and then click delete. You have other options like creating a group based on this virtual machine and view network details, create new machine image, different actions here. While the virtual machine is on, it is incurring charges. Even if you are in the free trial period, the credits will be consumed from the total. But you can stop the virtual machine when not using. The cost will be only on the disk and IP addresses only when the virtual machine is stopped. If you completely want to stop all charges or credit discount on your account, you should delete the virtual machine. Now, since you have the virtual machine, let's show how you can delete the virtual machine for the sake of this project, this lab. I will just click delete, and the virtual machine is now being deleted, and it will take some seconds for it to be completely removed from the account. Now the virtual machine is completely removed from your system. In this lab, I demonstrated how to create a virtual machine and how to delete a virtual machine you have no use anymore. Thank you for watching.
Hold on. Okay, sorry, we're back. We did a short lab there. We got a couple more short labs that are coming up real quick, but we just wanted to check in and see if anybody needed anything. We'll wait about 30 seconds to see if any questions popped up. If not, we'll roll with the new lab. And then if any questions pop up on there, Leo will be happy to answer them. So, Leo, which is the next one coming?
The next one is how to create the virtual machine and add a startup script. So when the virtual machine boots up, you can install applications, you can configure some services. So how to create a virtual machine with a startup script.
Okay. And what's the one after that, Leo?
After this one, we will have how to create a virtual machine and create the infrastructure for a LAMP stack.
Sounds great. Thank you. Chris, let's roll with the content.
Hello. In this lab, I will demonstrate how to create a virtual machine with a startup script to install applications. I will start here on the page cloud.google.com, and I will use the search bar and enter the term startup script. The first link is using startup scripts on Linux virtual machines. I will click to open this link. Here there is some considerations, some steps before you even begin creating the virtual machine. I will not follow these steps as they are in this guide, but I will do some adaptation. You can learn more by reading this page to learn how to use startup scripts during virtual machine creation. I will switch now to the Google Cloud Console. I'm already on the Compute Engine VM instances page. If you don't know how to reach this page, after you log in, use this top menu and go to Compute Engine and then VM instances. I will click Create Instance. And the first instance, I will create the traditional way using the console and checking the boxes and setting all configurations for this virtual machine. To simplify the steps for this demonstration, I will accept most defaults as they are suggested by the Google Cloud Console. I will go to the Networking tab and check to allow HTTP traffic, and then I will click Create. The only setting I changed was to allow HTTP traffic. All other settings for this virtual machine are the ones recommended by Google Console. The virtual machine is now ready. I will connect to the virtual machine using the SSH client provided by Google Cloud. I need to authorize the SSH connectivity. Now this prompt is from inside the Debian GNU Linux virtual machine. After installing an operating system, the first thing you need to do is to update the packages. So I will enter sudo apt update to update this operating system package. And then after that, I will install the Apache web server, issuing the command sudo apt install Apache 2. It's always recommended to visit the provider documentation, so you should go on the internet and check the Apache web server page to learn more about this web server. I will answer yes to the question if I want to continue with the installation. At this point, the installation of the Apache web server is finished. I can copy the external IP address of my virtual machine and then open a new tab here on the browser and enter http:// and then the external IP address of this virtual machine, and it should show the default Apache web server page. And it says Apache 2 Debian default page. It works. Just to demonstrate how to customize the page, of course, this demonstration will not cover the whole development of a web page, but just to demonstrate how to customize this page, I will bring the SSH window back here, and I will list the contents of a directory on this virtual machine. In this directory var www.html, the only existing file is the index.html file. I will now replace the content of this index.html file, that is what is being displayed here on the web page, with a bare minimum HTML page just to demonstrate the customization options. I will bring the command I have outside in another application and paste here in the command line interface. This command is basically replacing the content of the index.html file with this HTML code. So it has a head in the title, and then it has a body with some text inside. Let's see. And I have got permission denied. I will then rename the index.html file to try to avoid this permission denied problem. Renaming files on Linux is like moving the content of the old file to a new file. So the command is mv as in move, and I will pass the directory the file is located. And the name of the file, which is index.html, and I will pass now the destination for the new file. And I'll add the extension BKP as in backup. So I'm moving the file index.html to the file index.backup. And I cannot move. I need to escalate privileges here to act as an administrator. And I will list the contents of that directory again. Now we only have the index.bkp. And to create the new index.html file, I will open a text editor that is nano, and I will pass the path and then the name of the file I want to edit. the index.html doesn't exist, so the nanotext editor will create this file, and I can now enter the HTML code inside this file. I'll bring this code from the other application and right click to paste inside the file. Now I can use the Control Exit option to exit the file and say, yes, I want to save the modified buffer. I will hit enter to confirm the name of the file to write is the index.html file. If I list the content of that directory again, now we have the index backup and the index.html. Going back to the tab where I'm showing the content of that page, I will refresh the page, and then it says, hello world, this is the landing page of Linux startup script added directly. This was a manual process using the SSH window to install the Apache web server. Let's do this without the manual installation. I will exit this SSH window, and I will now create a new virtual machine, but now I will use the startup script. The same way as I did before, I will accept most defaults. I will go to the networking tab here, allow HTTP traffic, but now I will also go to the advanced tab and use this automation field to enter my startup script. I will get the startup script from the other application here, and I will paste the startup script inside here. Try to increase the size of this window. Here it is. This is the startup script. It identifies that the script is a bash script. It runs the apt update to update the package of the operating system. It runs the apt install Apache 2. The -y here is to do a silent installation, meaning it will not ask if I want to confirm I want to install the application. And then the moving of the index.html file into the index backup file, and then creating the content inside the index.html file. With the startup script ready, I will click Create. Now the virtual machine is being created, and once the operating system is installed and the virtual machine is started, the startup script will be executed to update the system packages, to install the Apache web server, and then customize the index.html file. The virtual machine finished creation. I will copy the external IP address here, open another tab, and enter http:// and the external IP address, and hit enter. It will take a while before the packages are updated and Apache is installed, and then the web page, the default web page, will be shown first. And then after the script updates the index.html file, the customized page will be shown. Here is the default web page, and in some seconds, the customized version will be ready. Here it is. Now I have two virtual machines. One was created using the manual process, or the Apache web server was installed using a manual process, and the second virtual machine, the Apache web server, was installed using a startup script. In this demonstration, I created the virtual machines and demonstrated how to use a startup script to automate the installation of applications in a new virtual machine just created. Thank you for watching and see you in the next lab.
Look, we are back for a very, very short break just to check in with everyone. And then we'll get into the Leo one. You know, in production, on the next time we do this, that might be a good addition. So thank you for the suggestion. Definitely like that. So we'll go back to the new content. Let me know you're awake. If you just got here, maybe give us a like, subscribe if you're learning something, having a good time. And Chris, let's get back to the content. We'll see you soon.
Hello. In this lab, I will demonstrate how to deploy a LAMP stack. LAMP stands for Linux, Apache, MySQL, and PHP. This is a commonly used stack for web development. I will start by using the search functionality and entering the LAMP stack keyword. I will open the first link here, and I am presented the page, what is a LAMP stack? If I scroll down here, there is a very interesting picture here describing the LAMP stack. Here we have the Linux operating system as the basis for the LAMP stack. We have the Apache web server. We have the MySQL database server. And then Google presents a free option for the programming language, PHP, Perl, or Python. We recommend you read this document to learn more about the LAMP stack. To install the LAMP stack, I will open another tab and I will search for Apache web server. I will right-click the first link, which is the httpd.apache.org. I will right-click to open in a new tab because I will search for MySQL. I will right-click the first link to open in a new tab. And I will also search for PHP. And I will open the first link, php.net. Switching to the Apache web server page. I am looking for an installation link or for a link for the installation page. Since there is no link or no direct link for the installation from the documentation section, I will click the version 2.4. That is probably the most updated version. And here from the reference manual section, there is a compiling and installing link, which I'll click to open the compiling and installing page for the Apache web server. Here are the commands for some operating systems like Fedora, CentOS, and Red Hat. And here are the commands for Ubuntu and Debian operating systems. Before I can run the commands, I need to have the virtual machine. So I will create a virtual machine right now. And I will name it the LAMP stack. I will accept most of the defaults, but I will change the image for the operating system from Debian GNU Linux to Ubuntu. And I will choose the version as Ubuntu 24.04 LTS for the x86 platform. And then I click Select. And then I click Create. While the virtual machine is being created, I will open the VPC network firewall page, and I will switch to that page and show that for each project you create, a default VPC network will be created. You can delete this default VPC and create your custom VPC, but for this project I will use the default VPC created. With the default VPC, some firewall rules are created as well. For instance, ICMP for ping, for testing the connectivity with the virtual machines. The internal default allow traffic. This is traffic going from virtual machines to virtual machines inside the same VPC. There is also a firewall rule to allow the RDP protocol and also for the SSH protocol. There is no firewall rule allowing HTTP traffic into the VPC or the virtual machines from this VPC. I will go back to the virtual machines page, and now the virtual machine is ready. I will click SSH to connect to the virtual machine. I will bring this window over here. And I will authorize the SSH connectivity. Now I have a prompt inside the virtual machine. Once you create a virtual machine, you should update the packages in the repository, so you always install the latest package. And from the Apache page, I will copy the command to install the Apache web server in the virtual machine. I will right click to paste the command here and hit enter to execute. It will ask for confirmation if I want to continue. I will hit the Y key in the keyboard and press enter to continue the installation. Once this command is executed, I can copy the other command, which is to start the Apache service. Right click, paste, hit enter to execute. Right now, the Apache web server should be already running. I will issue a command to verify the status of Apache 2. And the Apache web server is loaded, enabled, active, and running. Ideally, this now should be enough to allow me to open a new tab, enter the external IP address of this virtual machine, and get a response from the Apache web server. But as I demonstrated, there is no firewall rule allowing HTTP traffic into the VPC. For this reason, I will go to the firewall policies click Create Firewall Rule, enter a name, allow HTTP, and the network is the default network. The direction of the traffic is ingress or coming into the VPC, and the action on match is to allow the HTTP traffic. The source filter will be IPv4 ranges, and the range will be 0.0.0.0/0, meaning any IPv4 IP address can be able to reach the virtual machine. Here from the protocols and ports section, I will specify the TCP protocol with port 80, reminding everyone that HTTP on port 80 is not a secure protocol. For real-life use cases, prefer using the HTTPS protocol, which is secure, and its port is 443. After setting that, I can click Create to create the firewall rule, and I need to select all instances in the network. This rule will apply for all instances inside the VPC. This is not a secure procedure. There are other rules to make it more secure and restrict the HTTP protocol only to the virtual machines that will need to receive that protocol, and avoid creating rules for all instances inside the network. Once I set that, I can click Create. I am not using any security measures here because this is only a lab demonstration and I don't need to set that. But in a real life scenario, please make sure you take all security measures needed to protect the assets of your organization. Now we have the allow HTTP firewall rule, and I will go back to the virtual machine external IP address tab. And now the Apache web server default page is shown as a response to a request sent in the browser. I will go now to the MySQL web page, and from the documentation, I will search for the installation of MySQL. Here is the installation section, and I will choose the link for using the apt repository. Fresh installation, adding MySQL to the repository. I will not use that. Installing MySQL with apt. I will copy the command here and go back to the virtual machine SSH window. Right click, paste, hit enter to execute. Answer yes for confirmation that I want to continue the installation. Once the installation is finished, I will go back to the MySQL page again. And the next command is to check the status of the MySQL installation. Let's use that command to verify if everything is okay. And MySQL is loaded, enabled, active and running. And the last one is the PHP programming language. From the documentation, view online, I will click English to read the English manual. And for installation and configuration, I believe for Linux, I will use the installation of Linux using Apigee. I believe this is the best. I will use this one to install MySQL, to install PHP with MySQL and curl. I will merge the two commands, including PHP command and libapache and the command line interface as well in that same command. So apt install PHP MySQL, PHP curl, PHP command, libapache toolmod PHP, and PHP command line interface. Could not open the lock file frontend, permission denied. To correct that, I need to escalate the privileges. I will issue the command again and then add the sudo at the beginning of the command to overcome the limitation. It asks for confirmation. I answer yes, I want to continue the installation. While PHP is installing, I will go back to the tab requesting or receiving the response from the virtual machine, and the Apache default path is /var/www/html. And this file, or the file that is generated in this page, is an index.html file. After the installation of PHP, I will remove the original index.html file and create a customized index.html file with a bare minimum content just to show a hello world customized page. Let me go back to the SSH window. PHP ended installing, and I will list the content of that directory /var/www/html. And the content of that directory is the index.html file. I will move to rename a file in Linux is like moving the file to a new named file. Since I am in the home directory, I need to pass the full path for the file so I can execute the command on the file. So I want to move the index.html file, original file, to an index.backup file. If I list the content of the folder again, the content is only the index.bkp file. Now I will execute the Nano, which is a text editor, to create a new index.html file in that directory. And the content which I will add here in this file is HTML. Every HTML file has a header. Hitting tab, I will enter 2 spaces. And every HTML tag needs to be opened and closed. Here is the opening header. Here is the closing header. And in between both tags, I will enter, which is a title for my HTML page. It will show my LAMP stack. After the header comes the body of the HTML file with the corresponding closing tag. And inside the body, I will use an h1 tag with the text "Hello World." And I will follow by a paragraph line with "This is the landing page of my LAMP stack." And this is it. I need to close the HTML tag. And that's it for the minimum HTML file. I will hit Ctrl X to exit the editor. It will ask if I want to save the modify buffer. I answer yes. And it will ask if the file name to write is /var/www/html/index.html. I will press enter to confirm the file to be saved. And I will check the content of that path again. And now we have the index.bkp and the index.html. If I go back to the tab receiving the response from the web page, note that this title will change and the content of the page will also change when the web server sends me the new customized index.html file. Now it shows my LAMP stack, and here, hello world. This is the landing page of my LAMP stack. The objective of this lab is to demonstrate how to deploy, how to install the applications needed to use a LAMP stack to create web pages. I will not demonstrate a full programming or creation of a web page using the MySQL database, using the PHP programming language. Now, for the cleanup, I will bring the SSH window back, and I will enter exit to terminate the SSH connection. And from my virtual machine, I can select it and hit delete to delete the virtual machine. I will click delete to confirm I want to delete the virtual machine. While the virtual machine is being deleted, I can go to the firewall page, select the allow HTTP route, and click delete as well. I need to click delete button to confirm I want to delete the firewall rule. Now the firewall rule was deleted. The virtual machine is still being deleted, but trying to reach the external IP address from the browser tab should not work anymore. The browser is trying, but not receiving any replies from the web server. Now the virtual machine is deleted. In this lab, I demonstrated how to deploy a LAMP stack, a stack using Linux, Apache Web Server, MySQL database, and the PHP programming language. I showed how to access the web server from a browser, receiving the default web page at first, and then customizing the index.html file to show a customized version on the browser. After everything, I cleaned up, I deleted the virtual machine, and also I deleted the firewall rule allowing HTTP traffic into the VPC. Thank you for watching, and see you in the next lab.
Welcome back. We are here. We've got one more video to go today, a technical video, and then a lecture on more on the compute side. And then other than that, we will begin again next Monday, where we have almost a full fun-free week of training for the Google Professional Cloud Architect exam. So we're going to get into another video. If there are any quick questions here, let us know. And if they're not, Leo and I will go back with the next video of the content and see how we do. We're trying to go through this and make sure that we've answered all your questions, make sure everybody's getting a good experience. Leo, thank you for demoing that for everyone. And do you want to talk about some of the labs you have next week going on?
Sure. For next week, we have creating instance templates, manage instance groups. We have how to create a managed instance group from an existing virtual machine. So we have a lot of compute stuff to demonstrate for next week as well.
Okay, fantastic. And I look forward to that. As a reminder, we have a guide to help you pass this. If you just joined and just got notified by YouTube and just walked into this free Professional Cloud Architect Bootcamp, don't worry. You can go back and watch the previous 4 days. We also have a study guide, an extensive study guide to help you prepare for that Google Professional Cloud Architect exam. So click the link, sign up, and then you will get it. And then next week, like every week, we will run a webinar on how to become a cloud architect. Now, if you want to learn about a security architect, AI architect, enterprise architect, network architect, we've been doing this stuff forever, and we're happy to guide you in any of these roles. But we'll talk about the role, what we do, the skills you need, how to bypass HR when you're not hired, how to show that you're ready, how to create the right kind of portfolio, what hiring manager is looking for, and all of it. It's free, and then we'll answer any questions you have. So sign up. It is completely free. So I didn't see any other questions, which is pretty good. So maybe give me a hashtag Google Professional Cloud Architect. We'll have one more video, and then this will be the last one for the day, and then we'll finish the first week's. Congratulations, and then we'll be at the second week's next week. Chris, let's roll with this content.
So now we're going to talk about images and what virtual machine type images actually are in cloud computing. So I first want to describe it so you understand what an image is, and then we'll talk about the types of images. So normally speaking, you may have a hard drive, and if you look at the root of your hard drive, at Windows, it might be C:, or if you're on a Linux machine, it's /root. What you'll note you have is a whole lot of stuff underneath it. So you might have root, and then underneath that you may have users, for example. And then we may have we may have, say, Cindy as a user, and then Cindy may have her home directory. And then Cindy has her photos because she likes to take photos, Cindy photos. And then underneath the photos will be the folders. So that's what a normal hard drive would look like, for example. So what an image is where we take all of this, every single file, everything is copied bit by bit in an exact copy to this little single file called an image. And the key is, the key is this image, we'll call it a VM image. This virtual machine image can now be taken to any virtualization server on the world. So if I have this physical server, for example, and the image is running on this server, but I want to move it to another server, all I have to do is basically take an image and move it. And that's what we're going to see. And that's how easy it would really be as I take my image with me and where I want to go. So the cloud makes it a lot easier for you. So let's say in a hardware environment, we created a virtual machine. The first thing we needed to do when that virtual machine was install an operating system. And then we'd have to install any of the drivers that were necessary, if it were necessary. And then after that, we can install our necessary applications, right? Well, with an image, we can pretty much get pre-made, where all you have to do is click a button, an entire virtual machine where its operating system is going to fully come up for us. And we can go and get an image, for example, that's got the operating system and the application's already stored for us. So it takes out all the heavy work we used to do in the data center when we had to manually install these things. By the way, we can use virtual machine images in any virtualization data center, and that's why most servers have been using server virtualization for decades now, because that ability to just move and create an image seriously reduces overhead. So we'll have lots of images available on the Google Cloud Platform. Images will be available for a wide variety of operating systems, things like Debian or Red Hat Enterprise Linux or Windows Server. Or you may have an image that's already optimized with, say, Microsoft SQL Server even installed. Or you'll be able to get images that have firewall software, typically from a marketplace. So all kinds of cool images. And these are typically designed when you get them that are already hardened, that are usually secure and ready for you to go. So keep that in your mind. And some of them can be automatically receive security updates and other updates to keep these images running well. So in my mind, that's one of the advantages of any kind of competing or virtualization. So how do we get these images? Well, we can create a custom image. A custom image we could create, say, the golden image, which from a policy perspective, we want all virtual machines to use this operating system, all these patches, all this endpoint protection. So we create a golden image, and then anytime a new virtual machine is launched, it follows that image, and now we have less configuration drift in our images, in our virtual machines that are out there. It reduces time. So we can create custom images with custom software, all of our services there, and our configuration is already optimized. We can create that image, and then someone with an infrastructure as code script could launch 10,000 if they wanted in minutes. So that's the key benefit of cloud computing. That speed and agility is just incredible. It's worth extra costs in many cases. So, we have to determine who can manage the image. So we're going to need some degree of access control on the images, because we don't want the wrong people getting access to the images and being able to dissect what our environment looks like. But we need to determine who can deploy it. So we need to control the authorization of who's allowed to deploy an image. We need to store our images, typically speaking, in an image repository, which is a secure environment that is secured where their images are going to be. Some people call it an image factory as well. And we need to validate these images and make sure they haven't changed. Make sure that they're still good. And if we notice a weakness, maybe we need to remediate that image and create a new one that we use for the future. And now let's talk about the kinds of images that are available. We can get public images. And this is going to be an image that's made for us, made for the public in general. You just start it, it reduces the time and necessary for the setup. This is going to give you a secured virtual machine. So all in all, there may be a whole bunch of options that you can choose just to click from Google that'll be available to the public. That's easy. We can also make custom images tailored to the needs of our organization. And this helps us create a more secure, we can remove packages that we don't need, and we can also optimize to any level of security we want if we have the sophistication to do it. And that's the key. Do we have the sophistication to harden these systems? We can determine only the minimal services we want and nothing else, which could be used for an attack factor. So if we've got the right people, custom images can be great. They will offer us better control and compliance of our virtual machines. Now let's look at instance templates so that we can create something called an instance template, which is going to define a machine type, a boot disk image. It'll include some labels and other properties for the virtual machine. It's used to basically for creating virtual machines from pre-existing configurations quickly and consistently. So we have an instance, we make a template, and then it becomes so easy to create new versions of that same thing in the future. That's what we're really talking about. So when we talk about instant templates, it's really going to ensure consistency across multiple deployments, across multiple virtual machines. From a security perspective and a management perspective, we don't want what we call configuration drift. And Mike sets it up this way, Sally sets it up this way, Billy Bob sets it up this way, and Tony sets it up this way. We don't want that. We also want to do things in an efficient manner. People cost money, so if we can do things efficiently, but a pre-made image or pre-made instance makes life really easy. Think about that. Infrastructure as code. We've got pre-made instances, and one infrastructure as code script could launch 10,000 virtual machines. So we have that agility from some of these DevOps practices, some of this infrastructure as code, and then we've got the efficiency of good images. Things are starting to become a lot more efficient. There's much less like things to go wrong. Access control. We can determine where these images are so that only the right people can launch these and make the systems look the way they're supposed to be. And then we can monitor for differences in our configurations. Find configuration drift, find misconfigurations that will open us up to security vulnerabilities. So instant templates really are going to make sense here. And we can also think about that. Now let's talk about instance groups. So what are managed instant groups? Now that's going to be a collection of multiple virtual machines that you can manage as a single entity. So I want to say that again to make sure it makes sense. It's a collection of virtual machines that you can manage as a single entity. Think about this. Let's say you had a whole bunch of these little servers or virtual machines, and then you put them all in this group. And then all you have to do is manage the group. Okay. Remember when we talked about role-based access control, where when Cindy got hired, Cindy was put into the managers group? And then Cindy got all the permissions of the manager, all the systems she could access. Well, there was like various servers. There was like a performance management server she had access to, and an expense report system, if you'll recall, expense reports. And we hired a manager. All managers get the same managers groups and managers permissions, and then they all get access to these applications. It's fairly similar in concept, and we're using to the same thing. We can manage a lot of virtual machines by creating a management group and then just adding their virtual machines to the group, and it makes it so easy to manage a large number. And again, it all goes back to efficiency. We're always looking for efficiency. So when we create a managed group, we can add auto-scaling, which is going to add capacity when needed, and it'll shut those extra machines off when not. We can enable auto healing based on a health check. So I can say we need 3 virtual machines, and one of the virtual machines doesn't respond to a health check, so the load balancer stops sending traffic to it, and we add another virtual machine. All of a sudden, we're still up and operational. We can use these instant groups to deploy against multiple data centers or regions or entire global enterprise if we wanted. You can automatically update these images across without downtime. So we've got a whole lot of great things to use these instant groups. It's already got load balancing to load balance between your virtual machines. So that's called the managed instant group. We also have this concept of an unmanaged instant group, which is going to be a collection of virtual machine instances that you would manage individually. That's why we want to create this managed instant group. So we have to think about what we would use and where we would want to use it. So let's talk about managed group, instant group considerations. We have to make sure that we have a good configuration, because we need to make sure that our configuration is good, because incorrect updates, for example, could trigger endless creations of instances if a health check were to go down. So we need to make sure that the systems are really designed intelligently. So if a health check goes down, we don't just keep creating virtual machines because something else is broken. Imagine the cost of that. These managed instance groups are designed to assist with scalability and availability, which they can, assuming the compute is the limitation. If some other limitation is your problem, then just the virtual machines won't be enough. These managed instance groups are going to be great for workloads that are going to need high availability, because you can make sure that it self-heals and you have enough servers that are actually running, auto-scaling and auto-healing. So this is one of the benefits of cloud computing, is the concept of these kind of easy management and at the same time add capacity. So when we talk about auto-scaling and we talk about the kinds of scaling, let's talk about what the types of scaling. We generally speaking have vertical scaling, which is this. We add capacity. So we're on a server and we need bigger capacity. The server has 64 cores and 2 terabytes of RAM, and that's pretty much evenly utilized and heavily utilized. We go up to 128 cores and 2 terabytes of RAM, DRAM. That is vertical computing or vertical scaling. But guess what? What happens when that one big server fails? You got nothing. So horizontal scaling would say, well, if the 64 core server is not enough, add a second 64 core, or let's start with 32 core servers, and let's normally run 2 32 core servers and add extra when we come out. So that's horizontal scaling. And because the cloud, we can add capacity horizontally and then come in horizontally, it often makes sense. Now, we also have add more web servers, for example. But we also have to think about predictive versus reactive scaling. What if we can use AI to predict when we're going to need more capacity based upon what's going on and add the capacity ahead of time and then shut it down? Versus reactive scaling, which is typically what we use in cloud computing, is CPU hits 85%, add a new server. And the problem with reactive scaling is it's not often fast enough. So the problem is auto-scaling can take 10 minutes, 15 minutes, 20 minutes, depending upon how many things you need to scale out to reach maximum capacity that you need to. But it's usually a little slow. So imagine a company that was a global retailer that all of a sudden needs to send an email to 300 million users of theirs about a sale. Now that could take their computers, and as soon as that email goes out, it could come in with such a vengeance that it almost overwhelms their servers. And with predictive scaling, that could be predicted ahead of time. With reactive scaling, what's going to happen is so many things are going to hit that server. Some people for about 5 or 10 minutes are going to get bad performance until enough server capacity gets there, and some others might be lost. So what businesses typically do is they plan it ahead of time, and they intentionally scale when they know what's going to happen before it occurs. But what if AI could do it for you more dynamically? And that's going to be predictive scaling. And if we really think about how great this auto-scaling concept is, and it's one of the biggest benefits of any kind of cloud computing, so let's just look at this. Imagine we had a global retailer site. And for example, for this website, they really only need, let's say, 2 web servers. And these 2 web servers, they're typically running at 40% each at all times. Let's say this is a load balancer. So if these 2 web servers are normally running at 40% each, and that's everything is fine, even if one of these servers fails, the other server will only be at 80%. Just for argument's sake, let's just keep it there for 1 second. Now, this might be normal. This might be the normal utilization of this website. Now, this is all times throughout the year, except for the holiday season. So let's say in the holiday season, instead of needing 2 of these servers, we need 10 of them. So the way this would normally work in the data center, and obviously this would be multiple data load balancers, what we would have to do is we would have to run 10 all year long to make sure that when we had the big spikes in traffic, we didn't lose orders. And unless we use a cloud, and a private cloud can give us capacity too, we had to pre-build all this stuff out, which meant 90% of the time we were paying the electric, we were paying the fees, we were managing 8 additional servers when we only needed 2. So what the autoscaling really enables is everything is great. These 2 servers are happy. And now all of a sudden we have that big holiday season or that big sale or whatever's biggest for this business. And now all of a sudden we need extra servers. They're adding, they're coming up. And now we've got the same 10 servers. So that's one of the key benefits behind cloud computing is that autoscaling. And that autoscaling works for containers. That autoscaling works for virtual machines. So where do we store our environment? Well, if we're dealing with virtual machine storage, virtual machines store their information in block storage and cloud computing. We can't use the storage in the virtual machine, generally speaking, in the server itself, because what happens if we delete or terminate that instance in most cloud providers, it goes away. So when we have a virtual machine in a cloud computing environment, and we talked about this, or we'll talk about this more, but I know we've already talked about it, but we have our virtual machine, and the virtual machine's hard drive is block storage. Now, we may back up that a virtual machine to object storage, and if we needed 10 servers to share the information at the same time, we would do file storage, but it's always going to be block storage on the cloud, and it's always going to be block storage. So keep that in the back of your mind. So this is what all virtual machines will look like in all cloud computing. If you'll recall that in this particular environment, we've got storage servers that are sitting in here somewhere. And they're connected to the network. These virtual machines are connected to the network, and that's how they use this virtual hard drive that's stored on the storage servers. Now, if this is AWS, they call it elastic block storage. If it's Azure, they call it managed disks. But the marketing people at Google decided to call them persistent disks. So when we talk about block storage in Google, we'll be calling them persistent. And when it comes to storage that's network storage, block storage is going to be the fastest we can get. Please understand that block storage is nowhere close to as fast as the server storage that we're typically dealing with, which means if we're on server storage, we may need to get creative in the cloud to get to similar performance if we needed server level storage, but it's not usually that much of a problem. So we're going to have 2 kinds of block storage. We're going to have something called zone persistent disks. And those virtual disks or those virtual hard drives or those block storage environments are going to be attached to instances or virtual machines in a single zone, a single data center. This is going to give us very good performance and very good reliability for the workloads in that one zone. We also have the concept of a regional persistent disk. And what that's going to do is it's going to replicate this data across 2 data centers. And that way, we've got higher availability of our data. Because our data is redundant to 2 different data centers, and we could always get it from a different data center than the one we're actually in. So zone persistent disks, we can get them as, in a single zone or a single data center or across data centers, the regional persistent disk. When it comes to storage option, generally we have the local SSD, and that is going to be the local drive in the system. It'll typically be NVMe type storage at this point. Now, keep this in mind. This is the highest performance you're going to get. We're to the point where, there's a 19 million IOPS RAID card that you can put in a server itself, and block storage is nothing close to that. So if you have a workload that needs extraordinarily high IOPS, input and output operations per second, which means super low latency, this is the best thing to do. But here's the problem with cloud computing, that the data on this drive, on this virtual drive, is what's called ephemeral. So it is not long-term storage. If you stop that virtual machine, there goes that virtual hard drive. So you must use block storage if you need to be able to save your information after the virtual machine is gone. Let's talk about cloud storage budgets and buckets. And what are they? Object storage. And they, realistically speaking, require cloud storage fused to be configured within the virtual machine's operating system. And what it does is it mounts the cloud storage bucket as the file system. No, virtual machines don't use object storage. So for this to occur, there's a type of a gateway. There's a translation between object storage to make it feel like a block storage hard drive. So this could be used to store large amounts of information, large amounts of unstructured data, backups, and media files. So this is typically where, object storage, where you typically would upload your data, copy your virtual machine images. If for some reason you were looking for a cheaper form of storage, it uses some object storage to a degree, and there's some kind of translation to make it feel like block storage. Typically some form of a storage gateway, and not like an AWS storage gateway, but a gateway is when you translate one media to another media, that type of a gateway. Now, Google also has something called Filestore. And what is it? File storage. So if you had a Linux machine and you created an NFS share on it, the network file system share, that is file storage. On Windows machines, if you shared a folder and created a server message block share, that is file storage. And guess what? On a Linux machine, if you decided to set up a Samba share or a server message block share on a Linux machine, that is still file storage for Windows systems. So we can attach file storage to multiple instances, which means we can put the information in one place, and 50 servers could use the same information with file storage, and that's where we would typically use it. So Filestore is basically NFS for with Google's marketing name on it. It's going to operate just like NFS. So I want to make sure you understand those. File storage in cloud computing is used when we need it in multiple environments. So let's say this is the file storage. And let's say we had a whole bunch of servers that needed access to the same data. Let's say servers. Let's create some servers. And they all needed to access the same information at the same time. This is where we use file storage. So block storage, storage for a single server. File storage, serving information to multiple servers. Filestore is NFS-like, and it is POSIX compatible. Now, let's talk about the OS login. So the OS login is going to simplify SSH access management by linking SSH users in Linux to the respective Google identities and cloud identity. And it's going to centralize the SSH management using Google Cloud IAM to help with some of the management of using SSH to manage some of the machines. With OS login, we've got the benefit of centralized account management. It's going to manage the full life cycle of Linux accounts through Google identities, and it's going to be similar to single sign-on for SSH access. It's going to simplify permissions management because it's going to integrate with Cloud IAM. We've got the benefit of automatic updates and automatic permission updates to make it a lot easier to really manage SSH keys. We can import existing accounts, and we can import these accounts, these Linux accounts, from either on-premise Active Directory or an LDAP type servers, so we can synchronize across our environments. With regards to OS logins, it can help enforce security because an organization's policy can be enabled to enforce the OS login, preventing unauthorized users without those proper Google identity credentials from even accessing a virtual machine via SSH. It's going to help simplify key management. It's going to get rid of the complexity and the risks of manually provisioning and managing SSH keys because they're going to have to manage these keys, especially for privileged users. And if we think about a use case, it's going to be ideal for organizations that really want to manage SSH centrally, especially those kind of organizations that are going to, with existing cloud identity infrastructure, or people that are migrating from their off-premise environment and using a different directory, like one of the Google directories. Okay, we talked about virtual machines. Now let's talk about Google App Engine. And Google App Engine is a platform as a service environment from Google Cloud, which is going to provide a fully managed serverless application. So what does this mean? It means developers can create their code and they can deploy their code directly to the Google Cloud without thinking about the underlying infrastructure. This is called application virtualization. That's all it is. All cloud providers do it. It should sound a whole lot like Elastic Beanstalk with AWS. And it supports, the majority of those coding languages, the usual suspects that all other providers are working with. Now, what's the key? What are the benefits of using Google App Engine? Well, there's nothing to manage, so the developers can focus on building their code and building their applications. They don't need to think about the server. They're not thinking a lot about networking or heavy-duty networking here. Google is managing the platform. They're managing the scaling in and out when it needs, the patching, the monitoring, and it really enables developers to focus on code. And it means you need less teams, less networking people, less security people. You still need them, but you need less of them. Google App Engine tends to scale up and down on demand. It offers built-in memcache service to minimize any kind of database queries and improve performance. So there's a lot that you get with this, but you lose a lot of control with this. So is giving up the control worth it? It depends upon the organization. Some good uses of Google App Engine would be for development teams wanting to build applications and deploy them quickly and not have to manage them. Organizations that don't have a lot of infrastructure people that understand infrastructure well, this could be great for. And, it can make it fairly easy to deploy things and have version control. Applications that are comprised of one or more services often need different runtime configuration and performance settings. We can, deploy lots of things. We just write the code and it's just going to run. So it's so much easier. Different versions of code, different environments is needed. So traffic can be routed to various versions as needed. So you've got some good control over deployments. You might have a current deployment, push it to a new version, maybe 10% of the traffic, see how it worked. If you like it, transfer everybody over to the new version. Now, there's some problems with Google App Engine too. Well, it's proprietary, so this is going to potentially give you some vendor lock-in problems, which could be big. And, in a world where 98% of organizations are multi-cloud, do we want to deal with these vendor lock-in challenges? Possibly not. So it depends what it's there and who's going to use it. It was initially this was a very initially popular, and a lot of organizations really loved this kind of a balance. Especially initially with cloud computing, just create your code and it runs. But sometimes organizations need something where they've got a little more performance or control. And other times this concept of reduced operations could be highly beneficial. So it's all about knowing the organization and what they're trying to achieve. So let's talk about App Engine Flex versus App Engine Standard. App Engine Standard is a sandbox environment with you can basically run times supported programming languages. It is rapidly scaling. It's great for applications that are going to experience sudden spikes in traffic and need that kind of rapid scaling. And it's somewhat cost efficient. You have to pay for what you use when you need it. The applications can scale to 0 when there's no traffic, which is going to cut your cost, and then scale out when you need it. So, the App Engine Standard environment is going to be great for applications that they're used with supported programming language in the standard environment. So there's going to be a lot of use for that. Now let's discuss App Engine Flexible environment. And this is a little different. It's much more enhanced. In this case, the instances are going to run within Docker containers on Google Compute Engine virtual machines. So you're going to have a lot more flexibility here. Now, App Engine Flexible Environment is designed for consistent traffic with gradual scaling. It allows for custom run times and things that would not be supported with regards to App Engine Standard. We have different programming languages here. We get more versatility here. We've got more intelligent traffic routing from cloud to cloud, for example, or cloud to data center with App Engine Flexible Environment. So it's going to be much more robust for the kind of things that we deal with in many cases. So when should you use each? You would use App Engine Standard when your application runs on a supported runtime, when you need rapid autoscaling to handle sudden traffic spikes, and you're looking for a cost-efficient model that'll scale down to zero when it's not in use. When to use App Engine Flexible? Well, when you need custom runtimes or you need to use an unsupported language, when your application has steady traffic or requires gradual scaling, when you need to integrate more closely with the Google Cloud environment or route traffic more intelligently to other cloud providers because you have a multi-cloud architecture. So that's typically when you would use each.
And we are back. Reminding everyone that next week we have more labs. We have labs on creating a custom image, creating instance templates, creating managed instance groups, and we have block storage, object storage as well, creating object storage buckets.
Yeah.
And we will have some pub sub as well next week.
Fantastic. I love it. I think there is one question which I'll answer briefly, and then we can all have an absolute wonderful weekend and have more fun time next week. Rohit, can I give a path for learning to become a cloud architect? Yes, I will give you a document and invite you to a webinar. And is it required to follow a path like a CCNA before joining a cloud program, or start by training for the job you want, the cloud architect program? So here's what it takes to get hired. First, Chris, please drop a link to the How to Become a Cloud Architect ebook so Rohit can download it. Rohit, please come to my How to Become an Architect next week. We can talk. I'll go over the entire role, tell you everything you need to know, and we can ask questions live. Chris will drop that in. But what does it really take to be a cloud architect and get hired? It's not your experience. You have to have the top 25% of your skills out there, meaning you should be in the top 25% of all the cloud architects based upon your training. If you're with us, you will be, because you will stay with us until you're hired, and you have about 1,000 hours of training where everybody else does about 100 or 200. That's why you'll be in the top 25%. You also have to have the right skills, and at least 3/4 of the skills for the architect are actually business skills, not tech skills. But you have to have the business skills and the tech skills. You have to build a real architecture portfolio. Now, that are things that architects actually do. Architectural artifacts, RFP responses, reference type architectures, those types of things that are going to show you as an architect. After you're able to do the job, that's when you do your certifications, because there's people that I've gotten hired, like Jeffrey, who got hired at Kalian, and he never had any certifications, and he never worked in tech in his life, and it was his first tech job. Or Delroy, who got hired by CDW as a security architect without a single certification. So first we train you for skills, because you're hireable with skills, but you won't know anything out of a certification. After we teach you the skills, then you get the certifications. Then we teach you how to optimize your resume. Then you need to, and if you're with us, we'll teach you. But if not, you need to learn how to tune your LinkedIn profile, how to create the right content that gets hits, how to make managers come to you, and how to clean up your social media, because most people have content on their social media that I would look at as a hiring manager and say, I can't hire this person. So you need to know how to remove that. Then you need to know how to go straight to the hiring manager so you don't get blocked by off. And then you need to know how to interview, win the interview, and negotiate a higher salary. Now, we teach all that. Now, what is it, the skills that you need? And why will you not get them out of the CCNA? Well, you need to understand networking. So if you take the CCNA, and I like the CCNA, it is in my list of certifications. The CCA is about systems administration. What is systems administration? How do I configure something? How do I configure it? Now, the reality is, as an architect, you don't configure anything. So what I would tell you is this book, TCP/IP Illustrated, even if it's just volume 1. Now, this will teach you everything you need to understand about the Internet Protocol. For example, if you understand what the Internet Protocol header looks like, then you understand how you could interact with a firewall. You understand how you could traffic shape and traffic police a certain level of traffic, how you could take a certain level of traffic and prioritize it so that it gets through if a worm or a virus is there. You can do all kinds of things if you understand IP. But you won't learn that in the CCNA. You'll learn how to type config T, interface gigabit Ethernet 0/0. You'll learn how to put an IP address on it in no shot. So the CCNA is about systems administration. And the best way I can describe it is, here's what you learn in the CCNA as it pertains to the routing protocol OSPF, how to configure it. So you will learn config T, router OSPF1, for example. You learn how to add a network statement 10.0.0.0. And where you put it in which area, and that's pretty much it. Now, when I interview an architect, Rohit, I say, okay, now I see you put down that you've worked with OSPF. Yes, I've configured OSPF before, like in the CCNA, and I say, great. Could you tell me the type of LSAs that exist in the various areas? And what a type 1 LSA does, what a type 2 LSA does, what a type 3 LSA does, a type 4, a type 5, a type 7, a type 10. And they won't know. So you have to learn networking, but you actually have to learn BGP, which is not covered in the CCNA. You have to understand IP address planning, which we teach you, which is not covered in the CCNA. You have to understand routing architectures, which is not covered in the CCNA. So here's why I want you to do this. I want you to learn the skill. And the best way I can describe it is the certifications will be so silly easy if you have all the skills and have all the knowledge. But if you don't have the knowledge, the certifications will be hard. So Rohit, if we looked at your life, if we look at a cloud architect that on average earns $20,000 a month, if you spend 3 months to pass a CCNA, and then all of a sudden we have to start you from training from zero, it's going to take you another 9 months to train you. But what if we trained you and in 9 months you could just take the CCNA with a week's practice and pass it and be hired by the time you're done getting the certification? So the reason I like this book, and I've mentioned this book twice. So I guess it was about 4 years ago. Now, I've been designing cloud providers for decades. I've been designing clouds for decades. There's not a single thing that I didn't know in cloud computing or data center computing. But you know what I never touched, Rohit? I never touched the Google Cloud. So I bought this great book from Cybex. This Cybex book was basically a Google Cloud vocabulary book. It told me all the Google services and exactly what they were in real world. So then I took my 20 years of knowledge and took the exam 2 days later. The reason I could pass that exam in 2 days is because I knew cloud computing. I knew everything about cloud computing. I knew how to design it, how every system worked. It was just learning Google names. So if you're with us, you're going to have top 25% networking skills and top 25% security skills and top 25% compute skills. And you're going to have all the business skills you need, which will include things like sales skills, communication skills, presentation skills, writing skills, leadership skills, executive presence, the business knowledge you need to drive for transformation. But you'll also have those networking skills, whether they be BGP, IP address planning, switching, when to use NAT, how to select the right kind of wide area networking technology. In the CCNA, they'll teach you how to configure it, but you won't know whether to choose a software-defined WAN or a SASE WAN or an IPsec tunnel or a private line. But when you're done with us in architecture, you'll know that. So understand the CCNA is great. Understand the purpose of certifications are to get an interview. The purpose of developing your skills is to get hired. You can't get hired with the skills, but you can get hired without the certification. So that's why we say certifications last. Train the skills for the job. Be in the top 25%. Build all the skills that are absolutely necessary. Then build your portfolio, because now you're hireable. Then after you're hireable, you worry about brand building things like certifications, which get you an interview but not hired. But you'll get hired from your content that you learn. Then optimize your resume. Then optimize your LinkedIn profile. And then go to the hiring manager and prove to them you win. That's how you do it. And no, you don't need any other tech jobs. Noah's first job was the last job as a social worker, and he became a cloud architect. Vladimir was a 24-year-old in college, first job as a cloud architect. Wallace's first job at JP Morgan Chase was an enterprise architect. Pierre's last job was on a sailboat as a sailboat operator. He was in his 20s, but he's now working at LeaseWeb as a solutions architect. Debbie was doing something outside of tech, but got hired at Credera as a solutions architect. Jermaine was working in landscaping. It doesn't matter. Get the skills. You'll have any job you want. That's the way I train people. And that's the way I recommend you learn. And I'd love to see you in that webinar. And please download that document because it'll list every last skill you need. And I want you to be prepared because I want you to get these great cloud architect jobs, best jobs in the world. All right. Sorry about that. There was a career thing, and we know how I love careers because I like tech careers, and I've been an architect forever. And it's architecture and internal medicine. They're probably the only two things that I know, and they're the two things that I love most. So, Leo, you got all kinds of cool stuff for everybody next week to share. I've got some geekiness, academia, the underlying concepts, and as they pertain to architecture. So we are very excited to see you next week. So maybe give us a like, maybe tell some friends, please watch this over the weekend. Maybe rewatch the last 12 hours over the weekend. Be a top 25% professional because they're always there. The top 25% is always getting hired. The top 25% never gets laid off. And the top 25% can't be replaced by AI. So have a great weekend, learn a little bit, and I can't wait to see you all next week. Welcome back, everyone. Leo and I are back for day 5 of the completely free Google Professional Cloud Architect Bootcamp. Actually, this is day 6 to help you prepare for the Google Professional Cloud Architect certification and the Google Professional Cloud Architect exam. My name's Mike Gibbs. I'm here hosting this session along with Leo Paredes. I'm in South Florida. Leo's in Sao Paulo, Brazil today, and we have a big day outlined for you. So if you just joined us, if you just heard out about it, don't worry. I want to let you know that you can go back and work the previous 5 days. Chris from my team is going to give you the playlist for all those videos so you can catch up. You can attend today and then go back for the rest. If you just joined us, I want to let you know that we have a study guide, this nice 550-page study guide my team wrote to help you pass the exam to go along with this boot camp. And sign up. It'll be emailed to you within 10 to 15 minutes, and you can use that to follow along to prepare for the Google Professional Cloud Architect certification and to use it as a guide. So please download that. I also want to remind you that this Thursday, like every Thursday, we will have a how to get your first cloud architect job. We will talk about the system that I created 25 years ago, which is what you need to use when you get your first tech job. I've gotten people hired at Apple, Amazon, Cisco, Google, IBM, Accenture, Deloitte, KPMG, Capgemini, PricewaterhouseCoopers, Barclays Bank, JP Morgan, Chase Bank, any company you can think of, honestly. We'll talk about what it takes to get hired, what the skills that you need to be an architect, how you stand out, how you get interviews, how you bypass HR, and everything you need to do to get your first cloud architect job. It's free. We'll talk for about 30, 45 minutes, and then we'll answer any questions. You want to see if you're ready and you want a mini cloud architect interview? I'll tell you whether you're ready or not right then and there. Want to validate your skills? I'll validate your skills. Want me to check your LinkedIn profile and see if it looks like an architect versus an engineer? I'm happy to do it, and it's all free on this once-a-week webinar. This week, we'll do it at 11 a.m., 11 a.m. because we have the boot camp. So sign up. Chris from my team will drop that link. And then let's start thinking about passing this Google Professional Cloud Architect exam. So the flow today is going to be as follows. We're going to talk about compute and containers for about 45 minutes. Then Leo's got about 5 labs that we're going to go through. And Leo can tell you what they are in a minute. Then we're going to talk a little bit about storage. So this is going to be a fun day. Leo, you want to talk to people about the 5 labs that you have that are coming after the first lecture and what they're going to be?
Sure, Mike. We have labs demonstrations about creating custom image to boot virtual machines, how to create instance templates, how to create instance templates from existing virtual machines, how to create managed instance groups, and how to use autoscaling when using managed instance groups.
So that sounds fun, Leo. Okay, so I want to know that you're awake, you're alert, you're oriented, that you're going to be here and be present. So do 2 things for me. Please tell me where you're at with your ad in the chat box. I am in Port St. Lucie, Florida right now. Tell me where you're at. And then once I know where you're at, give me a hashtag Google Professional Cloud Architect, because that way I know what you're here for. I know what you're thinking, and I know everybody is awake. As soon as we see a few of those come in, we will begin with the content because we've got a very eventful today and a week for you. So Hector, you're in New York. I love that. Adrian, Google Professional Cloud Architect. I love it. Well communicated, Adrian. Thank you. San Jose, T-Folio. I used to fly out to Tasman Drive almost every week. Little Rock, Arkansas. I've actually never been there, but always wanted to. Middleton, New York. I've spent a lot of time with. A lot of time out there. Louisiana, I've actually spent a lot. How close is that to New Orleans? I've spent a lot of time in New Orleans. Cisco Live used to be there all the time. Lots of time in that area. Chicago, Darnell, I used to go out there all the time. Loved the Equinox. I think it was not Miracle Mile. It was a really great gym for me to work out because I like to work out. Ahmed's over there in Kingdom of Saudi Arabia. I haven't been there in a while, but I used to spend a lot of time in that part of the world. Always loved it. Spent great time in Saudi Arabia, great time in Dubai, lots of great times over there. All right. Well, Chris, it looks like people here are awake, they're alert and oriented. We'll go with the first lecture. And then after, though, and Chris picked it up exactly. I am not great with French words, so I intentionally tried to skew right over that one. Apologies. He is absolutely right, Chris, on that one. Now, if it's Greek, now we know we're talking another language. That makes sense to me. All right, Chris, let's roll with the content.
Okay, let's talk about containers. So we're going to begin with what is a container. A container is going to be a standardized unit of software packaging that basically is going to be the application and its dependencies. And the key with a container is it contains everything that's needed to run, except the underlying operating system components. So containers are very portable. So imagine taking a box, putting something into it, and shipping it somewhere else. That's the way I view the container, is we're putting the application, we're putting its dependencies in a single self-contained environment, and then we can move that anywhere we want. So that's going to be the container. And I'm going to show you in a document and a diagram I made in a minute to try to help make it easier. But that's what we're really talking about. Packaging up the application and its dependencies and then shipping it off to go run on another server that's designed to run containers. Now, when it comes to containers, there's two parts of it. There's the orchestration of it, which is the control plane that determines how many containers are running and things like that. And then there is the data plane, which is where the work is done. So let's talk about how this works together. So in a traditional architecture, and this would work, by the way, in any data center or any cloud, we typically have we have a control plane. And this exists for everything. We have a control plane for the network, typically the routing protocols. In a software-defined networking, we've got separation between where the routers, the forwarding capabilities, and the control plane, which is somewhere else. And the control plane is going to determine the number of containers. Now, the containers have to work somewhere. So no matter what you hear, containers are always going to be running on a server. Now, either they're going to be running on a provider's environment that's going to look like I show you, or this is going to be your own environment. It doesn't matter. It's all going to be used on something like this. And the way this is going to work is we typically have our servers, and we typically put containers on virtual machines. We could also put them in the bare metal server itself. So it could go either way, but typically virtual machines are pretty easy to manage. So we might have a server, we might smack a hypervisor on it, we might create a giant virtual machine with a whole bunch of CPU cores and a whole bunch of DRAM. And then we may install a container runtime module on it like Docker that enables the containers to run. And then we will have these little things called the container. Now, the reason I'm moving this thing around is this thing is portable. So if I have an application that's designed to run for Linux, this virtual machine is already Linux, so I already have that Linux kernel here, and whatever is necessary from the operating system for this container to use. And now what I have here is I've got my application, which is the code the developer wrote, and the dependencies or whatever that application needs. Any operating system libraries I need, I'm borrowing it directly from this container, from this virtual machine. And this container runtime module is like a hypervisor for an operating system, which logically isolates this virtual machine versus this virtual machine, where this hypervisor here is isolating virtual machine from virtual machine on that same physical server. The container runtime is really what's helping you isolate these containers from each other and allowing them to run separately in a secure, isolated environment. Containers will run off of container images, which will be considered a read-only snapshot that will define the environment that the container is used. Kubernetes can handle all of this now, but you often see this environment of Kubernetes doing the control plane and Docker being the container runtime module. So let's talk about Kubernetes. So we, realistically speaking, have two options. Option one, we manage our entire Kubernetes cluster. Now, if we're going to be in 3 clouds, we probably need some type of Kubernetes that we can have a control plane in all 3 clouds. And that way, if a single cloud fails, we don't have a problem. For example, we're going to talk about the Google Kubernetes engine. It is a wonderful, excellent Kubernetes engine. It's terrific. It's managed Kubernetes. And Kubernetes is great. And Google, kind of invented Kubernetes. So this is a strength of theirs, right? Here's the challenge. If our control plane is only in Google and Google were to have a catastrophic outage, we have no control plane running, say, our data center in the Azure cloud or the AWS cloud. So we may want to look towards something like an IBM OpenShift, which is a managed environment that we could put servers across clouds or that kind of environment, or a Kubernetes environment across clouds. But if we're not multi-cloud and we don't plan on being anywhere in the near future, we can use the Google Kubernetes engine. And that is going to be a fully managed Kubernetes service that will automate the deployment, scaling, and management of Kubernetes applications. So instead of managing your own Kubernetes cluster, the hard work is done for you by the cloud provider. So we can use this with self-managed clusters, where users are managing the underlying nodes, or in an autopilot node where basically Google Kubernetes engine is managing the infrastructure. Because it's made by Google, it's going to integrate beautifully in the Google Cloud with things like cloud monitoring, cloud logging, and even cloud storage for observability and storage. So kind of keep that in the back of your mind. Whenever we go with a cloud provider's thing, they integrate so smoothly with that same cloud provider. Now, there's basically 2 modes that we can use with regards to the Google Kubernetes engine. There is the standard mode where the users manage their Kubernetes modes, and that gives them full control over configuration and scaling. And then, of course, there's this autopilot mode where Google Kubernetes engine takes over the infrastructure management. And that enables users to focus more on their containers and their containerized applications on their code and less on the Kubernetes infrastructure and the infrastructure in general. So for organizations that don't have critical, significant performance needs and need great control, then autopilot could be convenient if this is an appropriate solution for you in your environment. So why might we use containers? Well, containers are elegant for a lot of reasons. We talked about the virtual machine versus the container environment before. And we talked about how each virtual machine, and I'll go back to that if you want, each virtual machine has to have its own operating system. And when we want to create an operating system, it may take, depending upon the operating system, a couple of gigs of DRAM to run the operating system. It could also take a lot of CPU cycles, maybe 10 or 15% of the CPU just to run the operating system. And that means that's a lot of overhead for virtualization. Where if we go to the containerized environment, if we really think about it, all we need to do is run the app and dependencies, and we're only using a single operating system. So these are lightweight. Plus, we've got a container that's got the app and dependencies. It's so easy to move it from one server to another, to move it off the Google Cloud and put it on the Azure Cloud, and off the Azure Cloud and onto the AWS Cloud, and off the AWS Cloud and back into the data center. So containers are great, and they're lightweight, and they're very, so they're being so efficient because they're using the host kernel of the operating system. So that's where the overhead is going. These things can be scaled out easily. Add as many Kubernetes as you want. And this is typically great, and it's typically one of the things we use Kubernetes for. add capacity on demand. So, and containers are usually easy to deploy. We're not dealing with operating systems. We're not dealing with as much stuff. So easier to deploy, faster deployment. It's that lightweight versus heavyweight environment that we're talking about. And if you look at it, I've always looked at there's a couple ways you can look at these situations. We can all look at them differently, but I typically use virtual machines for when we need the maximum performance. In fact, Alonzo from my team drew this chart. I think it'll help. So a virtual machine is heavyweight. And what we're actually dealing with, it's whatever performance is based upon the CPU. We can be the highest performance thing in the world if we've got a lot of CPU cores. We're low if we've got limited cores. Each virtual machine on the server has its own operating system. The virtualization is done in hardware, so it's going to be very, very fast. But the startup time of a virtual machine could be a minute or 2 minutes. And each virtual machine is going to take memory. And it's going to be the most secure because it's really isolated by the hypervisor. When you look at a container, you have to think how light they are and how portable they are. So a lot of containers can give us good performance, but containers themselves typically don't have a lot of performance unless we add a lot of them. All the containers are sharing the same operating system, which means it's potentially less secure than the virtual machine where the hypervisor is providing it. Containers start up fast, less than a second typically, potentially even in milliseconds, and they require less memory space. So it's all about what we're using as it pertains to any architectural option. If we look at the two by comparison and side by side, you can still see that containers offer much greater efficiency, but they don't typically offer the level of security that you would get in a virtual machine or the control that you might have of the virtual machine. Now let's talk about where you could host those virtual machines. Those containers. So, Google has something called Cloud Run. And Cloud Run is something will basically auto scale your containers based upon incoming HTTP type requests. So what Cloud Run will do is it will abstract away the underlying infrastructure manager, giving you a serverless experience. So instead of thinking about provisioning servers and managing servers, the developers just focus on code. But again, you lose control when you focus on code. And when you need maximum performance, you often need maximum control. So it becomes what you're choosing, agility and convenience versus control. Your performance needs will dictate this. Cloud Run for Anthos allows users to run containers on a Kubernetes cluster. So it gives you some additional control of what you're actually dealing with. Cloud Run is typically very good for applications with spiky traffic patterns, such as a web API, where you kind of need that automatic scaling in and scaling out. Now, where do you store these containers and where do you store the container images? Well, you're going to need some form of container registry, a secure environment to secure these servers. And like everybody else, Google actually has a storage environment. So that's called the Google Cloud Registry. They also have Artifact Registry, which is also going to be managed by the Google Cloud for storing and managing container images. So artifact and an architectural artifact is typically a piece of documentation, but there may be other types of artifacts that you deal with, like a piece of code could be considered an artifact to a software developer as well. So there's a concept of an artifact registry. And this is going to be a more advanced version of the Google Container Registry for storing container images. While both of these are going to give you access control and good availability for your container images, Artifact Registry is a place to store your container images, and it's going to integrate much easier into other Google services like Cloud Build for CI/CD pipelines and the Google IAM for fine-grained access control. So it's going to be a comprehensive and secure container management ecosystem because you're going to be dealing with this. It'll help work your CI/CD pipelines. You'll be able to store it in a secure environment. So that is the Google Artifact Registry, and it's going to integrate nicely with other environments. Continue our discussion on containers. Let's talk a little bit more about container orchestration and Kubernetes. So what is Kubernetes? Kubernetes is an open source container orchestration platform. It's used for automated deployment, scaling, and managing containerized applications. It's going to help solve the problem of running containers in a distributed environment. And it provides features like automated rollouts, service discovery, load balancing, and storage orchestration. So the point is, it's the control plane. And as I mentioned, you can build your own Kubernetes cluster, and Google, of course, has their own Google Kubernetes engine. So Google Net Kubernetes engine is going to handle everything from cluster creation to customer upgrades, scaling. So it all goes back to that focus on writing your code, not worrying about infrastructure philosophy. And sometimes that's a great philosophy, and sometimes it's not. So if we talk about the managed Kubernetes solution provided by Google Kubernetes engine, it's going to be there to manage and scale your containers. And it is open source. It is the standard Kubernetes. But I also did talk about what happens if the Google Cloud goes down. Now, if we think about Kubernetes, Google's really has a lot of experience here, probably more experience than anyone else, given the environment of Google, given the developer culture of Google, and it basically being a development company. They needed an environment where they could create a large number of containers and large number of microservices based applications because it worked within their culture. Thousands and thousands of developers all creating reusable code patterns that could then be reused in their environments. Kubernetes made total sense, and Microsoft and microservices in many cases architecturally made sense for Google. Sometimes it makes sense for other companies as well, and sometimes it doesn't. But in Google's case, they are experts with Kubernetes. So if you're dealing with a cloud provider's managed Kubernetes background, understand Google has a tremendous amount of experience. If you're there, they have had a lot of experience with their Borg. And Google has some pretty large-scale data centers. So if we think of this Google Kubernetes engine, it is an enterprise-grade Kubernetes environment. And it took the basic open source Kubernetes and it turned it into a very nice managed solution. And it's kind of a hybrid between giving you the control for an infrastructure as a service environment, and yet it's a platform as a service, kind of mixed into one when I think about Google Kubernetes engine, because it gives you the control that you might need of your Kubernetes infrastructure, but you're not really managing that Kubernetes infrastructure and the servers, then typically speaking, in much the same way you would if you did it yourself. So it's going to be smooth and simple and fast and elegant on the Google Cloud. There's no vendor lock-in with this. And let's be fair, we could use the Google Kubernetes engine on Google right now. And years later determine we need something different. Switch to IBM OpenShift, Red Hat OpenShift, and all of our containerized environment is good. We just use a different control plane. So this is good. No vendor lock-in. And again, it could manage our data center too, because it is great. Kubernetes is just what would happen if we only put it in Google and Google were to fail and the other cloud providers were still up. So that's the only time you might think of using something different multi-cloud for those reasons. Now, let's talk about the shared responsibility model with regards to Google Compute, the Google Kubernetes engine. So remember, in cloud computing, you're responsible for your stuff and they're responsible for their stuff. And that changes based upon what the stuff it is. If it's a software as a service application, they're responsible for everything. And pretty much the only control you have is how you use the application and your usernames, passwords, and your IAM stuff for the most part, your permissions. Whereas in certain responsibilities like infrastructure as a service, you have to manage your virtual machines, you have to manage your storage, you have to manage your operating systems, you have to manage much more of your network. So depending upon what's needed, depends upon what you're at. So let's talk about the shared responsibility model with Google Kubernetes. Google manages the infrastructure here. So you don't have to think about managing the virtual machines. Google manages the operating system on Google Kubernetes engine nodes. So basically speaking, that's taken care of for you. So these things are upgraded, patched, and secured for you, so you don't have to think about it. Google updates and maintains the Google Kubernetes distribution, so it's taken care of for you. Google is responsible for the control plane, the master VMs, the API server, Etsy.d, for example, the databases, and it's going to integrate beautifully with other Google services. Well, again, this is a nice service. Just think about it in multi-cloud, but it is a great service. Now, what is the customer going to be responsible in this situation? Node management. So the customer will be responsible for the nodes running the Kubernetes workloads, including any additional software or configuration of these nodes themselves. The workload security. The customers will manage and secure their applications, containers, their IAM configurations, and network settings. Keeping the nodes updated, whether you're using custom images or custom configurations, customers must keep their nodes up to date. And the applications and the environment, the customers are still responsible for the deployment and management of their workloads in the Google Kubernetes environment cluster, the GKE environment. So if we think of the GKE Cluster Architecture, it's going to be the foundational unit of Google Kubernetes Engine. It's the environment where all Kubernetes objects and all workloads are going to be deployed. The Kubernetes cluster, just like standard Kubernetes. Now we're going to have the cluster master. Now this is going to be the core component of the cluster. It's going to be responsible for running all the control plane processes, the primary node or the cloud master. But we'll also have other nodes there in case the primary node were to fail. And we'll always need an odd number of nodes, generally speaking, for this type of control plane. So we'll need a minimum of 3, and that way we can have an election to determine who's going to be the leader, and we need a tiebreaker. So keep that in the back of your mind. Typically speaking, for any kind of control plane of any cloud, you typically need an odd number, 3, 5, 7, 9, that kind of thing. So let's talk about the cloud master. Now that's going to be the core component responsible for the master node. So let's talk about the API server and what it's going to do, which is going to be part of the master node. And that's going to manage the API calls and interactions with the cluster. That's going to be the central hub for communication between the cluster nodes, the controllers, and the system components. So think the master node is responsible for a lot. The API server that manages all the API calls and interactions in the cluster and all the communication. Now we have the scheduler. And the scheduler assigns pods to nodes based upon requirements availability. And the resource controllers manage the state of the cluster, ensuring that the desired state matches what it's supposed to be. So with Google Kubernetes Engine, we've got the K8's API server, and that's going to be the main endpoint for facilitating interactions via things like HTTP or remote procedure calls, that kind of thing, those type of API calls. Now, of course, in any kind of Kubernetes, we're going to have this kubectl, which will be a command line tool that is used to send these API requests. And that's how users can manage these cluster resources, nodes, and system components. A node is going to be where the work is done. The node is the worker node, the data plane. And here is where the containerized applications and workloads are going to be executed. The nodes are like typically running in a compute engine instance, for example. So if you think about it, you've got the control plane. And the control plane is the API server, for the most part, the scheduler and the resource controllers. And that's controlling everything that you're typically dealing with. The node is where the work is actually done, typically a virtual machine. And the pod is going to ultimately be the smallest deployment of in Kubernetes. And that's going to be 1 or 2 containers that you might have running on a node. So I want you to think about it. You've got the node where the work is being done. And then on that, you'll have a pod. And the pod is basically running a container or 2. So I kind of hope that makes sense to you. Now, Google Kubernetes Engine is going to natively interact with everything beautifully on the Google Cloud. Persistent disks, so you could store your container information in block storage, persistent disks, load balancers to distribute your crowd traffic across containers, and cloud monitoring, obviously, to track the health and performance of your cluster and what's going on. So when it comes to configuration and customization and scalability, Google Kubernetes Engine will allow businesses to build highly customizable, scalable, and resilient applications. And what it's doing is abstracting or it's taking away or hiding much of the work for you. It provides cluster level and pod level configurations. So we can tune things on the cluster level, the top of it, the control plane, or we can determine the state and of what we need to do or change things on the virtual machines. For example, with regards to the individual pods, we could create for greater size virtual machines where these pods run. Remember, when it comes to storing information and cloud computing, where does it go? From a virtual machine, it typically goes to block storage. When it comes from a container, it typically goes to block storage. So we can attach persistent disks or block storage to the cluster nodes. And specific pods can be configured to share these kind of storage VMs. So that way we can have data persistence across restarts of our containers. Same reason we have block storage for data persistence across a reboot of a virtual machine. These two things should sound a lot alike because in many cases they're going to be. Now, when it comes to Google Kubernetes Engine, we have something called stateful sets. And they're used for deploying stateful applications that require persistent storage. So stateful set provides identities and stable host names that you're going to be using. So stateful sets are going to be useful for applications that require consistent storage. We have the concept of the horizontal pod autoscaler, and that will automatically adjust the number of pods in response to changing demand. So this way, if we need more, we can add more. Now we also have the vertical pod autoscaler. So let's say our things are set to a limited number of resources, and we need more. The pods can be coming out using more resources as well. So it adjusts the CPU and memory resources, which is incredibly great and convenient. So we can dynamically scale the containers up vertically as well as horizontally. So a lot of power here. Let's talk about how we could upgrade the nodes, like upgrade these environments where these containers are at and where the systems are actually running. Well, we can do what's called rolling node update. And we could do rolling node updates in Google Kubernetes environment where you can control the disruption level your workloads are using. And there's these commands like max surge and max unavailable. So the point is, how are you going to update them? Going to do a rolling update would be one opportunity. You can also do what's called the max surge. And that's going to determine how many additional nodes you can add during an upgrade. So why might you do this? Let's say you've got 10 nodes that are running right now, and you're upgrading and the performance goes away. With max surge, you can determine how many more you want to do during the upgrade to make sure your performance is okay. So think about that. We can also do that with a command called max unavailable or a configuration, and that's going to set the maximum number of nodes that can be unavailable during an update. So if we think about it, let's say if we need 10 at all times and we're updating a certain one, we need to make sure how many can be unavailable at a certain time. And if not, we're going to make sure a certain number will be. So max surge is how many do you want to add during the upgrade to keep the performance good. And max unavailable is how many can you tolerate not being available at a time. And then we can configure various surges, and different surge configurations will be a combination of max surge and max unavailable. So it'll help you balance the speed of your upgrades and the performance level that you'll have when you do these upgrades. Now let's talk about upgrading nodes a little more. We have to stay reliable at the time, right? So some businesses have 99.999% availability, meaning they can tolerate 5 minutes and 15 seconds of downtime per year and no more. So how do we update these? How important it is to be reliable of the system. So typically speaking, before we're going to make any change, obviously we need to look at it from a change management perspective and think of the impact of the business. But we can also think of how much performance do we need to add during the upgrades so we can tune things and nobody knows about it. So we need to think about when we upgrade, what performance do we need and how do we right size that? And that's where we have the ability to add with max surge, how many additional things do we want open, or max unavailable, how many things can we tolerate being down? And so that's going to give us a lot. Let's talk about auto upgrades. Most organizations don't like auto upgrades. because it's scary, it's terrifying, you don't know what goes on. But using them in conjunction with an optimized surge configuration can make it a lot easier to patch, because we can make sure systems are getting patched, taken offline, and new ones are being launched at the same time to keep it there. Now let's talk about cloud functions. So we talked about containers and what they look like. We talked about virtual machines and what they look like. So let's talk about a function. And a function is a serverless function, but it doesn't mean it's serverless. Typically what a function as a service is, so let's say we have our actual servers here, and they're sitting here. These are just a whole bunch of servers. And the way these functions are, you pretty much upload your code and you go. So the function is uploaded, this function as a service. And what'll happen is this function as a service is going to need compute capacity to run. So we'll have this cloud provider's control plane. So let's call this the cloud control plane. And what happens, that enables you to run a function as a service. So you and thousands of other customers also have functions as a service that they want to be running on the cloud. And there's nothing serverless about it. It's called serverless because you don't have to think about it. So here's what happens. Something happens and your function runs. So your function runs. The control plane determines where it should run. It runs on one of these servers with extra capacity, and the function is done. Now then, the function is gone. Now the next function hits the control plane. It gets scheduled on one of the servers. It runs, and it's then gone. The next function hits the Sole plane. It hits the server, it runs, and then it's gone. The next function hits the server plane, it runs on a server, and then it's gone. So what you can see, there's nothing serverless about this. Now here's the key. All you had to do was upload your code and it goes, and it runs on one of these servers. So what didn't you need to think about? You didn't need to think about CPU cores, DRAM, virtual machine sizing, patching your operating system, endpoint protection on your operating system, because the cloud provider did all that for you. Now, a function as a service could be very cheap, or it could be prohibitively expensive. And I want you to understand when it's going to be cheap and when it will be prohibitively expensive. I'd like you to think of taking an Uber every single day. So you have a choice of renting a car or buying a car or taking an Uber. And Uber is a good service. So let's say you live where I live in Florida. There's not a single thing that's not 10 miles away. And half of the things that I do require me to drive for 45 minutes or more. So if I go to the gym once in the day, which if I were to go to like a strength and conditioning facility near my house, I have one in my house, but let's say I went to the gym and let's say I took my wife out to dinner. Now, if I did that every day of the week, that would be 2 car rides every day of the week. If I used Uber, I might pay $20 for the first 2 car rides and another $20 for the second 2 car rides, which would be $40 a day. Now, if I did that for 30 days in a row, that would be $1,200 a month. Now, is that cheaper? Now there I outsourced all my driving. Now, by comparison, what if I could buy a car that was $400 a month? And that car needed $200 a month gas and $200 a month of insurance. So now to own the car, I'm paying $800 a month. And I can take that car anywhere I want. I can go to my 1-hour drives and not think about the cost of it. So in my case, it would not make sense to use an Uber to go places. It would be cheaper to buy a car. But what if I lived in the city? And what if I could walk everywhere I went and only twice a week I needed to travel? Well, maybe then using the Uber would be so much cheaper than owning a car. Now let's bring that back to functions as a service. If there are things we don't use a lot or we use sporadically, these are one of the most cost-efficient opportunities out there. If by comparison we use it all the time, imagine I needed to take 5-6 rides a day. One was a 1-hour ride to Palm Beach Gardens, which is an hour in both directions, the gym, and I took my wife out. Now, in that case, my Uber bills could be thousands of dollars a month versus, maybe $800 with a car payment. So we have to think of workload. Same thing, if we're going to keep going with these functions that are going all day, every day, it's going to cost a fortune. But if it's sporadic, or if it's event-driven or something like that, this could be one of the greatest tools we have. So understand that a serverless function is not serverless at all. We upload the code and it runs on a server. Where these do well is event-driven architecture. So let me tell you what event-driven is. If this happens, kick something off. So one of the problems we have as people in cloud computing is security of data storage, specifically object storage. Because in the data center, if you set the wrong file permissions, nobody outside the data center could see it in the first place. But in the cloud, your object storage is already connected to the internet. You potentially set the wrong permissions and provide the wrong link, and people on the internet can access your things. So we might use an event-driven architecture for every time somebody puts an object in an object storage bucket. If it sets it to public, we could have a serverless function remediate that and fix the permissions or fix the settings. So keep in the back of your mind, event-driven is when one thing happens, something else. And when we have these architectures that happen in response to something, and they don't happen all the time, we often get much cheaper pricing with this kind of serverless function. Why? The cloud provider, realistically speaking, is an environment where they can just add capacity at any one time. There's typically not a lot of performance guarantees that are associated with these functions. It enables the cloud provider to build a lot of capacity and just run these workloads. So typically very good profitable service if you're looking at the ability to basically aggregate everything and not really anybody needs to know where it's at. And they can be very cost effective if your code doesn't run. Because there's two ways we could do an event-driven architecture. One is we could have a server running at all times to notice if something happens and react. And the other, we could have an event-driven architecture where if something happens, this thing gets kicked off and we only pay for it when we use it and not all the time. So I hope that makes sense. Now, Google Cloud Functions are open source format. So they will run, if you write the code in your data center, they should run on on another cloud provider's if the way you're writing the code is standard code that can run on a cloud provider's environment. Typically speaking, think of a Java or a Python or like a Python, something can run everywhere. And these are used for ETL jobs to kick something off often, or maybe to trigger something and a remediation of something. Maybe you get an alert of something and you want to do something about it, tell somebody about it, send a message. Lots of cool reasons to use these. So cloud functions are going to integrate beautifully with anything Google Cloud because Google Cloud Functions are made by Google. The platform's owned by Google, so it's very easy to integrate with anything. So it'll integrate well with any kind of HTTP request, typically cloud storage, cloud pub sub, cloud Firestore, and even Firebase. And cloud functions will enable automatic forwarding of log entries from cloud logging to a publisher subscriber topic, which could then even trigger a cloud function. So you could have a CPU hit something, you could generate a cloud function, if you will, and notify somebody. So think about these kinds of things. Now, security here is going to be shared because the code's going to be executed on the Google Cloud. And the code execution is going to be under the cloud provider's responsibility because they're going to be managing these servers. It does reduce the operational burden of a lot on the end users. And for the most part with these things, your creativity is the limit with how much you can do for these things. You can have an incident or something and react to it, or an unplanned event and create a trigger. So there's a lot of really incredible things we can deal with these kind of functions on cloud computing environments. Now, it is serverless, which means you don't know where it's running, which means you have no control, but there's also nothing for you to manage. These are typically stateless functions. So each thing that has to happen is typically stateless. So that means we may need multiple things and something to coordinate them. But these are typically stateless containers that don't retain state in between requests. And it's all about Cloud Run is all about abstracting the complexities away from managing different types of containers, different types of virtual machines. All in all, upload your code and it's just running. It uses the open source Knative framework, which is an open source serverless type environment, which is great. And that means we can use it fairly easily with other environments. It's relatively easy to use, straightforward approach. And, you may see it on the exam. You may not see too much of a function, but this kind of environment you'll hear a lot of. Let's talk about API management and some challenges in API management as it pertains to what we're describing here, containers and other things. So creating, managing, and publishing APIs can be relatively complex, especially when we need to maintain consistency on APIs. And application programming interfaces are how one system could talk to another if you're new to this world. And all in all, there needs to be a management platform to manage these APIs. Modern APIs need some way to be able to make sure they're consistent, they're secured, and they're deployed consistently across the enterprise in a policy-based manner. So keep that in the back of your mind. There are platforms like Apigee that have a fully developed suite of tools to handle entire life cycles of APIs. So let's talk about some comparative solutions. While API provides robust, full-featured platforms, there are other solutions like cloud endpoints that may lack some of the features needed to manage APIs. So we need to think about consistency. We need to think about governance. So we need some kind of an API management platform that will help enforce consistency across all API endpoints, because we need governance of our API endpoints or any ways where people are attaching to any of our systems. So we can think about that. So let's talk a little bit about Apigee. Apigee is a full end-to-end API management platform complying with open API standards. It's going to manage the entire API lifecycle across any cloud, multi-cloud, and hybrid cloud environments, which is great because that's the reality of our world. Apigee has been recognized as the leader in API management since about 2020, or at least that's when they first were from Firestore in the Q3. And one of the things we need to think about is it gives us API management. So one of the features is an API proxy. And Apigee can act as an API proxy, presenting backend services as a single managed API to a client. And it'll support modern client-facing REST APIs, even if the backend doesn't support HTTP, microservices, or modernized technologies. So it's going to function as a transition layer, as a proxy. And we talked about other proxies where in a proxy you connect to something and it does something for you. So we can think of Apigee providing that API proxy services, being that proxy to whatever your backend thing is that you're dealing with. Apigee gives us a degree of control and security over our APIs. We can look at things like transaction rate, access controls, and control it. Maybe we don't want to send too many messages to an API because we want to prevent a DDoS attack, for example. And Apigee helps businesses expose their APIs to clients without having to modernize the backend system. So in this case, what we're describing here is modernization without reinvention, because it enables businesses to modernize what they're doing, to update their publicly facing API layer without having to revamp. So Apigee does a great job. You should always keep track and see what other companies are involved, but Apigee does a good job here. Let's talk about cloud endpoints and what they really are. Cloud endpoints are really an API management platform designed to secure, manage, and monitor APIs. So it's going to simplify API management by reducing the need to handle APIs manually in Google Cloud. There'll be a developer portal where cloud endpoints are going to allow the creation of API documentation that will be accessible via the developer portal, and it's going to make it easier for developers to be able to access and interact with the APIs. When it talks about cloud endpoints, let's talk about secure communication protocols. So it supports 3 communication protocols: Open API, gRPC, and Cloud Endpoint Frameworks for App Engine standard environments. Now, in here, the reason people are using these environments is to enable the teams to focus on developing their API, as opposed their interfaces into their system, as opposed to creating custom frameworks to manage these things. It's about standardization and simplicity. So let's talk about a little tiny bit about API security, just a touch, not enough that you would cover, for example, in a security program. But let's think about some API security considerations. APIs, your programming interfaces, expose application logic or business logic and potentially sensitive data by the way they're designed, because they're going to be enabling one system to connect to another. So because of this, APIs are good targets for attackers. So we want to think about tools like Apigee and Cloud Endpoints that can prevent flaws by default or offer configuration management. And of course, we're going to need to think about how do we protect these APIs with, say, IAM, packet filtering, firewalling type options, and many other things as well. Now, we need to classify our APIs. So when we manage them, there's going to be different API security that's going to need for things that are publicly facing, meaning facing the internet, that are being internal for internal uses versus partner facing or third-party providers. And typically we will need lots of ways to do this. We typically want to put an API in a demilitarized zone, a special security segment that would be segmented if it's going to go to somebody externally. So we have to think about API security the entire time. One of the things we may do with APIs and network security is we don't want stuff coming at us too fast. What if somebody tried to create a distributed denial of service attack and overwhelm something? So we might rate limit it. So for example, in network security, if we've got traffic that doesn't feel like normal traffic, we might limit it to 10% of the link or just drop it periodically. Now we still want to do the same thing. We want to rate limit the API things. What if hackers tried to DDoS it by sending 1 million requests? Well, if we rate limit it to something that we know our systems can handle, those requests won't even hit the API to actually damage the API in the first place. We have to be very careful on our APIs that we don't expose any unnecessary data. So we need to filter any unnecessary data long before displaying an API to an end user or a third party. When it comes to configuration and monitoring, we need to use consistent configurations and constantly monitor our APIs for any kind of security misconfiguration. We should think about things like input validation. We need to validate the inputs that are going to go into the API to make sure that we don't allow for things like an SQL injection, for example, or the input of malicious code. We probably want to use what's called IP whitelisting. So whatever you're going to do is you're going to determine which IP addresses need to access to it, and you'll whitelist those. And at least those will be the ones that get through. We typically may want to use load balancing to place APIs behind like a application load balancer, in certain cases to load balance between them for scalability purposes. And we need to be able to authenticate anyone that's interacting to the API. So we need to start thinking heavily about our IAM mechanisms, specifically the mechanisms of authenticating one system to another system.
Okay, we are back. And as it turned out, Chris did a poll in the audience and saw if anybody wanted to play more, learn more about virtual machines and containers. So the answer was an overwhelming yes. So I decided I was going to start to put together a little demo, and then I was going to walk you through a whiteboard and a demo at the absolute same time. So let me walk you through the virtual machine architecture, and then we're going to go build one. And then we're going to talk about the interplay of virtual machines and containers. If you want, we can talk about secure operating systems versus standard operating systems and the way they're actually containerized. And we'll look at how these play together. So let's go back. I want to just do a quick whiteboard as a reminder of what we're dealing with. And then I want to take you to a real server, and I'm going to take you to the real hypervisor. I'm going to walk you through. Then I'm going to show you how in the data center virtualization has worked for the last, say, 26 years. And when you understand that, you'll know exactly what's going on there. And basically, if you're taking a virtual machine from the data center to the cloud and you don't understand what the virtual machine is in the data center, you're not going to understand it in the cloud. So let's start with that. So let me begin. I'm going to produce a little whiteboard slide over here, and then we're going to go to my hypervisor. In this whiteboard slide, remember I said we start with a physical server in all of these virtual machine environments. Now, this is the server. Now, if we wanted to, and we needed the greatest performance, and bear with me, I've got to adjust my magnification here for you to see everything. But if we wanted to, we could easily install Linux directly on the server or Windows directly on the server and have a giant high performance application. We could. And I've worked on systems where latency is everything, and where we need the maximum performance out of a server, we don't run it in a virtualized environment. We run it directly on the server itself. Now, the majority of the applications out there don't need that level of performance of a single server, so it's not that common. But if you're going to work in banking, for example, or you're going to work in an environment where nanoseconds equal many, many millions of dollars, then you're going to run directly on the server. But let's say this server has 384 physical cores on it and 10 terabytes of DRAM. Chances are that's going to be enough for 50 virtual machines or more. So remember, with all of these environments, we're going to have a hypervisor, and then I'm going to bring you to a real hypervisor in a minute. We're going to walk through that hypervisor itself. It's going to be a hypervisor. And then on that hypervisor, we can create many virtual machines. Virtual machine 1, virtual machine 2, for example. And I want you to think about how cool this actually is in this virtual machine. And I'll show you on the hypervisor. This virtual machine is ultimately a single file, something that could be moved from one server to another physical server at a moment's notice. Cloud provider wants to take your server down, the server that you're sitting on right now, because they need to take it offline for maintenance. They can just move your virtual machines to another server and you stay up. We do the same thing in the data center since this existed, since this was created. Now, this hypervisor was created by VMware in 1999. It is the basis of all hypervisors. Linux offers a few hypervisors, KVM, QEMU, and all cloud providers are using some form of a Linux hypervisor, but it all came from VMware in 1999. It's the same technology. Now, let's extrapolate into one of these virtual machines. We might now create a virtual machine. Now, if we look at this virtual machine itself, what is a virtual machine going to need? It's going to require an operating system, as nothing will function. And then maybe we want to put containers on this virtual machine, and we're going to need to keep the containers separate from each other. Well, then we're going to need a container runtime module. So that we can, and I'll show you that in a second. Then we'll go to the real hypervisor. Now, this container runtime is what's going to be needed to enable containers to run on this system. Now, often you might see the interplay between Kubernetes and Docker. And what's going on is Docker is the runtime module for the containers that say sitting on this Linux server. And meanwhile, you're using Kubernetes as the control plane. So you've got this Kubernetes control plane. And then you have to have at least 3 nodes, because these things have to run an election process to determine who's the lead. And what'll happen is this control plane will then control the containers, whether to scale in, whether to scale out, whether to add containers, whether to remove containers. And meanwhile, these containers are running on side of this server with the container runtime module in an operating system that's sitting on side of typically a virtual machine. So let's go to my actual, and we can go back to this, but let's go back to my environment. I'm going to go to use this. This is great. This is a virtual machine I built a little earlier. I'm going to restart it, and then we're going to build one together. So this is a physical server, a regular server that you would see in a data center, running pretty much the industry standard hypervisor, which is VMware ESXi in some way, shape, or form, typically included with a vSphere package where an enterprise can manage the systems, their global environment. But this is pretty normal. Now, if you look in this environment, which is pretty normal, there's a couple things I want you to see. If you look in this upper right-hand corner, and it's not the easiest thing to see at the current size. Let me see if I can make my browser look a little bigger. to make it easier to see, and I'll zoom in and zoom out as we do this. But if you look carefully at this server, you can look at the CPU. You can see the CPU has a cumulative of 53.6 gigahertz left of capacity, compute capacity. It's got 109 gigs of DRAM left available, and it's got about 700 gigs of storage space. Now you can see that some of the storage space is used. This is for various virtual machines. You can see that some of this memory is used, and that's probably because virtual machines are running. Now, if you look a little carefully, you can see this is it's a Dell workstation, typically with server processors. These are Intel E5 2670 V3s. These are fantastic ones to use. And if you're curious about building a lab, or a lot of businesses, these are considered, even though the processor's end of life, these are typically considered standard compute on a normal cloud provider. These cost about $1,100 a month to rent these servers on a cloud provider, but you can buy them from Amazon for about $400 as refurbished gear. If you ever wanted a lab in your house, just keep that in the back of your mind. And also, it gives you the cost sometimes of comparison between running it on a cloud provider versus running it in your data center. Now, it's end-of-life gear, but just think about all these things. But you'll see is there's 24 CPU cores in here, physical cores. And you'll also see that there's 48 logical cores. Remember when I talked about hyper-threading the other day, and I talked about a processor being able to split its cores? You know what? Just for the fun of it, let me go back to that real quick before we actually get in, and then we'll have some fun with this. But let me just go back to that and make sure. Oops, no, bear with me one second. So if you'll recall, when we went over system architecture, that the chip will have multiple cores on it. For example, if this was a 4-core chip, which really wouldn't belong in any server in today's world, but let's just pretend it was 4 total cores that we have going on here. In this particular environment, what can happen is if the load coming into the core doesn't utilize all of this one core, this physical core can virtualize itself into 2 logical cores. So in a physical world, we get physical cores. When we rent virtual machines and it says 8 cores, these are 8 logical cores, which is 4 physical cores. So keep that in the back of your mind. Now, when we go back to my hypervisor, and now you see that it now has 2 processors with 12 physical cores per processor, which is how you get 24 physical cores. That's how you get the 48 logical cores, which is why I said core performance is not the same in potentially a physical server as it would be a virtualized environment. Now, if we also look through this to get you a feel for what these things look for, here's going to be the process to create a virtual machine on a server. And I want you to see what it is, because whenever I said CPU, when you size a virtual machine, it's about CPU cores, and it's about DRAM and or network performance. Well, this is typically the way it would be created. Now, it would typically be created something like this. I'm going to name the virtual machine. And since I'm a security person, I will do all the things when I name this virtual machine and create the virtual machine you wouldn't do, and to hopefully make you understand the security rationale. First, I would not call the machine Cindy the cat, because everybody knows Mike loves cats. So I would never use the word cat. I would never use the word Cindy. I would never use my pet's name as a password, as a this, as in anything, but just think about that. But instead of calling it this, I was going to call it Cindy the cat, but let's call it Google Bootcamp 2. But I hope that makes sense about why you wouldn't want to do that, because it's too easy to do. Now, then we're going to tell it the kind of operating system we want. We're going to tell it Linux. And then we're going to pick an operating system version, and we're going to tell it Ubuntu. Now, what I'm going to do is walk you through the first part of the setup, and then I'm going to open up a virtual machine I just created so you can see it. And I did that in the last few minutes. So let me move this up, because we're going to have to go back and forth and zoom in and zoom out so you can see it. The next thing that we need to do is we need to say, how much of the resources from the physical server are we going to put in this virtual machine? And we have an option. So let's say it's a Linux machine. Let's say we need 4 physical cores. Let's say the machine is a very small Linux machine. It needs 8 gigabytes of DRAM. Let's say the hard drive for this virtual machine is going to be 20 gigabytes. And then realistically speaking, we would have the ability to specify custom settings for a virtual video card, or we could put a physical GPU into this virtual machine for AI purposes if we wanted, or 8 virtual GPUs into this virtual machine if we wanted, if they were on the system. Now what we need to do is go to the next phase where we need to tell it where it's going to boot from. And I'll pick Ubuntu 22.04 desktop. Looks like a fun thing to install. If I click next on this, you'll be able to see the virtual machine, the cores, the DRAM that it's going to pull. And I want you to notice something. So right now, very carefully, look at the amount that we have. We have 53 gigahertz free. We've got 109 gigahertz free. So let's see what happens when we click next. Now at this point, let me kind of put this in a better spot. Let me show you. So we've now created the virtual machine, so it should be sitting under our virtual machines. And we're going to turn on this virtual machine, but I want you to go back and see this. Note we've now got 54.9 gigahertz capacity, probably because what we were doing before was taking CPU cycles to create that machine. Now let's take this virtual machine, Cindy the cat, or virtual machines. Let's turn on this Google 2 Bootcamp virtual machine, which we just made. And let's first do 2 things. Yes, hold on. We want to install it, but let's go back to the host real quick, just so you can see something. Notice some CPU resources were gone. Now you're going to notice as this virtual machine comes up, it's going to pull more resources from the main server. So we're going to boot this system. We'll install it. Continue. We're not going to do a very sophisticated install here. We're not going to download updates to make it very quick. We're going to do a very minimal installation here. So it doesn't take very long. So we'll erase and install. This is going to be pretty quick. Maybe we'll even work through it. It's going to tell you what the partition table of your drive is. And the key here is when you look at it, I want you to see that it's very similar in the look and feel to what you'd see in real life if you did it on your own notebook. It's exactly the same. It's using a virtual one. So we're going to use the username Cindy. Again, I don't want you to ever do something like this. Now, when it comes to cracking passwords, with 24 RTX 4090s, we can crack an 8-digit password in less than a minute or so. So if you think about that, you probably don't want to use a password. Maybe you want to use a passphrase, which is harder. Maybe you want to use 16 characters, or better yet, use something that's not a password. Because imagine how easy. If I use Cindy, how hard is it to go to social media and find Mike has a cat named Cindy? Or anything that you would know. So please, pick things that are obscure and wild and crazy. I'm going to call it 1, 2, 3, 4, 5, 6, because we know that's not a good idea. 1, 2, 3, 4, 5, 6. And the reason it gave it a fair password is it wasn't smart enough to know how ridiculous of a commonly random password that was. There was a point where the most common password on the internet was Cisco. And I'm not joking, because it was part of a certification exam. So people just put it on the router. So just think about that. Now, give this about a minute, because I didn't ask it to actually update itself. And then you're going to see that it's going to look and feel just like the real thing. And then I'm going to boot up I'm going to show you there's another virtual machine while this thing is doing its thing. I also want you to see that there's other things running on the same thing. For example, here's another virtual machine. We can turn that on and you can see it. Now, this is another Ubuntu server that I had installed while we were on there as a demo in case this was going to take a long time to do. Now, while these two are running, you see that there's two. Now let's go to the host and move it out of the way. And look, wow, we only have 49.5 physical gigahertz free. Now we only have 101. Where do you think that's coming from? It's coming from all the resources of the second virtual machine. But look, I have two servers. The first one has 8 cores, and the other one that we're creating right now has 16 cores. So 8 and 16 is 24 cores, but it's not using 50% of my CPU capacity. Now, these two machines, I want to say it again, these two machines are scheduled to use 14 physical cores from the server. So if this server has basically 48, 14 divided by 48 is about 25%, but note it's only using 10% of the CPU, including to run the hypervisor. And why is that? That is because most virtual machines don't use full capacity at the same time. Now think about this. This virtual machine and this virtual machine are probably only using 8%, even though they could be using 25%. So understand that it is common practice in a service provider to sell possibly more of these virtual machines than they actually have physical capacity for. And it works on the statistical anomalies of not all these virtual machines are using the same capacity. Your internet service providers do it in the way they send their bandwidth, for example. And that's why, like, for example, when COVID happened and we all started working from home, people didn't expect the internet service to be that big and that bad. Okay, so it is actually trying to update it. We'll go back to this and we'll go back to our drawing and we'll come back to this in a minute. So bear with me. Now, if we look in a large-scale virtualization environment, and this is like any other cloud provider, what are they going to have? They're going to have tens of thousands of servers. Also, we'll pretend these are all servers. And when we have this, the cloud provider is going to have their control plane. And then when you create a virtual machine on the control plane, or you click for one to start up, that virtual machine, I desire to open this, hits the control plane, often via an API, and then that provisions the capabilities here. So many of you have interacted with the control plane, well, the part of the control plane. So if you log in and use the management console, the console that's Leo's showing, that application of that console is going to feed into the control plane, and that's going to create that virtual machine on one of these servers. And that control plane is going to create your virtual data center in here. And your virtual data center, again, is just going to be your VPC. So that's your virtual data center. And this is created logically in the memory of the servers. And all this networking that's going on inside your VPC, that is virtualized networking called software-defined networking. Let's see if our virtual machine is finished doing its installation. Okay, it's almost done. It's going to reboot in a couple of seconds, and we should be fairly good here. And then we're going to turn on this virtual machine. And when you see this, now you know exactly what's going on under the hood in the cloud provider's data center. They're going to have an orchestration system, which you're going to interact with, and it's going to make the changes in there. Now, guess what? If you use infrastructure as code, it's going to interact with that same control plane, and it's still going to deploy that virtual environment. And it's all going to happen behind the scenes in an interaction with that control plane. Then that puts it on the servers, which you don't know where they are, with the exception of which data center they are for the most part. And that's one of the things that we're typically talking about. Well, it looks like that thing's going to take another minute. So let's have some fun with one more concept that we can talk about that you can typically do to increase performance, just a drop. And we'll typically talk about the placement of these servers. And you typically have various architectural choices. So let's say I had a system and the requirements of the system were as lowest latency as possible. Maybe this thing is a trading system and the trading system buys and sells options. And if it can buy it a nanosecond before the competition, so there's news that says this is going to go up. If you can buy it before the competitors, you can buy it cheaper. So if we were trying to create an AI-based trading system that's going to trade faster than the traders are, competitive advantage is latency. Now, in a high sensitivity latency environment, we might actually take all the servers, run them on bare metal, not versus a virtual machine, and you can do this in the cloud, and we may place them all on the same rack, all in the same switch. So what we have is incredibly low latency. This would be a rack. So we'd have a server, a server, a server, a server. This is typically the switch or a layer 3 switch. And we'd have all our stuff in the same rack. Now, obviously, this is going to give us the greatest performance in the world. Now, the architectural trade-off is if anything component here goes, you lost everything. So typically in these environments, we run 2 of them and we do a few other things to play with it. But just keep that in the back of your mind. Where we place this stuff will also have some degree of performance. You may hear that called placement groups or something like that in your cloud provider. Now, I think we're probably back. I think our virtual machine is most likely going to be finished here. Okay, it looks like it's due in the last possible seconds. We'll reboot it. We'll log into it and you'll see what it is. Now, you can run these on your desktop if you've got a type 2 hypervisor, which is where you'd get like VMware Desktop or the VMware Player or the, I think there's one made by Oracle that's a freeware virtualization thing you can use on your system. If you've got Linux, you've got KVM or QEMU that you could potentially use as well. This happens to be what's used in most data centers, so I thought I would use it. And it looks like it's going to take an additional second or two for this thing to come up. Nothing's ever as fast as you want it to be when you're demoing it in real time. So we will come back to that. But that's really what we're talking about. Now, while it's doing that, let's talk about one set of architectural trade-offs. I did say I would talk about secure operating systems first. So let's talk about that fairly quickly. So what is a secure operating system? Well, or more secure operating systems. Many of them do this. So in a traditional operating system, here's your OS, and your applications all sit on top of the operating system. And they've been doing this forever. I'm sorry, this is an app. Since Pablo brought something up, and this is where certain operating systems actually work that are when you need security. So what you see in a normal environment is this. You've got your operating system and all your applications, and here's where things go wrong. If you can in some way escape one application and get into another application, one system could be hacked along the way. One app goes haywire and uses all the CPU memory and DRAM in the system, it can cause the system to crash. And many, many years ago, we used to see a lot more of that. Now, what some operating systems do is they literally virtualize everything from the scratch. So every application runs in a separate container in a separate memory space. So now if each app is in its own container, like I've shown you here, theoretically, if the app inside one of these containers crashes, it shouldn't go over to the main operating system. That doesn't mean it can't, but it shouldn't. So some of the operating systems actually run all their applications separately in containers. And there are some servers that an operating system you can use to isolate memory space from one to another. But that is way beyond the scope of this. Let's go back and see if our virtual machine came up. And it did. So let's play with this. We'll bring our virtual machine back up. And I'll show you how it's going to look and feel just like any other Linux machine. We should be up in a couple of seconds. Okay, and you're going to see this is going to look a lot like any other Ubuntu Linux desktop that you might ever use in your life. But I do want you to think about one thing. Some companies use these remote desktops where you sit at your house and then you use a remote desktop. And why might they do that? Well, first, you can see this is going to perform relatively well. It's the first time. It might be a little slow. See if it's slower the next time. So these things are going to perform good enough. But if you VPN into their system and then you're using the system that's in the data center and it's not on your desktop, your data in this virtual machine never left my data center. And that way I could just back up my data center. And if you ever run into a problem, I could just create a new virtual machine for you as opposed to totally re-imaging your computing systems. So that's what you can see. This is exactly what you're getting in the cloud provider. It's just that you just select it and it starts, and they've got these things automatically deployed for you. So keep that in the back of your mind, and that's pretty much it. This is exactly the way virtualization works in every data center. You can see where the difference between the virtual machine is where the container would be. And then that brings us back to one last concept to really think about. And that is those trade-offs between the two of them. So if we look at a virtual machine, we have the ability to get the most power. I could put all 384 physical cores in that virtual machine, or 768. I could put 4 terabytes of DRAM in that virtual machine. Now with a container, they're typically small compute power. With my virtual machine, they're pretty segregated from each other. And by pretty segregated, I mean this. Here's my let's go back to here. I'll get rid of some of this stuff. Here's my server. And here's my hypervisor. And let's get this out of the way. In this particular environment, I now have my virtual machines. Now, and most likely, these virtual machines are going to be in a different subnet too. So this virtual machine might be in a different subnet than this one, which is going to make it very hard for them to talk to each other without a router in between them. And you don't have routing in between these. So the only way that you could hack this would be to somehow escape out of the virtual machine that you were in, and somehow from that virtual machine be able to hit this hypervisor over here, and then hack into the hypervisor to be able to escape your virtual machine, and then to escape the virtual machine and enter another system that you'd have to hack into. That is really, really hard to do if your hypervisors are patched and up to date, and that's why cloud computing works. Now, if this is a container, and this is our VM with our OS, and then we've got a container runtime module to make this happen. And then we've got our containers. No, so you got a couple things that could enable this to go wrong. If you hack into the operating system of the system, you might be easier able to escape the operating system into one of these containers. If you hack into the container runtime module, you might be able to get into one of these containers. So theoretically, it would be easier to go from a container to a container than it would be from a virtual machine to a virtual machine. So you have a little more power with the virtual machine. Theoretically, you've got a little more security, but you've got a lot of overhead from all these operating systems. So I hope that little we decided to do something that was fun in the short term, covering some virtual machines. I really hope that helped. If there are other questions, let me know. Otherwise, we've got some really fun labs from Leo on compute to play with. Did everybody get enough of a live whiteboard session from what everybody was asking? So, and Claudia, so APIs could be load balanced in a lot of ways. They could be load balanced with an API gateway. They could be load balanced with a reverse proxy. The key is whenever you're load balancing for several reasons. You're load balancing to increase fault tolerance so you don't have a single point of failure. You're typically load balancing to increase performance. So you could do it either way. Now, if you load balance with a reverse proxy, you might be able to cache certain information as well versus a traditional load balancer. But you can balance APIs any way you want. Lots of ways to do it. The goal is, what do you need to do? Okay, Leo, good to see you back. So Leo, in case people, well, actually, if you're just joining us, as a reminder, we've got the first 5 days of the boot camp. You can go back. My team will drop a link to that in the chat box. If for some reason you just found us on day 6, welcome. In addition to going back to the first thing, we've got a free e-guide that's going to help you prepare for the Google Professional Cloud Architect exam. So sign up for it. My team will drop a link. Leo's now going to get into, I think, about 5 different labs. I know we talked about, for new viewers, Leo, what are your labs about?
Well, now we have demonstrations about how to create a custom virtual machine image.
Good.
And how to create instance templates to standardize how to create many virtual machines practically equal to each other. And we will use those instance templates to create managed instance groups. And once we have groups, we can use Autoscaling to cope with variable amount of requests. So those are the demonstrations we will see now.
Sounds fun. So give me a hashtag Google Professional Cloud Architect Leo's Labs. And in production, I'll ask that question, explain container runtime module. So let's say you wanted to run a container on a server. It has to run in something. You have to have something that separates my containers from your containers, and that's the container runtime module. So if you think about it, what is it that the containers actually need from the underlying operating system to run? They're leveraging the kernel of the underlying operating system. They're leveraging various packages of, say, the underlying operating system. But if we put container 1 and container 2 just on the same operating system, then you can leave container 1 and you can go to container 2. And if we just put it on the operating system without the container runtime module, we won't have anything to limit the CPU and the resources of it as well. So that's typically why we had that, which is why in that last diagram, let me go back to it. Oops, wrong thing. When you work off of 4 monitors, you open and close windows, and you're terrible about reboots, finding the right window is always a bit of a challenge. So, okay, so if we go back to this graphic here real quick, which you were asking about, let me shrink that down so we can see it. So, and let's just put it on bare metal just to make life a little easier to understand this, because you could do this on a bare metal server. So if we have the server, and this is just the physical server itself, and then let's say we install Red Hat Enterprise Linux server, Windows server, Ubuntu server, I don't care. In order to have this container and say this container is Leo's container, and let's say Leo and I are in different companies, his containers and I shouldn't be talking to each other, right? So in this particular file, we've got Mike's containers. And because my cat, she thinks she's going to be a media celebrity and she's doing all kinds of crazy stuff, she has her own containers, and they are all three different businesses. It's that container runtime that almost, to me, and this is like a more of a simile, if you will, than an actual technical thing. The same way we had a hypervisor on the server to chop it up into middle servers, this container runtime almost, it makes it like you're virtualizing the operating system. So this is separate from this, which is separate from this. And that's really what the container runtime module does. Meantime, the container control plane says, Leo needs 10 containers and one of his containers crashed, so he only has 9, add 1. Or Leo needed 10 containers, but the load on these containers is too much, so add 10 more containers. That's what your control plane's doing. And the runtime is enabling it to happen. I hope that helps, because that's a great question. Okay, well, I think we answered all the questions right now. If you have more questions, when we come back, we'll be happy to answer them. So, Chris, let's get back and let's start with the labs, Leo's lab. We're all looking forward to them.
Hello. In this lab, I will demonstrate how to create a custom image. You can create a custom image from an existing disk from a virtual machine. This means you can create a virtual machine from scratch, install all the softwares or applications needed, configure the virtual machine exactly the way you need it, and then, when ready, you can create sort of a clone of the disk of this virtual machine to create other virtual machines that are exactly the same as the first one or the original one. I will start here in the cloud.google.com page, and then I will use the search bar and enter create custom image. I will select the first link. We recommend you learn about the services you are going to use, so you can cover the contents of this page on your own. I will not cover all aspects of this page, but just do a simple demonstration on how to create a custom image. In the Before You Begin section, there is a link for the images document. I will right-click the image link and click to open in a new tab. I will switch to the OS images page. The content of this page is about the images that can be used to create virtual machines. So use operating system images to create boot disks for your virtual machine instances. You can use one of the following operating system image types. Public operating system images are provided and maintained by Google, open source communities, and third-party vendors. By default, all Google Cloud projects have access to these operating system images and can use them to create virtual machine instances. Custom operating system images are available only to your Google Cloud project. You can create a custom operating system image from boot disk and other images. Then, use the custom operating system image to create virtual machine instances. Some operating system images are also capable of running containers on Compute Engine. I will scroll down the page. I recommend you cover the content of the page to learn more about the operating system images. And here we have the operating system image costs. It says that premium operating system images, whether public or custom, incur licensing fees to run on Compute Engine. This is about operating systems that require paying a license for usage, such as Windows, Red Hat, and Ubuntu Pro, for instance. The last statement for this section is, for custom operating system images, you will also incur an image storage charge while you keep your custom operating system image in your project. So please be aware about the costs of the services you use in the Google Cloud Platform. You can cover the content of this page on your own. I will close this tab and go back to the previous page. Scrolling down to the Create a Custom Image section, there is a Prepare your virtual machine for an image. You can create an image from a disk even while it is attached to a running virtual machine. However, your image is more reliable if you put the virtual machine in a state that is easier for the image to capture. This section describes how to prepare your boot disk for the image. So to minimize writing data to the persistent disk, one step you can take is to stop the virtual machine you are going to create the image from its disk. The second step is to disable the auto-delete option for the disk. I will go to the virtual machine instances page, and I will stop this virtual machine so I can create an image out of its boot disk. Now the virtual machine is stopped. I will click the name of the virtual machine to enter its details page, and then I will click the edit button and scroll down to the boot disk delete rule, and here it is. It's set to delete the disk when the virtual machine is deleted. I will change to keep disk and then click save. The page refreshed. Now I will use the top left menu to go to the Compute Engine Images page. I will right click to open in a new tab and switch to that tab. And here we have a list, a long list of public images. I will click Create Image. I will enter name for my image. I will call it Custom Apache Web Server Image. The source is a disk, and I will now select the source disk. I need to go back to the VM instances page and check which one is the one I stopped is 852. So I will go back there and select the 852 instance as the source disk for the custom image I'm going to create. The location, just for simplicity, I will select regional and accept the same region as my virtual machine exists. And I will just accept the other defaults and click create. While the image is being created here, I will go back to the virtual machine details again and click edit, and I will scroll down all the way to the bottom and just to observe if this virtual machine has any automation. And yes, this virtual machine was created with a startup script to install, to update the system packages and install Apache 2 and customize the index HTML file with a bare minimum web page here. Since this startup script was executed when the virtual machine started, the customization made by the startup script is already performed in the existing virtual machine. Therefore, the image of the disk of this virtual machine will be already updated and has Apache 2 installed on it. Let's go back to the images window, and the custom Apache web server image is ready. I can now go to the VM instances page, and I will now create an instance using that customized or that custom image. I will accept all or most the defaults. I will go to the operating system and storage, and I will click Change. And instead of a public image, now I will select a custom image to create my virtual machine. I will open here the list of images. And this is not the one I want. I want the one that's called Custom Apache Web Server Image. I will select this one, accept the remaining defaults, click Select. And just I did when I created those two virtual machines in previous labs, I will go to the networking tab and allow HTTP traffic because I installed Apache Web Server and I want that web server to be reached from the internet. So I'm allowing HTTP traffic, and I will go to the Advanced tab and make sure that the automation and startup script is empty. I will click Create to create the virtual machine using that custom image. Now the virtual machine is ready. I will copy its external IP address, open a new tab and enter http :// and enter the external IP address of the virtual machine, and it shows hello world. This is the landing page of my Apache web server page. This is just the same customized web page as the virtual machines I created in previous labs. In this lab, I demonstrated how to create a custom image from an existing virtual machine, and then I demonstrated how to create a new virtual machine using a custom image. Thank you for watching. See you in the next lab.
Okay, we're back for a couple of quick seconds, just checking in on you, seeing if anybody need anything out of the last lab. And if not, we'll go straight into the next lab. So let us know that you're awake. If you don't have any questions, maybe give us a hashtag Google Professional Cloud Architect or a hashtag Leo's demos are great. Whatever you want, just so I know that you're there. And we'll give it a couple more seconds, see if anything pops up. And if not, we'll go to the next one. And Leo, what's in the next lab again?
The next one is how to create instance templates.
All right, Chris, I didn't see any questions pop in, so let's roll with the content on how to create instance templates. And as a reminder, we have a
Hello. In this lab, I will demonstrate how to create instance templates. An instance template is a resource that you can use to create virtual machines individually or in managed instance groups. Instance templates define the machine type, boot disk image or container image, labels, and other virtual machine properties. Instance templates are a convenient way to save a virtual machine's configuration so you can use it later to create virtual machines or groups of virtual machines. I will start by opening a new tab and visiting cloud.google.com. This is Google's entrance page. You can perform your login, you can access the console, and also you can access the documentation. I will click Docs to open Google's documentation, and from the left side menu, I will click Compute. Then I will click Virtual Machines, and after that, I will click Compute Engine. This will open the Compute Engine documentation. We recommend you read the documentation of the services you are going to use to understand the services, the charges involved, everything. In this section, Documentation Resources, under the guides, I have the option to choose a deployment strategy. I click this link to open the document. And again, you can cover the content of this document on your own. I will go straight to the point I want to highlight or to call your attention for the information. Here, under the review the available deployment options, we see you can use standalone virtual machines depending on the use case you have. You can use unmanaged instance groups, and you can use managed instance groups. When using standalone virtual machines, you choose the machine type, image, disks, and other attributes individually for each virtual machine that you provision, and you manage the virtual machines as separate resources. When using an unmanaged instance group, you can provision standalone virtual machines and add them to an instance group. You can then use the unmanaged instance group as a backend to a load balancer. In this case, let's say you are running a web server. You can have several virtual machines running the application, the web server application, and use them in an unmanaged instance group, and you put in front of them a load balancer to distribute the incoming requests. When using a managed instance group, you would have identical virtual machines or similarly configured instances that you provision by using an instance template. So first, you create an instance template, and from the instance template, you create the virtual machines that will be part of the managed instance group. You can make a managed instance group stateful so that specific disks or metadata are preserved. For a stateless managed instance group, you can enable autoscaling and configure a scaling policy. If you are not familiar with stateful or stateless concepts, basically stateful is something that has a track record and keeps data, and a stateless is something that doesn't care about the data being processed. It does its job and then finish and start the next job. It doesn't keep track of anything. The important aspect here is that for a stateless managed instance group, you can enable autoscaling. Autoscaling is the ability or the functionality that allows the number of virtual machines inside a managed instance group to increase or decrease depending on the demand. When the demand increases, the number of virtual machines will increase inside the managed instance group, so the group is able to take care of the demand. When the demand decreases, the number of virtual machines can be reduced to avoid costs of virtual machines working with very low utilization. The last topic from the managed instance group characteristics is, while creating a managed instance group, you can choose to deploy the virtual machines within a single zone or distribute them across more than one zone in a region for high availability. I will keep scrolling down. You should read this page and understand the different concepts here. How to choose the strategy based on the requirements, the decision tree. And here from the What's Next session, I will click the link to learn more about instance templates. Again, read this page, cover the documentation to learn about the services. I will go straight to What's Next section and then click Create an Instance Template from scratch. This opens the Create Instance Templates page, and I will go down to the steps. The steps under the Create an Instance Template section. The steps I will execute now will create an instance template that can be used to create virtual machines identical to one I created manually using the console in a previous lab. The difference is that one can use the instance template to repeat the creation of virtual machines thousands of times, and they will always be equal, saving time and reducing the chance of errors. Here, on the step-by-step, the first step is to go to the Instance Templates page and then click Create Instance Template. Let's go to the console. I'm already under the Compute Engine. I use the left menu to click Compute Engine, and now I will go to the Instances Templates page. I will click Create Instance Template. To make this demonstration simpler, I will accept most of the defaults, especially the recommended ones. I will accept the machine type. I will accept the boot disk. This is using a public image to create the boot disk. I will check to allow HTTP traffic because I will install Apache web server in this virtual machines created by this instance template. And then I will click open the advanced options, go to the management section, scroll down to find the automation fields, and then I will paste the startup script here. The startup script is basically updating the system package, apt updates, installing the Apache web server, and then it replaces the index.html default file with a bare minimum HTML file just to customize the web page. With that done, I can click Create to create the instance template. The template is ready, and you can use it to create identical virtual machines. The creation of virtual machines using instance templates will be demonstrated in another lab. The instance templates are used for automating the creation of virtual machines. Let's think of a web server application. If we have a fixed number of servers to respond to the average demand, when the amount of user requests increases, the system will not be able to respond to all requests. This is bad for business. On the other hand, if we have a fixed number of servers to respond to the peak demand, they will work most of the time at low utilization. This means unneeded costs. To solve this issue, we should use a technology that monitors, for instance, the server utilization, and when it exceeds a threshold, for instance, 70% of its capacity, a new virtual machine is added to the pool of web servers. Please refer to the bootcamp content and to the documentation about autoscaling groups to learn how they work and the different types of load balancers that can be used with groups of virtual machines. I will open another tab here in the browser and visit cloud.google.com again. Now I will use the search functionality and enter Autoscaling group. I will open the first link. I will not explain autoscaling in this demonstration, but you should read the documentation to understand and learn more about autoscaling. You can see here that autoscaling can be based on CPU utilization, load balancing serving capacity, and cloud monitoring metrics. as the Autoscaling group monitors the server metrics, for instance, CPU utilization, and let's say we have 5 servers in a group and they are almost reaching that limit utilization of the threshold. If one of those servers fails and go offline, the others will need to take care of the demand, and then their utilization will increase. When their utilization increases, it will trigger the auto-scaling to create a new virtual machine to add to the pool so the utilization is kept under the threshold. I will close this tab and go back to the demonstration. Now, let's say our web server is in production and using the auto-scaling group to add more virtual machines when the demand increases. Let's say that Apache released a new version of the Apache web server. The next virtual machine created using that instance template will update the system packages and install the new version of the Apache web server. That could be an issue. In a production environment, before applying any software updates, it must be tested in a controlled environment to make sure the update doesn't break the applications or create any unexpected behavior. Only after the update is tested and approved, it is applied to the production servers. This means that using a startup script in an instance template, as I did before, is a risk for the business. There must be, or there could be, scenarios or use cases that would need an instance template with a startup script to be used, but in general, it should be avoided. To avoid that kind of risk, you should create deterministic templates. I will switch to the documentation page again and click here on deterministic instance templates. On the first paragraph, the second statement starts with deterministic instance templates make explicitly clear the type of third-party services or apps to install on your instances when the instance template is deployed. By creating deterministic instance templates, you minimize ambiguity and unexpected behavior from your instance templates. And here, the section Why Create Deterministic Instance Templates states, in general, we recommend that the properties of your instance templates be as explicit and deterministic as possible. If you employ startup scripts in your instance templates that install or use third-party services, make sure that these scripts provide explicit information, such as the version of app to install. Compute engine can only rely on information defined in the template and has no control over referenced third-party services. If your template is too vague, your instance template might behave unexpectedly. Here we have one non-deterministic code sample. This is using the G-Cloud command line tool to create compute instance templates. And what we can see here is the family of the operating system used. And here under the startup script part, it's using sudo apt install Apache 2 and is using the secure copy protocol from a remote machine with this IP address to copy the index.php from that machine or from that server. This index.php will be used in the instances created by using this instance template. Now I will scroll down to show the equivalent code but more deterministic. Here is this an equivalent sample code for that one, and the name of the startup, the name of the instance is created with this instance template, has sort of a versioning, and the Apache web server application to be installed using the apt install command has one specific version. So every virtual machine will install the same version of the Apache web server. Also, the index.php file that will be copied from a remote server will also have a versioning system. So every application installed or copied from a remote server will have one specific version. So all instances or virtual machines created by using this instance template would use the same versions of the softwares. Here, just above, there is a paragraph about create a custom image. And it says, create a custom image to use as the image for the template. This is preferable to startup scripts because it guarantees that every instance is the same. Startup scripts might have different results after distribution package updates. Use startup scripts in your instance templates for prototyping and rapid development, and use custom images when you are ready to deploy production quality services. Creating a custom image is like cloning the boot disk of the virtual machine. To use the custom image to create virtual machines, you need to create an instance template and set the machine type, the network and subnets, etc. The advantage of creating an instance template with a custom image is full control over the virtual machine settings. Another alternative to clone an existing virtual machine disk is to create an instance template from an existing virtual machine. The instance template inherits the machine type, the network settings, the virtual machine metadata, and so forth. It is basically a clone of the original virtual machine. The advantage in this case, it saves time when creating virtual machines and reduces configuration errors. I will go back again to the Google console and I will click Create Instance Template. As I did before, I will accept most of the defaults, but I need to change the boot disk, and I will click here the Change button. And instead of using a public image, this time I will select Custom Images and select the image I want to use. In a previous lab, I created this custom Apache web server image. If you want to see how to create a custom image, please refer to that demonstration. I will accept the remaining options and click Select. I will scroll down and allow HTTP traffic again. The virtual machines created using this instance template, they will have Apache web server installed. That's why I need to allow the HTTP traffic. Reminding everyone that HTTP is not secure. In a production environment, you make sure you use HTTPS traffic. After allowing the HTTP traffic, I will click Create. I will hit refresh. And now I have two instance templates. One was created using a public image plus a startup script. And the second one was created using a custom image. The advantage of the second one is that all virtual machines created using this instance template will have the same versions of the softwares installed on it. In another lab, I will demonstrate how to use instance templates to create virtual machines. In this lab, I demonstrated how to create an instance template using a public image and a startup script, and I have also emphasized the importance of creating a deterministic instance template. Finally, I demonstrated how to create an instance template using a custom image. Thank you for watching.
Hello, and we are back. So far, we have demonstrated how to create a custom image and how to create instance templates to automate the creation of virtual machines, so we can create many virtual machines for the same purpose, for the same responsibility. What we will see after is how to use the instance templates to create virtual machines and how to create groups of virtual machines or manage instance groups. And once we have managed instance groups, how we can use autoscaling to increase and decrease the number of virtual machines on that group based on the demand. Should we go to the next lab, Chris?
Hello. In this lab, I will demonstrate how to create virtual machines using instance templates. I will start opening a new tab and visiting cloud.google.com, and I will use the search bar and enter the following keywords: create a VM from an instance template. I will select the first link here. Here is the page about creating a virtual machine from an instance template. I will not go over all the content of the page. I will go straight to the steps required to create a virtual machine instance from an instance template. We have just a few steps. The first one is to go to the console and switch to the create an instance page. Then I will use the create VM from button or option to select to use instance templates to create the virtual machine. And then in the create VM from template window, select the template and then click create to create the virtual machine. I will go then to the console, and since I'm already in the VM instances page, I will click create instance. Here at the top, we have the create VM from button or option. I will click this button and select instance templates. This opens the list of instance templates available to use. And right now I cannot differentiate which one is using a public image with a startup script and which one is using a custom image. I will pause this step for now, and I will need to close here first. And then I will switch to the instance templates window, or right click to open the instance templates window in a new tab. Switch to that tab. And then here I see 324 is the one with the custom image, while 807 is the one with the public image and a startup script. I will use first the 324 to create a virtual machine instance. I will close this tab and then click the Create VM From option again, select Instance Templates, and now select the 324 to use the instance template with a custom image. Then I will click the Create button to create the virtual machine. The virtual machine is being created, and once it has a public IP or external IP address, I will copy that address, open a new tab, paste the address here, and check if I can reach the web server. It should show a customized web page, a very minimum web page that I customized when creating the custom image. This should show the minimum HTML customized page I used when creating the custom image. I will leave this tab there, and I will demonstrate now how to create a virtual machine with overrides. If I go back to the documentation, is the topic just below that one, and where or how you can customize the creation of the virtual machines even while using instance templates. I will click Create Instance again, click Create VM From button, select Instance Templates. Now I will select the instance template ending with 807, which is the one I created using a public image plus a startup script. I will then click Customize. Here, you can customize different options of the virtual machine, and I will go to the Advanced tab, and here is the automation script, the startup script I used to create that instance template with a startup script. I will select all the content here and delete it because I want to add a new startup script here that is different from the one used before. It is also a very minimal startup script, is a bash script, and I have some comments now to update the system package. I'm running the apt update-y command to install Apache Web Server apt install Apache 2-y commands. And here now I have some commands to fetch data or metadata from the virtual machine. It's using the cur command to fetch some metadata from the virtual machine. The first one will store the name of the virtual machine on this variable VM underscore name, and there is another one to fetch the external IP address of the virtual machine and store in the external IP variable. Later, when creating the minimum index HTML file, I will use those variables to show hello from VM and then show the name of the virtual machine, and also to show the external IP address of that virtual machine. At the end of this script, I have a command, a system command, to restart the Apache web server. When everything is done about the startup script or the customization for this new virtual machine, I can click Create. The virtual machine is now being created. You can observe that it will take a little bit longer than the one created with a custom virtual machine, because this one will do all the customization, execute the startup script after the virtual machine is created. And the detail for this one is that each virtual machine that you create with the instance template should be equal. But in this case, I am customizing the settings of the virtual machine and using the instance template. So I am saving time because I'm using the instance template, but each virtual machine will be unique depending on the customizations, the manual customizations I do when creating the virtual machine with the customize option, even using an instance template. I will click the IP address of the virtual machine. I will copy the external IP of the virtual machine, open a new tab, paste the IP address here. It shows the customized index.html file I have using the latest startup script. I will close these tabs. And since I created those virtual machines just to demonstrate, I will select them all and hit delete to remove them from my project and avoid any costs. In this lab, I demonstrated how to create a virtual machine using an instance template, and I also demonstrated how to create a virtual machine using an instance template, but customizing some aspects of the virtual machine created. Thank you for watching, and see you in the next lab.
Okay, we are back. What we're going to do is I think we have 2 more labs left. Is that if that's correct? And then we're going to go back and have 2 lectures on containers, which I always think is fun. But I wanted to remind everyone that we have a webinar on Thursday on how to become an architect. Please join us. We'll go over the role. We'll talk about what we do. We'll talk about the things that you need to do to get hired when you don't have any experience, because you can. You just have to have a certain set of characteristics, and we'll talk about what those characteristics actually are. And it's free, and I'll answer any questions you may have about your career. So my team will drop a link to that. I also wanted to let you know that if you just joined, lots of times YouTube sends people notifications at all kinds of times. We have the first week, my team will drop the playlist you can view. But we also have a completely free guide, a study guide for the Google Professional Cloud Architect exam that you can also sign up for, and it will be emailed to you. So please go check that out. My team will also drop that in the chat box. And if you've got some questions, let Leo and I know. Leo, what's coming next from your next 2 labs?
Next, I will demonstrate how to use that instance template to create a managed instance group, and then how to use auto-scaling on that group of virtual machines.
Sounds great. All right, Chris, let's start Leo's labs.
Hello. In this lab, I will demonstrate how to create a managed instance group. A managed instance group is a group of virtual machines that you control as a single entity. Managed instance groups support features such as auto-healing, auto-scaling, load balancing, multiple zone coverage, and stateful workloads. I will start here at this page, cloud.google.com, and I will click Docs to open Google Cloud documentation. And here from the left side menu, I will click Compute, then Virtual Machines, and lastly, I will click Compute Engine. Here is the documentation about the Compute Engine. We recommend you read the documentation to learn about the services you are going to use. From the documentation resources, one of the guides is Choose a Deployment Strategy. I will click this link to open this document, and then I will scroll down to the Review the available deployment options. This page shows and explains the different deployment options, but the focus of this demonstration is the Managed Instance Group, and it says a Managed Instance Group is a group of identical or similarly configured instances that you provision by using an instance template. You can make a Managed Instance Group stateful so that specific disks or metadata are preserved. For a stateless Managed Instance Group, you can enable autoscaling and configure a scaling policy. This means that if you want to use autoscaling, then you need to use a stateless Managed Instance Group. I will keep scrolling down. You can cover this document on your own time. I will not explain all the details from this document, but I will go to the What's Next session. And among the options, there is one to create a Managed Instance Group. I will click this link to open the document. And here, under the basic scenarios for creating a Managed Instance Group, there are different guides here. I will click the first one, create a Managed Instance Group with virtual machines in a single zone, what is called Zonal Managed Instance Group. Now I have the Create a Managed Instance Group in a Single Zone document open, and I will go to the steps needed to create a Managed Instance Group in a single zone. There are quite a few steps, but the first one is to go to the Google Cloud Console and select the Instance Groups page. After that, click Create Instance Group. That will start the window to configure the instance group with the different settings and options. I will then go to the Google Console. Since I don't have the Google Console open, I will right-click Console and then open in a new tab. I will switch to that page and open the left side menu, Compute Engine, Instance Groups. I will click the button Create Instance Group. Here on the Create Instance Group page, we have different options on the left side. We have a new Managed Instance Group for stateless virtual machines, another one for stateful virtual machines, and a new Unmanaged Instance Group. Since I want to create a Managed Instance Group with autoscaling enabled, I need to select the stateless, the first one. Here, for the options, I will accept most of the defaults, but I need to select an instance template. I will use the instance template I created from or using a custom image which has Apache Web Server installed with a minimal index HTML file or customized file just saying hello. Scrolling down, I will reach the autoscaling section, and after opening the combo selection box here, I can see different options. Off, do not autoscale, scale out, only add instances to the group, never remove instances, and I can set autoscaling to on, add and remove instances to the group. Depending on the use case you have at hand, a different selection will apply. For this demonstration, I will choose the option on to add and remove instances to the group. I will accept the minimum number of instances as 1 and maximum as 10. And also I will accept the CPU utilization as 60%. Continue scrolling down, we will reach a show advanced configuration, and here you can find what is a standby pool. This means you would create or you would set the manage instance group to create virtual machines and have them on suspended state, ready to be resumed whenever the auto-scaling is triggered to add more virtual machines to the group. This means the virtual machines will be ready quicker than if the auto-scaling had to create the virtual machines and then add them to the group. With this option set, I will click Create to create the Manage Instance group with auto-scaling enabled. I will select the Compute Engine VM instances. I will right-click to open in a new tab to observe the virtual machines that will be created by the instance group. Here, we already have one virtual machine being created. It already has an external IP address. I will copy this IP address, open a new tab, paste the IP address here, and try to reach the web server that exists in that virtual machine. And the page says, "Hello world, this is the landing page of my Apache web server page." This is what I have customized in the custom image that is used by the instance template to create the manage instance group. And here we can see the characteristics or information about the manage instance group. Right now it has one instance. It is a group type, a manage group type. And we have here the auto-scaling settings to on with target CPU utilization at 60%. Now I will go to the VM instances page, and I will wait for the virtual machine is completely ready so I can SSH into that virtual machine. I will bring the SSH window up here. I will authorize the SSH window. And I will drag the SSH window to the side, and I will click the observability tab here on the VM instances page to show some metrics, and I will choose CPU, and I will click this button to enable auto refresh. I will also select the last 15 minutes to be shown on the screen. I will bring back the SSH window, and now I will update the system on the virtual machine. And when that's finished, I will install an application called Stress. This application will be used to simulate a higher CPU utilization on the virtual machine, kind of a stress test on the virtual machine. So the higher CPU utilization can trigger the auto-scaling group to add more virtual machines to the manage instance group. The application finished installing, and I will use, or I will type in the command stress --CPU. 2 virtual CPUs will be stress tests --timeout 30 seconds. I will hit enter and switch to the metrics window. I will just move out and in again to see the utilization going up, and then at some point the number of virtual machines will also increase because the Autoscaling group will trigger the creation and addition of new virtual machines to this group. Now we have a second virtual machine being added and becoming available. And now we have a third virtual machine also being added to the group. The existing one was the 129. I will get the IP address of this one, that is 120, and also test to see if I can reach the web server is there. And the last one is also there. So at this moment, I have 3 virtual machines running in this managed instance group. And this number reflects here on the details of the managed instance group. I will go back to the documentation now, and I will scroll all the way to the bottom, and under the What's Next session, there is one link to enable autoscaling to automatically add or delete virtual machines from your managed instance group based on increases or decreases in load. And in this document, I want to explain or to comment one of the sections that is called stabilization period. This document informs that since the metrics, CPU utilization, load balancing utilization, since those metrics usually vary a lot in time, they increase, they decrease all the time, having new virtual machines being added and removed all the time will not be practical or feasible. When the CPU utilization increases, new virtual machines are added to the managed instance group. But when the demand decreases, when the CPU utilization reduces, the auto-scaling group will wait for the time for this stabilization period. If no other peak in CPU utilization happens within a 10-minute period, the virtual machines will be reduced. But if in the period of 10 minutes another peak happens, then a new stabilization period will start. The stabilization period is equal to 10 minutes or initialization period that you set for the instance template, whichever is longer. And the stabilization period is used only for scale-in decisions when the autoscaling has to delete virtual machines. I will keep scrolling down. And here under limitations, we have some limitations of using autoscaling. It says you cannot use autoscaling with the following instance groups, which don't allow the autoscaler to create or delete virtual machines according to demand. The first one that you cannot use autoscaling with is an unmanaged instance group. You also cannot use autoscaling with managed instance groups with stateful configuration. Also, with managed instance groups with virtual machine repair turned off. Regional managed instance groups with a target distribution shape of any single zone. And you cannot create virtual machine instances with specific names while autoscaling is turned on. The last item of the limitations informs do not use compute engine autoscaling with managed instance groups that are owned by Google Kubernetes engine. For Google Kubernetes engine groups, use cluster autoscaling instead. After reading the documentation, I will go back to the virtual machine instances page, and we have 3 virtual machines working. I will refresh the pages that are accessing their web servers. and all of them are still running and responding to the requests from the web browser. I will wait for the 10 minutes to pass. So after the 10 minutes, the Autoscaling group reduces the number of virtual machines present in the managed instance group. We can see the utilization has reduced. So the stabilization period is being counted. And when the stabilization period is over, the virtual machines will be reduced and only one will remain, because this is the minimum set when creating the managed instance group. I'll hit refresh to check if the virtual machines have been removed. And yes, now we have only one virtual machine running. And if we try to refresh the web page they were serving, two of them will time out. Let's see. And checking the instance group, it will show one instance only. So after the stabilization period, the virtual machines were removed because there was only one peak in CPU utilization. Since no other CPU utilization peaks occurred in the stabilization period, the virtual machines are removed from the managed instance group. And here the first one timed out, and here the second one also timed out, and only one keeps working because the virtual machine still exists. Now we have one virtual machine running that was created by that managed instance group, and we have the instance group here. Whenever you don't want the virtual machines anymore, you can delete the whole instance group and it will take care of deleting the virtual machines as well. So I selected the instance group here and I will click delete to completely delete the instance group with the virtual machines. It requires to confirm that I want to delete. I typed delete and then I press the delete button. Let me refresh the virtual machines page as well. After some time, the virtual machine disappeared. And if I switch to the instance groups page and refresh it, after some time, the instance group is also deleted. So right now, we don't have any instance groups and we don't have any virtual machines. In this lab, I demonstrated how to create a managed instance group with Autoscaling enabled. Thank you for watching and see you in the next lab.
Okay, we are back. We've got one more lab, but it looked like one question came in from Sergio. So I think we'll answer Sergio's question, see if any other questions came in, and then we'll get back to Leo's lab and then the next content. So Chris, if you want to bring in Sergio's question. Sergio says, hi, Mike. You said that a container could be hacked and could jump to another container or container runtime. Could I explain how these containers, and talk about the front end being exposed or not front end being exposed. Sergio, all this can occur without the front end even being exposed. And let me give you a couple of examples of the technology, its limitations, and therefore what some people actually do in super high security environments. Now, you may notice that the US government, for example, does not use the same cloud that regular people use. They asked for a separate cloud to be built for them for this particular reason. But that doesn't mean that a normal cloud isn't safe. So let's look at the real reality of where we're going into one of these environments. And let's take a cloud provider server or one of our servers, for example, while we're at it. So let me go to this example. It looks like these slides are pretty much where they're supposed to be. So let's say this is a server at the cloud provider. And on that server at the cloud provider, they've got their runtime module. And this could happen in your own data center too. Now, and then you've got your containers. So this is customer A. Now, we'll put a couple of the customer A servers on this, customer A's container on this. Now we've got customer B. Now we've got customer C. And this shouldn't happen under normal circumstances. But just work on this assumption. So this thing has an IP address on it, this container. So if anything does actually, let's do this. So there's a couple ways this could be hacked. One is if the operating system itself is hacked on the server. If you hack this operating system, anything contained in this operating system can also be hacked. So this server is on a cloud provider. If the cloud provider itself gets hacked, they can get into that server. The operating system, you'd have to hack the server. So what would have to happen is, and it's not the easiest attack to execute, you're the customer or you're a hacker, it doesn't matter. From the customer, you're always inside this. You can always reach your systems from the internal IP address. So if customer A, maybe they did something silly on their system, got hacked through that system, and it was able to hack the runtime module, it could theoretically go into one of their containers or another container sitting on that same server, because they're all sitting on that same server. That's the concern. Now, sure, if this was exposed to the internet, or worse yet, somebody had a Bastion host out there, and from the Bastion host, you can go jump on the customer's network and then break out of that and go through. But so that's one option, but it shouldn't happen that often. But at the same time, let's just the virtualization attack, which is harder to execute. You still have the security risk. So this could be a hypervisor. And if it's possible and you could have virtual machines from two servers for the same customer. So this could be customer A, and this could be customer B, all on the same server. So if this is a virtual machine, it's pretty hard to go from here to here, because these things are typically going to be on different subnets. In order to hack the hypervisor, you're going to have to escape the entire operating system itself, which should be really hard to do, and then hack into the hypervisor, and then escape the hypervisor back into this system, which is going to have a different IP, which is going to be very hard to do. But what do customers do when they can't handle other people's things on their servers? They basically get a dedicated host, which is not the same as a dedicated server. But in many cases, what they'll do is they'll get a dedicated host, and that host will have the cloud provider's hypervisor, and they will only put the cloud one customer's virtual machines on that. Now, you could also, if you wanted to, buy a dedicated hardware, and instead of taking the cloud provider's hypervisor, you could use Nutanix or VMware or something like that. and that you could put on your servers, and you could have the same Nutanix control plane in your data center and cloud. But that's the key, is with a virtual machine, you'd have to escape the virtual machine, escape the hypervisor, and go back. With the container, it's easier theoretically, because you would leave one container either through the container runtime module, or you'd hack the operating system. So theoretically, that's why virtual machines are more secure. Now, obviously, if they're exposed to the internet, that's even there, but you still have access to the private IP addresses of your system. So, and all this stuff could happen from a private network to a private network. Hope that helps there, Sergio. But it's not likely to really execute too many of these hacks. These are just the architectural considerations we face as cloud architects, cloud security architects, and any architect for that matter. All right, we've got a lab and then a lecture. Leo, what's your next lab on?
The next lab is how to create managed instance groups from an existing virtual machine.
Sounds great. Give me a hashtag Google Professional Cloud Architect, and let's roll with the content.
Hello. In this lab, I will demonstrate how to create a managed instance group from an existing virtual machine. I already have a virtual machine here. This virtual machine was created to be a web server. I used a custom image to create this virtual machine. Just to test it, I will copy the external IP address of this virtual machine, open a new tab here, paste the IP address and press enter. It should show the customized minimum web page from that web server. It shows hello world. So the virtual machine is working as a minimum web server. Please note, this is not for production, it's just for learning purposes. I will go back to the page cloud.google.com and I will use the search functionality. I will enter create a mic from an existing VM. And the first link is create a managed instance group from an existing virtual machine. I will click this link to open the document. And as usual, we recommend you read the documentation to learn more about the services you are going to use. There are some steps before you even begin. There are limitations you need to know when creating a managed instance group from an existing virtual machine. And here are the steps to create a managed instance group from an existing virtual machine. The first step is to visit the Google Cloud Virtual Machine Instances page and then select the name or select the virtual machine that I want to use to create a managed instance group. Here is the virtual machine I already have tested. I will select this virtual machine. So it shows the create a group based on this virtual machine option. I click that option. And then here there are some suggested steps. For instance, the name of the instance template that will be created to create the managed instance group. I will accept the suggested name. Regarding the disk, the default value is to generate a new image from the disk from the existing virtual machine. I will click the Edit Boot Disk option here, select a custom image, and select the custom Apache Web Server image. It's the same one I used to create the existing virtual machine. After that, I will click the Select button. Scrolling down the page, there are some settings for the instance group properties. I will accept the instance group name, the location as a single zone. Please read the documentation to learn more about the difference when using single zones and multiple zones. And I will click the Configure Instance Group button. to open more options for customization of the managed instance group that I want to create from an existing virtual machine. I will accept the name, the location, but I will click the Configure Autoscaling button to configure how this managed instance group will behave regarding autoscaling. I will accept the autoscaling mode set to on. There are different modes here. I will not explain all of them, but the autoscaling mode on means the autoscaling will add virtual machines when needed and will remove virtual machines when they are not needed anymore based on the current demand or number of requests. I will accept the defaults as 1 for minimum number of instances and 10 for maximum number of instances inside this managed instance group. I will also accept the CPU utilization target or threshold as 60%. Any virtual machine that goes beyond the 60% threshold will trigger the creation of a new virtual machine. So the load on all instances in the managed instance group is below the threshold. With all set, I will click Done. And then I will click Create Group. Now the instance group is created. And if I go to the virtual machine instances page, it will show a new virtual machine was created for the instance group 1. The documentation emphasizes that the existing virtual machine that is used to create the managed instance group is not included as part of that group. Once you have created the group based on that existing virtual machine, you can turn it off, you can delete it, you can do whatever you need to do with that virtual machine, since it will not be part of this managed instance group. Just to test the virtual machine created in this lab, I will copy the external IP address, open a new tab, paste the IP address and press enter to verify if the web server shows hello world, and it does. We verify that the created virtual machine is working, and whenever the CPU utilization reaches the threshold of 60% for this virtual machine, the managed instance group will automatically create new virtual machines to keep the CPU utilization below the threshold. The cleanup part is based on the instance group page. You select the instance group and then you click delete, and you need to type in delete and press the delete button to confirm you want to delete the instance group. Now the instance group is deleted. There are no more instance groups. And let's go to the VM instances page and refresh. The virtual machine that was created with the managed instance group is deleted as well. So deleting the managed instance group will delete all virtual machines that were created when creating that managed instance group. The only virtual machine remaining is the existing virtual machine that was used to create that managed instance group. In this lab, I demonstrated how to create a managed instance group from an existing virtual machine. I also demonstrated how to remove all the virtual machines by deleting the managed instance group. Thank you for watching, and see you in the next lab.
Okay, Leo and I are back. We've got a little bit of container content to go. We know we're working aggressively. We're going to try and finish up on Thursday, if at all possible, so that you can have Friday off. And then if you want next weekend, maybe you prepare for the exam. It's a pretty straightforward exam or something like that. Or watch it a second time or a third time or whatever. So we've got one more to go. Give me a hashtag Google Professional Cloud Architect. And Chris, let's get back to this content.
In this next section, where we're going to prepare you for the Google Cloud Certified Google Professional Cloud Architect exam, we're going to cover storage, databases, data analytics, and observability. We're going to start with storage. So what is cloud storage? Storage is where you store your information. And there's lots of types of storage. I mean, we introduced them earlier: block storage, object storage, and file storage. We also talked about their use cases, but we'll go over it a little more here. But storage is where you store your data. So, for example, a business may have data. It will put it in one form of storage based upon how the storage needs to be used. Of course, if we're dealing with a virtual machine, which is going to use block storage, we have storage related to the data on that virtual machine. But there'll also be storage that's taken up on that virtual machine for the applications and the operating system as well. But they could be on different volumes, or example, which are like virtual drives. But keep that in the back of your mind, as storage where you keep things. And cloud storage where you keep your things on the cloud. Now, in Google world, cloud storage typically means object storage, but we'll talk about storage in general, and then we'll talk about the types of storage. So the point is you need to store your information somewhere. And that's what we're going to talk about. In this case, we're going to start with object storage. And object storage is a form of storage. Let's map it out. And the key with object storage is it's not like normal storage at all. It's much, much, much more like a database. And we're going to walk through this so you understand what is object storage and, for the most part, how it works. So if this is our RAID array that actually has the storage and underlying infrastructure, this thing is going to be a server, and it's just going to be full of hard drives. And they'll be in a RAID environment, increased speed, availability. And that's, well, I meant to draw hard drives, but that's what we're normally going to get. So that's the actual physical object storage. And they're going to be servers with a whole lot of hard drives. But the way object storage is going to work for us is, let's say we create a bucket, which is our virtual storage area, if you will. And all the providers use different terms. It doesn't matter how we call it. We have data over here. And let's say this data is, Cindy's Excel sheet, cindy.xls. So if this is Cindy's spreadsheet. Now, when this actually gets written into or saved in object storage, what you're going to see is still going to look like Cindy XLS, but the data is actually going to be stored as an object. So as far as the object storage notice, this Cindy XLS is an object. And everything that puts in here will be individual objects. So if Cindy, for example, took a photo, and let's say it's Cindy.jpg, JPG, it's still going to be a different object, and it'll have a different object number, and it's going to have different information about that object. So the first thing is, when data is stored in object storage, it becomes an object. The second thing I want you to know is metadata. Metadata is data about the data. So Cindy.xls could have a lot of information about what's in that Excel spreadsheet, for example. Or the metadata could really tell you what's going on with that Cindy.jpg. So we can, if we need to search for something, we can find it because this stuff has metadata that we can search through. So a lot of good comes from that metadata. Now, we also have to understand that this is flat storage. And what I mean by flat storage is, it's not hierarchical like you would actually deal with in traditional storage. So you might have you might be used to the root of the drive in file storage, for example, and underneath the root, you may have something like users, and underneath the users, you could have like, Mike, for example, and it all falls underneath each other. In object storage, it's really just flat storage. But what happens is when Cindy actually drops off her Excel spreadsheet in this case, there's going to be a pointer to the data that's going to say reach the data here. And the pointer to the data is going to be stored in very much like a database type format. And that's going to be how the data is actually accessed. So we may create things to make it look and feel hierarchical, but that's for us. It's a big, giant, flat storage environment with a pointer to the data. Now, the last thing we need to really remember with object storage is it's worm storage, or write once and read many times. And here's the reason. In traditional object storage, the Cindy.xls cannot be changed. So if Cindy were to make just 0.1% difference, it would be a Cindy XLS, say, object, and it'll have a different object identifier. And then if she touches and removes it and manipulates it even one bit, it's going to create a new version. And because of that, the way object storage works like that, you can't really use it for a hard drive in most cases unless you're doing some kind of a storage gateway or to translate it, because this is different kind of storage. Imagine a swap file on a computer that had 4 terabytes of DRAM. That's the virtual RAM that you would use the hard drive for if you ran out of RAM. So if you had 4 terabytes of DRAM, and that means your swap file would be 6 terabytes. And what if that thing changed 100,000 times in a minute, which it could on your computer? That would be filling up. Just imagine each one of those would be 6 terabytes. And every single time it changed, potentially 100,000 times a minute, there'd be a new 6 terabyte object. So this is write once, read many times, and that's why object storage is not used for virtual machines. It's used for backup and archival purposes, software distribution, static website hosting. So now let's go back and talk about cloud storage. So now you know that Google's cloud storage is object storage, which means it's basically the same thing as AWS S3 or Azure Blob. Now, all the manufacturers have slightly different feature sets from each other, but the technology we're talking about is the same. Object storage is a very critical form of storage in cloud computing. It enables the persistent saving and retrieval of something. So you may have a virtual machine and you have an image of it, and you store that in object storage, and it doesn't change when it's in object storage. So, we may be using object storage, for example, for backups, and that's the reason why. Now, when we talk about cloud storage, when we talk about object storage, you may recall I talked about metadata on the data or data about the data. So for this reason, to be able to get data about the data, you often see object storage used in big data environments and data lakes because of the way object storage is structured. Object storage is incredible for backup, and it's typically good for analytics because of all the metadata that we can be collecting. So Google Cloud Storage is going to be scalable because the capacity is just there. You just need to use it. And it's designed to be what's called durable. And in addition to be relatively high availability. So the difference between availability and durability is as follows. Availability means, is it there when I need it? And you could have a 99.99% availability, means that system's available to you upwards and you can tolerate about 50 minutes of downtime per year, but otherwise it would be up and operational. Now, imagine that your system's not operational for 52 minutes, but your data stayed. It was durable and nothing changed when you couldn't access it. So that's what we mean by durability. Availability is related to the systems being there when you need it. So if you want to think about that, how does the cloud provider do this? They take your data and they replicate it to other regions. Now, this means, if you've got a data center here, they moved it to another geographic area in another data center. So that means durability, which is wonderful. But what if you're in an environment where you have to provide what's called data sovereignty, where your data can't be copied to another region that's in another country or part of the world? So this is one of the things we have to think about when we deal with the SLAs and the contracts going back and forth to the cloud providers and even the cloud services we use, what we can use and when we cannot use it. But that's a much bigger topic. But if you were taking like a CISSP or a CCSP, it would be covered because it's critical there. And obviously it's something we teach to our security architects, but it's way above this type of certification. So we talked about what this is. So that is your object storage. Now, I want to talk about block storage, which we're going to have in the Google Cloud. And that's going to be what Google calls persistent disks. But the real reason is it's just block storage. So we can map that out in a minute. We can go look at what that would be for you. And I hope that it actually makes sense. So let's say we have your notebook computer. Let's say for right now, this is your notebook. And the reason I want to show this to you. Now your notebook, inside of it has a hard drive. Probably an NVMe hard drive if you bought anything modern or real, because it's super fast and they're super tiny, which means they don't take up a lot of space. So they're really ideal for notebooks. They're great for that's what we use in high performance servers as well. But there is that. Now, when we store data over here on the hard drive, now this hard drive is file storage, and I'm sure you've looked. And let's say this is I'll give you let's say what a Windows machine would look like. I've not really used Windows machines for many years, and I recently bought one. So let's say this is the root of your drive, and then so we can call this C, if it's a C drive that you have. And then underneath that, you might have a folder called users. I'm trying to look at my computer to see what we'd have on a Windows machine. And then underneath the users, you got your username, which in my case would be Mike. And underneath that, we'll have folder versus folder versus folder. Now, the interesting thing to think about in this particular environment is this. When data is being stored to this drive, the way hard drives are typically designed is the data is written in little mini blocks. Now, this is file storage, but the data is actually written in little mini blocks. So this is a traditional way your computer would work. Now, since normally the data is written into blocks, let me introduce you to block storage. So the reason we have block storage is there's a limitation to how much storage we can put in a computer. So let's say this is a server, and let's say this server's got a lot of processing capacity. In a normal world where the storage limited to the server is limited to the number of, I don't know what I just did there, bear with me. The storage in the server would be limited to the number of hard drives in the server and the size of the hard drives of the server. But what if the server was mostly doing compute, meaning heavy-duty calculations while it still store things? We don't want ever the storage and the server to be a limitation. So what we do in the modern data centers, and by modern data centers, I mean for the last couple of decades, what we do is this. We decouple the server environment from the storage environment. So what we have over here is something called the storage area network. And what is that? I can tell you right now, it's a big box, or they're server boxes, and they're full of hard drives. Now, these could be NVMe hard drives, and that's going to be your fastest type of storage you would get in this environment. They could be old school magnetic hard drives, but let's just talk about this. So this is what you typically get in a storage area network. Now, because we have a network between these devices, and obviously there's going to be different routers and switches, but I'm just going to call this the network. And the storage area network is plugged into the network, and the server is now plugged into the network. And this is typical in a data center environment. Cloud provider, traditional data center, and here's why. I showed you how normally we save data in blocks on file storage. But block storage, and one of the greatest things about block storage is when we take data into a storage area network or a block storage environment, what ultimately happens is the data is written in a block. So that we have the data, and it's going to be written into a block or a group of blocks that are going to be pooled on this storage environment. So what block storage enables us to do is we can create a virtual hard drive that really speaks, so virtual HDD, And that virtual hard drive is really here, but we can mount that virtual hard drive to the server, and the server thinks it's a local hard drive because of the way data is normally written into blocks into a normal hard drive. And in the storage area network, they write the data into blocks, and it looks and feels a lot like the storage you traditionally had in the server. But it's not. First, this storage is accessed over a network, which means the network will be the limitation. If this server has a 10 gig Ethernet network card, there's no way then they could ever get faster than 10 gigs, no matter how fast the storage environment would be. So keep that in mind, that we've decoupled the servers and the storage, which is great from a scalability perspective, but we're not going to get anywhere near the same performance. And here's the other reason we're not going to get the same amount of performance. We have to think about the amount of network connections the NVM, this storage area network has, and it only is going to have so much capacity. But we have to remember that this block storage area network could be divided by 100 or 1,000 different cloud customers. And they're all sharing this bandwidth and the speed of this, which is why you can typically get much faster storage inside of the server itself than you ever can with block storage. I hope that makes sense. But in most cases, block storage will be the fastest storage we have in cloud computing. So block storage on Google is called a persistent disk. And there'll be various options you have for storing. And when it comes to storage, we have to think of IOPS and we have to think of throughput. So maybe I'll whiteboard that out for you so you can understand what we're talking about here. So IOPS refers to this: how many input and output operations you can do in a second here. So if we have more IOPS, we can write, and read more times per second. If this is, we can access this drive 1,000 times a second, then we can access this drive 1,000 times a second. And we can't access it more than that. So if we think about latency, how often you can actually go to the disk will determine your latency. So the higher your IOPS, or input and output operations per second, the lower your latency. Higher IOPS, lower latency. So that means there's an inverse correlation to IOPS and latency. Low IOPS, or low input and output operations per second, like an old school magnetic hard drive, high latency. So keep that in the back of your mind. Now, we also need to be considered with the throughput of our load. So let's say we had two vehicles that we were going to send from Palm Beach to New York City. Vehicle one is a tractor trailer, and it's a big truck with huge capacity. The other vehicle is a Lamborghini. I'm going to call it Lambo to save space. So now, which one has less time from 0 to 60? It's the Lamborghini. This vehicle has much lower latency to start up and access it. Now, which one has more throughput? Throughput is the amount of stuff that can be carried. So if we took the tractor trailer and then we took the Lamborghini and we said, I want you to go to New York as fast as you can, carry as much stuff as you can, and but at the end of the day, the winner is the person or the vehicle that brought more stuff. Who do you think that would win? The tractor trailer has much higher throughput. This thing can maybe hold 3 or 4 or 5 or 10 tons worth of weight. I think it's more than that. This Lamborghini may stop at a few hundred pounds of capacity, maybe 1,000 pounds of capacity, maybe 2 tons. I don't know, but it's not, or maybe a ton, but it's not going to be that much. So throughput is typically measured in megabit per second or gigabit per second. And latency, we typically think of higher IOPS means lower latency. And you'll have options of which of these you potentially could use. Now, when do you use which? When it's for object storage, we often use it, like I said, for backup, archival purposes, unstructured data like images, videos, backups, large data sets. The data is stored as an object. It includes the object, which includes the content, the metadata, and a unique identifier. That's that database pointer I was referring to, database-like pointer. So if you think about that, object storage is really great for anything that needs scalable, durable storage, and it can be accessed over an API, and that's one of the ways it's often accessed. So we have multiple options which we can talk about with regards to how redundant you want it to be, how you can manage your information, and potentially object storage can integrate into other Google services like BigQuery. Now, when we'll talk about file storage. File storage is just the standard kind of storage we normally use. It's what's in your hard drive. It's that hierarchical root, users, home, whatever, underneath that. But where would we use that in cloud computing? Well, where we use it in cloud computing is when we need multiple systems to be able to access the same thing. Let's say we have multiple servers that need to access the same content to give it to somebody else. This is where we use file storage. Because block storage, even though it's going to be local to the server because it's going to be like a virtual hard drive. But file storage itself, now that's different. That's shared amongst other users. So we often use these types of file storage. Google also has a managed file storage, their file storage they call Filestore, and it's a fully managed file storage system. And that obviously integrates fairly easily with Compute Engine for virtual machines that can access it, Kubernetes. So traditional, what we're talking about, file storage accessed over now. Now let's discuss the storage tiers you have with Google Cloud Storage, otherwise known as object storage. And Google has storage tiers just like any other cloud providers. And the storage tiers, as I mentioned, will be related to the availability and the performance. So let's walk down some of these stores. We have standard storage. Now this is the standard object storage offering given by Google Cloud. You can think of this as, say, AWS S3. It's Google's equivalent version of that platform. Now, this typically comes with some very good availability. In fact, with standard storage, we're talking about availability that's at least or greater than 99.99%, especially because with multi-region and dual-region environments, and 99% in all regions, or 99.99% in all regions. So this is good, relatively high available storage, and of course, it's also very highly durable, meaning if something were to happen and these systems were down, it's still going to be there. Now, we also have nearline in the Google Cloud, and what we're dealing with nearline is we pay less to put our data there. We typically get reduced availability, and the key with this for us to work is we really want to store our data here for at least 30 days, and that's going to be the minimum storage duration anyway. And the availability is reduced, and now it's 99.95 in multi-regions and dual region, and 99.9% available in regions. So we're actually lost a big level of availability, because if you think of standard storage, we had 99.99% in regions, and when it comes down to nearline, it's 99.9. So big difference in availability. But this is not designed for data that you need to access all the time. It's data that you need to access intermittently for a period of time. And you pay less to store your data here, but you pay a retrieval fee. So if you think of nearline, and then you want to think of like AWS by comparison, this is S3 and frequent access. So now we can talk about Google Cold Line Storage. Now here we're paying a lot less. We have to store our data here for at least 90 days. We're going to pay a retrieval fee for getting our data. And the availability is still really good here, or it's at least as good as nearline, in that it's 99.95% in multi-region and dual region deployments, and 99.9% in regions. So we're still dealing with good availability, but It's designed for low cost, but you're not going to use it that often. You need to store your data for, say, 90 days. And then we have the archive. And this is your longest term, lowest cost storage that you can possibly have, but you're going to pay retrieval fees to get it. So I hope this kind of helps. The last two are just, let's say, different versions of AWS Glacier that we'd be talking about. But those are really your storage classes when we're actually talking about the Google Cloud for object storage. And I hope those classes make sense to you. So let's talk about lifecycle management. Lifecycle management of data is typically going to be moving your storage around to the things that make most sense for you. And you may do this for the reasons of you want to optimize your costs. So let me show you what lifecycle management could be. You might actively use your data periodically. So let's map it out. So let's say we have new data. And this new data we're going to frequently access for about 60 days. So while we're frequently accessing it, let's keep it. And let's keep it in the most performance-oriented standard type of we have. So let's keep it in standard. Now let's say that we use this data all the time for 60 days. And then after 60 days, we may only use this data 5-10 times that much. So here's where we're going to put it in that nearline storage. Access, low, and intermittent. And let's say we keep it here for 30 days. And we'll set up a policy that says keep data here for 60 days, then move to, nearline for 60 days. And then what if at that point we're not really going to need it very frequently and we're not time sensitive when we actually need it? And we want to store it as low cost as possible. So maybe after 30 days, what we put it in cold line. And we keep it here for a long period of time, maybe 6 months, maybe 9 months, maybe a year. And at some point when it needs to be archived, then we move it somewhere else. So that's the point of lifecycle management, is to move your data around so you're going to pay the least cost for your data and have it when you need it, but find ways to make it less inexpensive. So let's talk about encryption that you're getting in Google Cloud. By default, the data at rest is going to be encrypted with AES 256-bit encryption, which is the standard now for the most part for encrypting data. And data in transit or in movement will be encrypted with TLS type security. For users requiring additional control of encryption, Google does support customer-managed encryption keys and customer-supplied encryption keys. And this gives the ability for high-security environments to have a little more flexibility and any kind of compliance they need for sensitive security workloads. Now, we can talk about backups and snapshots. So, obviously, you want to back up your data, but you also want to snapshot your virtual machine. And that is going to make it very, very easy for you to go build back your system. Let me whiteboard it out for you. So let's say we have a virtual machine. I guess I should call it compute engine since it is a Google Professional Cloud Architect exam. But let's say we've got this VM. I'll call it compute engine. So let's say we've got this, and you'll recall that we always have block storage here. And that's going to be the virtual hard drive. So this is block storage, otherwise known. Google likes to call it Google likes to call it a persistent disk. So, we've got this virtual machine. What we can actually do is we can take this virtual machine and we can create a bit-by-bit image. And this bit identical image is going to be a bit-by-bit copy of that entire hard drive into an image type file. And just think of that. So if anything happens to this server, it goes away. all you do is you use this bit identical image, and it will launch that identical server with every last amount of data on it, assuming it's every last amount of data, assuming you made an image of that drive that you have on it, and that's up and operational. This is, a snapshot, and you'll typically take these snapshots, and they'll typically be stored on object storage. And this gives you the option, and you can also do versions of this and create versions of this. So we could actually keep the backup of this version from today, tomorrow, the next day, the next day, the next day, the next day, and we could do it more frequently than that if we wanted to keep our systems great. So that is a snapshot. Now, the snapshot's different than a backup. A backup is when we take the hard drive or the block storage drive, and then we basically back up whatever data we want on a frequently thing, and we send this to something. It could be this is backup. This could be object storage, which we often use. This could be a backup tape. This could be a backup hard drive, but we're backing up the data. The snapshot's a bit by bit identical thing, one thing, and it reconstitutes the whole thing. And this is copies of your data. So it's similar but different. The reality is you need both of these, typically speaking, in a high availability security environment. If we think storage has evolved quite a lot over time, I mean, early hard drives were huge, and they stored less than a megabit of file. I remember having floppy disks, these 5 1/4 floppy disks, and I think if I remember correctly, they were 360K. And I think if I remember correctly, that was what we got out of them. But they didn't give us a whole lot of data either. And now I've got a 96 terabyte RAID array that sits right next to my computer. And it's only this big. It's kind of amazing to think about how we've grown so much. So keep that in the back of your mind. Now, when it comes to the cloud, they've already got all this storage that's actually ready for you. May cost more, may not. May cost a lot more, may not. And you'll have to figure that out for your business based upon your data needs and your data utilization patterns and where you store. But understand that cloud does provide a lot. But also understand there's a lot of analytics that can be done on this data, especially the data that's stored as data storage. So let's think of the future of data here. Organizations have now determined that data is a critical asset. And for all the AI things people want to do, the only thing we can train our models on is data and quality data. When it comes to AI, if we feed it and train it on bad data, then the results are bad. If we feed it and train it on pristine data, then our AI systems are much more likely to do what we want. So we need to think about data. We see GPUs growing every single day in their capacity in terms of managing data. We see CPUs that are getting better at AI workloads. There are companies that make ASICs, which are little chips that can do various AI things super fast, much faster than a GPU in many cases, but it can very specific tasks that they can do. So we have to think about all of these things. And Google's cloud focus is going to be on big data. They're going to focus on databases. They're going to focus on analytics. They're going to focus on a lot of data security. And if you think about Google, when they talk about data, they've got a little bit of experience in here, right? They've got advertising, which has collected all kinds of data to be able to target your advertising, which people you're looking for, which part of the world, with which hobbies. I mean, there's all this data they've got. So keep that in the back of your mind. So let's discuss Google Cloud Storage a little more. We have the concept of bucket labels. Now that's what we're going to label our buckets, or where we're ultimately calling it. And what it's going to use is it's going to use a key value pair to actually label the buckets with other resources. And that'll help keep track of what these things are. So we might use bucket labels for data classification or team ownership or billing, and we can put up to 64 labels per bucket. So we're storing our data, and that's what I said. We put a lot of information, a lot of labels, a lot of metadata on that label. Now, we also want to think about object naming and versioning. Anytime we deal with an object and object storage, the names have to be unique inside of a bucket, but not globally, which means I have to use the same things in, if I've got an object storage bucket, all those names need to be unique. But if I have a different bucket, I can use different names. Well, I hope that kind of makes sense to you. In a single folder, you wouldn't have two identical things that are typically speaking on your hard drive, and your hard drive wouldn't let you. It either overwrite the first one or ask you to change the name of the second version. But you could have two folders on your computer with the same name inside of each folder. So even though it's object storage, not file storage, it should be easy for you to remember. Object names must be unique inside of a bucket, but do not have to be globally. And with regards to object versioning, if we're using versioning, which normally object storage does by default, but the cloud providers may usually disable that by default, and then they give you the option to use versioning. And versioning means every time that file is touched or modified, it creates a new one and it stores the old ones for you. And by doing so, you've got access to many different copies. And that might be good sometimes. It might be costly, but it might be good. What if the entire team was working on something and the last version got corrupted? You can go back to the previous version. At least it gives you that. So good backups, all these things we want to do because we want to think about how do we keep our data as durable as possible. And versioning may help us even more. But the more versions we store, the greater our storage costs are. So it's an architectural trade-off. And what makes a good trade? The one that provides the business most of what it needs or is the best for the business after evaluating all trade-offs and the technology, the architecture solution, what have you. And we can, with regards to object lifecycle management, we can automate things. And we can automate deleting objects or changing storage classes based upon a condition like an age or a last access, or even the number of versions we have. Let's finish our discussion on storage. So now let's talk a little bit more about Filestore. As you recall, Filestore is Google managed a file sharing for you. And it uses something that's very similar to the NFS file system because it's basically file storage. It is just file storage. And because it's just like NFS, it's going to be what's called POSIX compatible. So if you need POSIX compatible storage, understand Filestore will give it to you. And you can use the last.d file to grow and shrink your clusters as needed, the amount of storage you actually have. And it's pretty good availability at 99.9%, for which, for a single file server, that would be, you'd get a little more than that, but it's not terrible for a single file server. And obviously, you can use more than one file server if you needed, and to use it to create your own high availability storage. But the reality is, for most people, 99.9% for file storage is going to be good enough. So I want to show you the difference between the way this works and what you would normally have to do. And then we're going to talk about how do you get your storage set up, what have you, and using the storage. So in a traditional environment, here's what we have to do to use file storage. So let's say we've got our server over here. And we've got our storage over here. These are our hard drives or our storage volumes or whatever. So let's just call this storage. What we have to do on a normal file server is we have to create a file share. And it could be a Windows SMB share. It could be an NFS share on a Linux machine or a Unix machine. And then what happens is other users or other servers that need to access the data, for example, can just access the data off of this NFS share. This is normally what we've been using for decades. And the only thing that you have to think of about this is, you have to manage this server and you have to manage this storage. Now, here's where things can get icky on this server. What happens when the server runs out of storage? What do? We either move to a bigger server that has greater capacity storage, or we create a different file share on another server. So the out of the capacity thing here, we have to maintain the server, patch the operating system. It's not that big of a deal, but people, try to make it sound so much scarier than it is. It's not that big of a deal, but, we'd have to manage the server. We'd have to manage our capacity planning, and we have to think about it. Now let's talk about what Filestore really is. Well, Firestore is basically Google has some type of device that's creating file sharing NFS like file storage. So in this case, you basically purchase your NFS file share for them, but it's called Filestore, and it's going to be very NFS like. And it's a managed service, so all you do is create your share, and all the underlying servers, all that make this possible, they're all managed by Google. Now, the other good thing that's kind of great is, generally speaking, Filestore isn't going to run out of capacity. So you can typically just use it and add more as you actually need it. So that is the advantage, the real advantage of the cloud. I mean, some people would say not managing the server is an advantage. Yeah, it is, but it's not that much of an advantage. But not having to worry about your file storage running out of storage over here and not having to think about that is a big win here. Let's really think about this. So how do we deal with this? How do we create a Firestore instance? So what we do is we create a Firestore instance, and a single NFS share is going to be created with default Unix permissions. And the instances must be in the same project and VPC network as your compute engine would be, or your Kubernetes engine clients, or your containers has to be, unless you're going to use some form of a shared VPC. Now, the IP allocation that Filestore can automatically select an available IP address that'll work, but remember, it's going to be coming from a private IP address, RFC 1918 private addresses. So why wouldn't you use something like this? You would use it when you need multiple devices that actually need access to the same data at the same time. You would use this anytime you would need to use file sharing, just like you used to use a file server. Now, I talked about block storage, and I talked about block storage being the virtual hard drives that we actually have. Now, we have to understand that block storage is going to be our best, but there are different flavors of block storage. Generally speaking, magnetic hard drives are a lot cheaper per gigabit or terabit than non-volatile memory express drives are. Now, NVMe drives are super fast and relatively low latency. Hard drives are not fast at all, and they have relatively high latency, but they're relatively cheap for storage. So when we choose a disk for our virtual machine, we have multiple options, and I want to talk about some of those options. We have performance persistent disk. Now, this is going to be the highest performance, meaning lowest latency storage we actually have. So what that means, the highest IOPS. It's going to be one of the highest we actually have. And this is going to mean lower latency, and it's going to be backed by hard drives that are going to be solid state drives. So this is going to be relatively good performance. Now, when we have a cheaper option, which is what's called the standard persistent disk. Now, this you could use. It's suitable for data processing workloads potentially that are not latency affected, and they typically use sequential input and output. Because remember, we're dealing with a hard drive that's going to be spinning, and if it's in a similar part of the drive, it's going to be easier to access and faster to access because the latency is going to be slow to search across the entire hard drive. So standard persistent disk is going to be relatively inexpensive, but it's not going to give you any good level of performance at all. Now, you can ultimately run into the extreme persistent disk, and it says they're backed by solid state drives. They are, but they're probably backed by NVMe SSD drives. Now, these are designed for your databases that require low latency and a lot of input and output operations per second. It's going to be one of the fastest things you can actually get inside of Google Cloud. So large databases, for example, you might be wanting to do this. So, and then we also have this balanced persistence disk, and it's going to be backed by SSD, and it's going to be really an alternative to the performance persistent disk, and it's going to give us balance of performance and cost. So it'll be somewhere, it's going to give us for virtual machines, you might use it for normal size virtual machines, not very big ones, because These disks have the same maximum number of IOPS as the SSD performance, but it's designed for general purpose applications. Let's discuss a little bit more about the persistent disk. And this is something really great about persistent disks in cloud computing, is that we can actually resize them. So let's say we thought we needed a 50 gigabyte persistent disk for a small server, and because it was doing very small things, wasn't going to be storing that much, and somehow it got filled up and we needed to change it to 500 gigabits. We can resize this, and we can resize this VM in the Cloud Console, which makes it easy to use. We can resize file systems using the resize 2FS or 2FS command that you typically on Linux, and that will enable you to scale to increase the size of your hard drive. So keep this in mind, that they're virtually attached. Remember, over a network, they're not physically attached to the actual server. One thing to remember is we can resize up, making it bigger, the disk, but we can't resize the disk down. Now, obviously, the highest performance, the lowest latency storage that we're ever going to get is going to be local to that server itself. So we have the option at times of using the local SSD for certain things, but we have to remember that it's ephemeral, meaning that it goes away if we get rid of the instance or the virtual machine. But what's happening is it's using the SSDs that are attached to the server. So this gives us incredibly good performance. Very high IOPS, which means very low latency, typically very good throughput. Let's think about where we could use this. Where could we benefit from high performance storage and not have to worry about the data basically going away when we get rid of the virtual machine? So we have a caching environment, or we need a scratch processing space. That's the kind of use case where we could use the local SSD and get that maximum performance and not have to worry about the information being ephemeral. So remember, that's exactly what's in the system. So if we have high performance compute that we need to do with a local SSD, media rendering, for example, some kind of data analytics, cache, any kind of load thing that we're not worried about storing the data later, that's where the local SSD will make sense.
Okay, so Leo and I are going to wrap up for the day. So, just want to give you that kind of guidance. I think we had a pretty big day. We talked about a lot of things, lots of compute, got into a little bit of storage, and that's what we're going to finish for today. Now, Leo, I know you're going to have some more labs that are going to be coming up. And the next thing we're going to go on to tomorrow will be things a little more on storage, and then we're going to go into databases. What labs do you have coming up soon, Leo?
Tomorrow we have labs of how to attach a persistent disk to a virtual machine, how to create a bucket, a cloud storage bucket, and how to host a static website in a cloud storage bucket.
Sounds terrific. And I'm going to end with Rohit's question, because it's a great question. Rohit asked how we can evaluate someone and let them know where they're at. So if you are a student of ours in our program, I'd let you know. For example, our students right now are working on an architecture. As soon as this boot camp's over, they'll be presenting the architecture back to us, giving us their RFP responses like they would in a real architecture, giving a presentation back to us, and we'll be able to evaluate them on their technical ability, their logic, the rationale behind their architectures, how well the business architecture and the technology architecture solve the problem, its relevance to the business, the presentation skills, the executive communication skills, and the CXO relevancy. And if I've got students that are ready, I can tell them right there, you're ready, because we train our people in architecture, and that's how we do it. But if you're not one of our students, and if you want to see if you know, I am more than happy on any of our weekly free architecture webinars. After we talk about what we do, and after we talk about the skills you need, and after we talk about how to get hired, if you say, Mike, could you tell me if I'm ready to get an architecture job, or ready to get a network engineering job, or ready to get an enterprise architect job, I'll be able to give you 3 or 4 questions that'll show me in about 2 minutes whether you understand architecture, and where your gaps are, because I'll go to a business thing, I'll ask you a holistic thing that'll get your perspective of the whole architecture. I'll be able to see your ability to evaluate trade-offs, and I can say, all you need is this cert, or you need this training, or you need to do this. And I'm happy to do it, Rawhead, and I do it completely free on our weekly webinar. So maybe come to the weekly webinar, learn what we do, learn the skills you do, and I would be honored to assist you in getting to your goals. Okay, Leo, we're going to say good night to everybody. I really grateful you stuck around a little longer. We're going to try and finish Thursday night and give you Friday completely off. And we did a heck of a boot camp here. We got involved into a lot of stuff. We got far beyond the concepts in the boot camp, and Leo gave you lots of demonstrations. So if you haven't given us a video like, maybe give it a like. If you're not a subscriber, maybe subscribe and hit the bell. And then Leo and I will be back tomorrow. Anything to say, Leo? Okay, I think Leo was... Leo got a little cut off. Are you saying welcome back tomorrow? We look forward to see you. Is that what I was reading essentially?
That's correct.
All right. See you all tomorrow. Have a wonderful night, and maybe give us a hashtag.